Bir dakika içinde hallolacak sanırım. Tamam, sanırım şu an bir problem yok. Ben içeriye alıyorum katılımcıları ve ondan sonra videoyu paylaşacağım.
Okay. So, I think I can start.
Yes, hocam, please.
All right. I would like to welcome all the attendees and participants to the second day of the second International Conference on Light and Light-Based Technologies. So I will be chairing the first session of the morning. I'm Alpan Bek from Middle East Technical University Physics Department. I lead the Nano-Optics Research Lab. Today in our session, in the first session, we will have 3 speakers. We have 1 plenary talk and 2 invited talks. Our plenary speaker today is Professor Viktor Kotlyar. He's from Samara University in Russia. And he's the head of the laboratory at Image Processing Systems Institute of the Russian Academy of Sciences. And he's also a professor of computer science department at Samara National Research University. And he graduated from Kubyshev State University. He received his candidate and doctor's degrees in physics and math from Saratov State University and Moscow Central Design Institute of Unique Instrumentation of the RAS. He's a prominent speaker. He has authored more than 400 scientific papers, 10 books. He is editor of several scientific journals, and he has several inventions as well. And his current research interests include diffractive optics, nanophotonics, and optical vortices. So if Professor Kotliar is available to turn on the camera and the microphone. Okay. Hello.
Hello. Hello, Professor Beck.
I think we have time for 50 minutes, including the talk and the questions. So if you could arrange the time accordingly, we would be glad. Okay.
Так, принять, что там? Экран есть? Я могу читать, да? Good morning, dear conference attendees. My name is Victor Kotliar, and I work at Samara State University, Russia. I wish to thank the chair and organizing committee of the conference for the opportunity to give a plenary talk at this conference. I feel greatly honored. My talk is entitled Topological Charge of a Superposition of Optical Vortices and prepared jointly with Dr. Alexey Kovalev. Не слышно? А что не двигается? Что не двигается? На экран вот он. Laser beam are known to be defined by two key characteristics. They carry an orbital angular momentum and have a topological charge. These are two different quantities characterizing the light field. Topological charge depends only on the phase of the light field, whereas orbital angular momentum is both phase and amplitude dependent. It is interesting that the same light field can have a non-zero topological charge while having zero orbital angular momentum, and vice versa. There are optical fields that carry a non-zero orbital angular momentum but have a zero topological charge. For some light fields, topological charge might be undefined. For example, this is the case for a coaxial superposition of two diffraction-free Bessel beams, since the zero of two different ordered Bessel functions are found at different radii. Therefore, topological charge of such superposition will take different values at different distance from the optical axis. While the orbital angular momentum of any paraxial light field is always conserved upon propagation, its topological charge can be either conserved, like for instance, topological charge of Laguerre-Gaussian or of the Bessel-Gaussian beams, or not conserved. Topological charge is equal to the number of the phase jumps by 2 pi when making a full circle around the isolated intensity null. See equation 1. However, Michael Berry has proposed a more fruitful equation to describe topological charge. See equation 2. The idea is to calculate topological charge along the circle of infinite radius. In this way, all possible phase singularities of a scalar paraxial light field can be taken into account. In my talk, I will use equation 2 to calculate topological charge of optical vortices. Equation 3 describes a longitudinal projection of the orbital angular momentum vector normalized to the beam power. After a simple optical vortex, equation 2 passes through an orbital amplitude mask of equation 3, its topological charge described by equation 4 remains unchanged, provided that the amplitude mask does not block a phase singularity center. It is shown noting that the amplitude of the mask can be not only binary, as is the case in equation 3, but also described by any real function which have no intensity null as the phase singularity center. This illustration show the pattern of intensity and phase of a Gaussian optical vortex. Number 5, bounded by sectored aperture in the initial plane following the propagation in the free space for two different angles. Sectored initial aperture 30 degrees and 45 degrees. In the phase pattern, 5 individual phase singularities can be seen. 5. So we can infer that a result of any amplitude distortion at nth order optical vortices is deintegrated into n simple vortices. Meanwhile, the total topological charge of the distorted beams remains the same and equal 5. If the center of a phase singularity embedded into laser beam is shifted across the beam cross-section, the topological charge of the whole beam remains unchanged. At the same time, such a shift causes of essential distortion of amplitude pattern of the beam. Substituting the amplitude of the such a beam of equation 1 in equation 2 for calculating topological charge, we find that the topological charge equals n. This result also applied to the propagation of the Gaussian beam through a shifted spiral phase plate of equation 3, bounded by circular aperture. Substituting 3 interrelationship for topological charge, we obtain equation 4, from which an interesting conclusion can be made. If the singularity is located at the aperture boundary after passing the aperture, topological charge is beam equals the half of the topological charge before the aperture, this one. If n is odd, topological charge after the aperture is half integer. Later in my talk, I examine the dynamic of the original fractional topological charge upon its propagation. This figure shows distributions of intensity and phase of the Gaussian beam with off-axis optical vortex in the initial plane and after propagation in free space for different values of the lateral of axis displacement of the vortex. We can see that the orbital angular momentum on equation 5 also deduced with increasing of axis shift of the singularity center. If the singularity center falls on the aperture edge, the orbital angular momentum is 0. Let us find the topological charge of a coaxial superposition of the finite number of optical vortices. Equation 1 describes a superposition of Laguerre-Gaussian beam with 0 radial index. Topological charge of the superposition given by equation 1 is described by equation 2. Tending to infinity, the radial coordinate r, in equation 2, we find the following. If m is greater than n, then topological charge of the beam in equation 1 is minus m. If m is less than n, then topological charge in equation 1 equals n. Summing up, we can infer that topological charge of a finite superposition of Laguerre-Gaussian beams equals to maximum topological charge of the constituent beams. We obtain a different result when calculating topological charge of superposition of a couple of Gaussian optical vortices. Equation 4 describes such a superposition, and equation 5 shows the corresponding topological charge. From 5, it's follows that if the absolute value A is greater than B, then topological charge equal to n. And if the A is less than B, then topological charge equal to m. If A equals B, then topological charge is half integer. The figure shows an intensity and phase of n-axis superposition of two Gaussian vortices with different topological charge, 12 and 7, but with the same weight amplitude in the initial plane and at the relay range. Red rings on the phase pattern mark the radius of a ring along which the topological charge is calculated. From the illustration, the superposition is seen to have half-integer topological charge in original plane, becoming integer upon propagation. Let us analyze how topological charge changes following an elliptic deformation at optical vortex.
Professor Kotler,
Yes.
could you switch to the presentation mode in PowerPoint?
PowerPoint.
Yeah, there is this button down below next to the magnification bar. Or yes, that's okay. Yeah.
Okay.
Great, thank you.
Так, подожди. Где тут там? Let us analyze how topological charge following elliptic deformation of the optical vortex. An elliptic vortex embedded into a Gaussian beam takes the form of equation 1. The parameter alpha specifies the ellipticity degree of the phase and amplitude. Equation 2 suggests that any ellipticity degree topological charge is conserved and equal n. Hence, the conclusion that an elliptic deformation does not result in the change the optical vortex topological charge. This figure shows pattern of intensity and phase for a Gaussian beam with elliptical vortex in the initial plane and after free space propagation for different ellipticity. From the figure it is seen that due to elliptical deformation as the nth order optical vortex with central intensity null is disintegrated into the n optical vortices with topological charge +1, which are arranged along the ellipse minor axis. Here we analyze the evolution of the optical vortex with initial fractional topological charge. In the general case, upon free space propagation of a paraxial optical vortex, its topological charge is not conserved, unlike the orbital angular momentum, which remain unchanged. As I mentioned earlier, Michael Berry has demonstrated that Gaussian optical vortex with initial fractional topological charge can be represented as a series, which is described by equation 1. Michael Berry has also shown that as the beam propagates, its topological charge integer in the new field. Integer in the new field. If the fractional part of the topological charge is less than 0.5, the integer topological charge of the propagating beam becomes equal to the nearest lesser integer. Otherwise, the propagating vertex has topological charge equal to nearest larger integer. This figure, however, upon further propagation in the Fresnel diffraction zone and as the focus of the spherical length, that is in the far field, such optical vortices start to behave in a different way, with their topological charge changing. This figure shows intensity and phase of the Gaussian beam with original fractional topological charge equal to 3.3. In the near field, near field, Fresnel zone, a far field. You can see that in Fresnel zone, at extra optical vertices, optical vortex with topological charge equal to +1 occurs. So then the topological charge of the whole beam becomes equal to 4. However, in the far field, one more optical vortex with topological charge by -1 appears, with the topological charge of the whole beam again becoming equal to 3. This slide depicts an experiment of the generation optical vertices with initial fractional topological charge. And intensity and interferograms were measured in the near field, Fresnel field, and far field. The measurement results for topological charge are given in the table. Let us analyze in more detail a situation of the odd integer part of the initial topological charge equal to 3.7, this column. In the beam center, four additional fork T's are clearly seen in the interferogram. However, in the bottom on interferogram, a characteristic defect of fringes can be seen, which reveal an additional vortex with topological charge -1. Therefore, for fractional vortices with the odd order 3, topological charge in far field equals 3. The experiment has confirmed that irrespective of the odd or even integer part, the initial fractional topological charge, the field with the odd integer topological charge is generated at length focus or far field. In this slide, I discuss an experimental study of an immunity of the integer topological charge to the phase distortions. A Gaussian beam is incident on a SLM where a vertex phase with number 5 is recorded. Each pixel of the SLM is being distorted by adding 2p alpha to its phase, where alpha is a random number from the interval 0,1. In the figure, column 1, the phase of the SLM ranging from 0 to 2 pi. Column 2 shows intensity pattern as the focus of the spherical lens, where an intensity ring is supported to be generated. And column 3 shows the intensity pattern as a double focal length from the cylindrical lens. Based on the number dark fringes, it is possible to determine the topological charge of the vortex B. The degree of phase distortion is getting higher from row 1 to bottom. The topological charge of an optical vortex is seen to remain integer and equal to 5 until random phase distortion of the initial vortex get as large as about half wavelengths. Let us look how topological charge of an asymmetric basal Gaussian beam is calculated. The complex amplitude of a usually basal Gauss beam is described by equation 1. It is easy seeing that topological charge of the beam 1 equals n. Equation 2 describes a complex amplitude of an asymmetric basal Gaussian beam. The asymmetric basal Gaussian beam of the equation 2 is derived as superposition on conventional basal beams with mathematically expressed using a reference series 3. From equation 3, The asymmetric basal Gauss beam is seen to be a superposition of multiple vortex beams, and the magnitude of its topological charge is not evident. Equation 4 shows that any asymmetry degree and any distance from the source plane of an asymmetry basal Gaussian beam topological charge equal n. This figure shows pattern of intensity and phase for the asymmetric basal Gauss beam in 3 different planes. At the center of the phase pattern, we can see an off-axis screw dislocation with topological charge 8. The Hermite Gaussian beams are known to carry no orbital angular momentum and have 0 topological charge. In the meantime, a superposition of 2 Hermite Gaussian beams with the phase shift, see equation 1, will have a not 0 topological charge. This can be inferred from equation 1, as its first term has n vertical 0 line and n plus 1 horizontal 0 lines. On the contrary, the second term in equation 1 has n plus 1 vertical 0 line and n horizontal 0 line. Hence, the intensity nulls in the equation 1 are found at intersection point of the horizontal and vertical 0 lines. Therefore, for field 1, topological charge is defined by equation 2. This one. Let us analyze a vortex Hermite Gaussian beam, equation 1. It would be difficult to determine its topological charge in a straightforward way because the constituent Hermite Gaussian beam in the superposition in equation 1 have complex coefficients too. But using a Berry formula, it is easy to find the topological charge of the beam 1. From equation 3, we can infer that topological charge of the beam 1 equals the number n of the Hermite polynomial. Figure shows pattern of intensity and phase for the vortex Hermite Gaussian beam in the source plane. From the figure, all intensity nulls and screw dislocation are seen to lie on the vertical axis. Let us complicate our task to analyze a superposition of 2 basal Gaussian beams with different orders, n and m, scales, alpha and beta, and power, en and em. See equation 1. What is interesting, in this case, topological charge of such superposition is defined by the competition between the basal function scaling factor, alpha, and beta, irrespective of the amplitudes of the constituent beams. If alpha is greater than beta, then topological charge equal to n. If alpha is less than beta, then topological charge is equal to m. Finally, alpha equals beta, the topological charge of the superposition is defined by equation 2. Putting En equal to Em and alpha equal to beta, we find that far away from the optical axis, the amplitude of field 1 is given by equation 3. From 3, the sum is seen to produce a vortices an infinity that has fractional topological charge equal to n plus m divided by 2 and n minus m intensity petals. But the vortex have fractional topological charge at infinity, which is termed as hidden phase. If n is less than m, then topological charge equal n will always occur as a center, and m minus n vertices found on the circle of certain radius. This figure shows a radius of circle of the topological charge jump from 2 to 5 versus the amplitude ratio. If the amplitude of the two beam is identical, then n minus m peripheral vortices go to infinity. Three-phase singularity found on circle as large radius are characterized by topological charge equal to 1.5, taking into account that there is a central vortex with topological charge 2. The total topological charge on beam 1 equals 3.5 in this case. It would be interest to analyze the evolution of the topological charge for superposition of two Laguerre-Gaussian beam with number n and m, see equation 1, and different waist radii, W1 and W2, see equation 2. Upon free space propagation, the waist radii get equal to each other at distance z0 in equation 2. We show that for an on-axis superposition of two different waist Laguerre-Gaussian beams with number n and m, the topological charge remains equal to m up to the plane, whereas the beam's waist becomes the same, provided that the Laguerre-Gaussian beam m has a larger waist, W2. And after that plane, the topological charge becomes equal to n. The explanation of effect may be as follows. There is an on-axis vortex with m in the superposition source plane. Which is complemented by n minus m extra vortices with topological charge equal to +1 and m minus m vortices with topological charge -1 found at different radii. This one. On approaching the set plane of interest Z0, the vortex with topological charge -1 depart to infinity. With higher than light speed, with the topological charge of superposition become equal to n. After this plane become equal to n. This occurs because after the border distance Z0, waist radius W1 becomes larger than W2. This picture depicts an intensity and phase of field 1 in the source plane. In the phase pattern, three singularities with topological charge +1 are seen to be arranged on the circle of radius R1, and three singularities with topological charge -1 on the circle with radius R2. The total topological charge of superposition and the illustration equal to. This equal to after border equal 5. Here, we may ask a question. It is possible to generate optical vortices with infinite topological charge. It turns out that such beam exists. Equation 1 describes a structurally stable cosine Gaussian beam which has a countable number of the intensity nulls, screw dislocation. The intensity distribution of beam 1 is described by equation 2. If alpha is smaller than W, where there are only two local intensity maximum in equation 2, two intensity maximum. This figure shows intensity and phase distribution as a beam from equation 1 in the source plane and after a free space propagation. Free space propagation in the phase pattern. The phase singularity points are seen to be arranged on the straight line, which is perpendicular to the line connected to intensity maximum. This line and this line. Considering that the beam under analysis is structurally stable, the entire pattern rotates as a whole. Entire pattern rotates as a whole. Also, the topology of beam 1 is infinite, but its orbital angular momentum is finite, as described by equation 3. This slide is one more example of a structurally stable optical vortex with infinite topological charge, phase singularity of which are found on the two Cartesian axes, and get thicker with increasing distance from the optical axis. See equation 1. The only difference, the beam 1 from the previous example, is the squared argument of the cosine function. This one, squared argument. Equation 2 describes an intensity of beam 1. From equation 2, it is seen that there is no on-axis intensity null, but there is on-axis intensity peak. Intensity peak, this C. It is seen that intensity distribution is shaped as 4-point star at one central intensity peak, 4-point star. The intensity null are located on the Cartesian axis, and the density grows from the center to the periphery. Since all these nulls are of the order +1, the total topological charge of beam 1 is infinite. At the same time, orbital angular momentum of the beam 1 infinite and described by equation 4. In this slide, it is demonstrated that using an astigmatic transfer edge dislocation are converted into optical vortices. Equation 1 describes two edge dislocations and embedded into Gaussian beam with astigmatic phase. As a double focal length, the amplitude of light field 1 is derived from the Fresnel transform as equation as shown in equation 2. Using equation 2, it makes intensity nulls double focal length. With increasing distance, two optical vortices are first generated on the horizontal axis, before converging at the origin, and then diverged along the vertical axis. Irrespective of the between line distance, such optical vortices has topological charge equal to -2 at any distance except for the source plane. With changing distance between zero intensity line, the orbital angular momentum, see equation 3, that the beam carries is changing, taking positive value, negative value, or zero value as a certain between line distance. Before concluding my talk, I would like to briefly discuss two novel remarkable laser beams. This slide depicts an expression to excite describe a propagation invariant of axis elliptic Gaussian beam that carry the orbital angle momentum, but have no topological charge. See equation 1. Relation 2 describes the orbital angle momentum of the beam 1. Shown in this figure, the intensity and phase pattern for two of X elliptical Gaussian beam characterized by different ellipticity and different of axis shift. The beam is seen to remain elliptic and rotate upon free propagation. Combining such elliptic beam, we can engineer more complex shaped beams that would only rotate upon free space propagation. By way of illustration, in this figure, they depict and combine three elliptic Gaussian beams that shape a triangle in the cross-section. The triangle is seen to remain its shape, only rotating upon free space propagation. Another promising vortex beam is worth mentioning. All currently known Bessel beams are not Fourier invariant. For instance, a Fourier image of a diffraction-free Bessel beam is a narrow intensity ring. However, Fourier invariant Bessel beams exist. This slide example of a Fourier invariant Bessel beam, see equation 1. Equation 1 gives the amplitude of the Bessel in the source place. And equation 2 gives an amplitude of the beam in the far field Fourier plane. Both amplitudes are seen to be polar variable dependent in the same wave. This beam is physically realizable since it is a finite energy. Also, it does not contain Gaussian envelope. The main difference of Fourier invariant Bessel beam from the Bessel-like beam is that former have low side lobes. My conclusion. Okay. So far, there is no general proof of the conservation of the topological charge during free space propagation on the arbitrary scalar paraxial optical vortex. The fact is that in the course of propagation, some beam individual phase singularity can hide at infinity. Experimentally, such screw dislocation cannot be detected. By the effect, the value of the total topological charge. During free space propagation, an original fractional optical vortex has an integer topological charge, but this integer topological charge can increase or decrease, dropping by 1. There are optical vortices with an infinite topological charge, but they carry a finite orbital angular momentum. The topological charge of the superposition of Laguerre-Gaussian beam equal to maximum topological charge among the constituent beams in the superposition. Topological charge of couple of Laguerre-Gaussian beam with different waist radii is equal to the topological charge of the beam with the greater waist radius. Upon free space propagation, screw dislocation of the optical vortices can move in infinity as a greater than light speed. Thank you for your attention.
Okay. Thank you, Professor, for this very interesting talk. I think we have time for a few questions. So we can, let me look for questions.
Questions.
Well, I do have one regarding this triangular beam that you showed in one of the last slides. Yeah, that sort of beam is another way of interesting helical beam in a sense, right? It rotates as the beam propagates, and so it does carry an optical angular momentum, right?
Yes, this beam has only orbital angular momentum, but has no topological charge.
Yeah.
This beam is structurally stable and in free space only rotating as whole.
Okay, so besides the helical beams that we typically know of carrying optical angular momentum, so interesting variants of the beam shapes can be thought of in developing applications to transfer momentum to, for example, rotate nanoscale objects, etc. So that's really interesting.
Thank you.
Any other comments, questions from the audience? Okay, there is one. I'll read the question. It's from Fatima Nourani. She's saying, thank you for a good presentation. Do you think the topological charge will change or remain constant during the propagation of in a nanostructured solution?
As usual for Laguerre-Gauss, Bessel-Gauss beam, topological charge is non-change upon propagation.
Mm-hmm.
But there are some beams for
свободном пространстве, это в наноструктурированном растворе. В отличие от, вот если ты будешь не в свободном пространстве, а в наноструктурированном растворе, он сохраняется.
Okay.
If this solution have helicity, topology will be changed. If solution not helicity, as also scattering, topology charge will not be changed.
Okay, thank you, Professor, for the answer. I don't see any. One more question from Savino Chavez. She's saying, very nice talk. The Fourier invariant Bessel beam in your last slide with squared argument is the limitation of extent and thus of propagation, as it will be limited by the wavelength of the light.
No, the Fourier invariant Bessel beam show in this slide don't independent for wavelengths.
So,
this beam
have been obtained within the paraxial approximation.
This beam obtained as in paraxial approximation.
okay, all right.
Beam waist radius should be much greater than the wavelength. The beam width should be much greater than the wavelength.
My
Yeah. Okay. Professor Chavez is saying the Bessel function oscillates faster and faster until it reaches the period of the wavelength, and beyond that it must decay.
Faster, faster, when.
Until it reaches the wavelength in the period of equals to the wavelength, and afterwards it has to decay.
Почему без wavelength? Sorry.
Okay, I think that's a nice point, and
Yeah, I see. Argument Bessel function is square, because yes, you right. Zero, this function decay from 0 to infinity.
okay.
Yes, decay.
I thank him for the comment, and also to you, Professor, for the answer. So I think we can stop here. I would like to thank Professor Kotliar once more for this nice talk and explanation.
Thank you very much.
We can now proceed with the second talk of the day. The second talk is an invited talk, and it's going to be given by Professor Hümeyra Çağlayan, and she's with the Faculty of Science in Department of Physics in Tampere University in Finland. She's leading the Metaplasmonics group. She received her PhD degree in physics from Bilkent University in Turkey, and where she investigated novel electromagnetic phenomena in metamaterials and plasmonic structures. And after she finalized PhD studies, she worked as a postdoc together with Professor Nadir Engeta group at University of Pennsylvania. And her group focuses on engineering the fundamental interaction between light and matter at the nanoscale for plasmonic and metamaterial-based devices. And she's a recipient of ERC grant for 2019-2023. She's also a close friend of mine. So, hello, Hümeyra.
Hello, good morning, everyone. Thank you, Alpan. Thank you.
Okay. So,
Hümeyra, welcome.
Thank you very much, Simon Hocam. Thank you. It's very nice to be here, even virtually.
I think we have 30 minutes for the whole talk. So if you could tailor the time accordingly.
Yeah. Let me share my screen here. And then I think, yes. So thank you once more for the invitation. It's really, I mean, this is a really amazing conference. I would like to also congratulate all the organizer committee putting this together. I know that should be quite a hard work. Yes, and thank you, Alpan, for the intro. Without further ado, let me get back to my presentation. Today, I will talk about, actually, the title I have chosen was light matter interaction control with multi-layer epsilon layers or metamaterials. Yet, I think today I will touch only actually the light matter interaction with, like in the nonlinear regime. Still interesting, I promise. So just before I go to the presentation, maybe those people who doesn't know much about the Finland and the Tampere University, just want to give you where I am at right now, so that you can imagine where I am sitting at. So this is the Finland. It's been quite a north from the Istanbul and Ankara, and then in Finland, Tampere is a little bit north of, it's inland, and then inland city, and a little bit north of Helsinki, and yet there's still a lot of north to go. But the good thing is that we have a really nice campus, as you see here, and our lab is actually located over here, where I am right now. So it's a good place to, as you see, nice green area, but also it's nice that if you're working on light matter interaction, it's also a great opportunity to see really nice light matter interactions going on. I would invite everyone to if you have the option. after COVID, of course. And this is where we do our light matter interactions, actually, other than in a different scale. This is where we do our work and investigate light matter interactions. This is just a quick peek to our lab here in Tampere University. It's located in Red Labs. So today my topic is about epsilon near zero metamaterials, but before I go into the detail of those metamaterials, I would like to point out the extreme parameter materials. What are we talking about? Since the start of the metamaterials and even in general materials, people have been looking for different materials, and these materials have different permittivity values, and that can give you different optical interactions with the light. This permittivity, which I will refer epsilon in our case, it can give you quite interesting properties when it is quite large, and such as like interesting scattering properties, and you can do different control with the scattering. Quite nice examples there. But actually, I'm more interested in this epsilon near zero case, where we have the epsilon, the permittivity value that is getting closer to the zero. There are some quite interesting things happening there, which I will touch briefly, but this has been an interesting topic for now more than 10 years, and people have been looking for different applications. I think mostly it started with supercoupling, but it evolved into many other things. One of the early examples also I studied was optical nanocircuits using these wonderful materials, and they can give, for example, one of the highest frequency operating nanocircuits. Really, really interesting topics. Of course, one can ask then, like, okay, you're talking about something interesting here, but do we have those materials? Actually, those materials are available in nature. One of the best examples that I highlighted here is ITO, indium tin oxide, which is a transparent conducting oxide. It is actually, the funny thing is that it is actually something that you might be looking at right now, because it has been used in the screens, either on your phone that you're looking at right now, or they're on screen on your laptop. That is what you see. That is the material. And the silicon carbide is, just one thing with the ITO before I forget, that it operates, actually the ENZ wavelength is around 1.5 micron, 1.4, 1.5 micron. And another example, which is again available through nature, is that silicon carbide, though the epsilon near zero wavelength is around 10.3 micron. There are other examples like aluminum arsenide that is actually around like 8 micron, I believe, and other transparent conducting oxides available. Titanium nitride has been used, although a little bit lossy than this, but that's still an option. It's a visible option, but not easy to obtain, titanium nitride. And then, of course, there has been, now comes the structuring and the metamaterials. One of the options, I think the good option, is that you can combine metal and dielectric, and you can create your own epsilon near zero medium. Another option, which we have also shown, is using a waveguide operating at a cutoff mode, but that is a whole lot of things going on there, and for the sake of the time, I'm not going to touch on that at all today. So let's get back to it. So this is, for example, an example of this material. It's an aluminum doped zinc oxide. I think one of the good things, as I mentioned, for those transparent conducting oxide, indium tin oxide ITO or aluminum doped zinc oxide AZO, is good. They are really nice, and they have a low imaginary part as well, not just the real part, but also the imaginary part. Yet they operate in the near infrared range. It might be good for some telecom applications. There's no doubt on that. But then the question is that it comes to is what are we going to do if we want to make an application for the visible range? Then you're a little bit limited. You don't have a lot of options. Like if you would go to the metals, which obviously should have an epsilon near zero, yet in the UV, and also the imaginary part was quite high. That's why you're kind of like a little bit of a gap here. And then there comes the game of metamaterials that we could do, and we could arrange it. Ourselves. I'm going to show you an example today. Actually, 2 examples today that we have fabricated. What we did is that we take the advantage of metal and dielectrics, we combine them together, and this is a metamaterial that has been used and known and called hyperbolic metamaterials for some time now. And the good thing about them is that you can arrange the thickness, the metals or the dielectrics and the compositions, and then you can play with the EMZ wavelength. Therefore, what we did is that we tried to simplify a little bit, and then we tried to focus on options that are available that might give us 2 different wavelengths. One is around more 600, one is more around 700. And then what we did, we kept the metal layer, in our case it's gold, fixed thickness, it's 10 nanometers, and changed the titanium dioxide, which is a dielectric layer, either as 25 or 45 nanometers. Maxwell-Garrett approximation has been used for these kind of metamaterials, and that's what we did. And this is the calculations that you have seen here. It gives you the permittivity value of these metamaterials, and the calculations gives us that these metamaterials can work really nicely for different wavelengths. And these are, I think, these were good for what we aimed in this project. And then just for the completeness of the story, I'm just going to show you the transmission values of these 2 hyperbolic metamaterials or metamaterials, and where it has a certain ENZ wavelength in the visible range. And they're in a good agreement with what the calculations that we had done so far. I think the overall thing that I would like to highlight from these introductions is that first we needed the visible range ENZ medium, and then the best options that we could have is using metal and dielectrics, and that's what we did here. And that is actually good because it has a good publication quality. It's not that complicated, and it's easy to change and tune. And you can have a different options. Either you can use different metals or different dielectrics and different thickness, etc. So you can play around in the visible range with quite a flexibility. Yeah, and now let me go ahead and explain you actually mainly why I want to go to the nonlinear and not just stick with the linear. Linear part is really nice and fun. We did also a lot of work on that, but today I'm not going to explain those. And these materials, just to summarize again, they have near zero optical parameters. They have a low wave number. That's where they have the high phase velocity, and these are also all relevant for our case as well. And then basically what happens in the end is that they kind of have this stretching of high frequency signals. And one of the very nice examples on this is the supercoupling. And just if you're interested in more, I would recommend these. I would like to highlight these, especially these 2. One belongs to this really nice science paper by Nader, who is my postdoc supervisor as well. And then I would like to now, based on all these nice and useful features, I would like to go to the enhanced nonlinearity. So this enhanced nonlinearity is always been an issue. I think since people started looking at light matter interactions, using nonlinearity is always a good and useful. And I think that is why we have now so many applications on that. But from the ENZ material or ENZ metamaterial perspective, it is even getting more interesting because it kind of acts a little bit differently. If you look at here, this is the nonlinear index that we all know. And then here we can, this is definitely depends on this N0. But keep in mind that for our case, N0 is almost 0. So that's why we have quite an enhancement in the nonlinearity. And of course, we are not the first to show this. This has been studied with natural ENZ materials, not as metamaterials, but the ENZ, like an aluminum doped zinc oxide or ITO. This is one example. I think this is one of the earliest examples from Shaliev's group, or then Shaliev's group from Purdue University, that they have used this aluminum doped zinc oxide, and they have shown that it's a nice ultra-fast switching at the telecom wavelengths. I wanted to highlight here especially, I would like you to keep in mind this data over here. Here, two important things, please take into account, that like the change in the reflection and also the timing over here, like how fast this would be. And then later on we can come back and compare what we obtained. And this is from the Boyd's group. Bob Boyd showed in their science paper that we can use ITO as well. I think this is a little bit thicker than what we have in our study, but yet they have shown really nicely also how you can tune and change the index nonlinear with the nonlinearity. Okay. So just to bring you back, what we aim here is that we aim for all optical simple design, and we aim for visible range. We want to achieve the highest modulation of this permittivity change, and last but not least, the ultra fast. These are our key points to attack. And again, as I explained, why we needed this structure, why we needed to create our own ENZ medium. This is what we have at the end. So what we did fabricate gold and titanium dioxide layers on a fused silica, and this is a cross section of the cross section of the structure through the SEM images, and I think the fabricated layers more or less was on the correct thickness layer that we aimed for. Again, we used gold and titanium dioxide. Gold is around 15 nanometers and titanium dioxide being around 37, 35 we aimed for. I think I have seen some, okay, I was going to check some. I thought maybe some questions on the chat, but nope. Okay, then let me continue. So what I think first thing to do is, of course, to check the linear properties of such a structure before we go to any kind of nonlinearity thing. And then what you see here is the calculation as well as the experimental value. We did two different calculations, and I need to explain why we needed both. So we wanted to do this transfer matrix calculations, because definitely we would need it afterwards, especially when we need to calculate the permittivity values using inverse TM method. But also we wanted to make sure that this TMM method, which so to say ignores the local effects, should be included. Therefore, instead of making this TMM code even more advanced, we just compared it with the FDDT, and it seems like they are all okay. They have good comparability, and we can consider both our experiment, and the TMM works fine in the linear case. So that then therefore we can move to our nonlinear measurements. And this is my last slide before I show my experimental data. So this is the extraction of the effective permittivity. What we really need to do to show you that there's a good change of tuning of the permittivity with this nonlinearity thing going on, we want to make sure that we calculate the permittivity for the linear case as well as the nonlinear case. But of course, we started with the linear case. For those who are not much familiar with the with this TMM method, I think what we did is basically we used this matrix and then we included all those layers, the index of all those layers. And then based on that, we also make an inverse transfer matrix calculations. So what we did, we said that we know what is reflection, we know what's transmission and incident. And so based on these, this code should give us what is the effective permittivity or index of this medium. And this is what we calculated at the end, and this shows nicely that this complex permittivity around 600 nanometers, which is actually what we wanted to have. Yes, so far that is all about the nonlinearity. And for the nonlinear investigations, what we did, we used this transient absorption spectrometer. Just very briefly for those, maybe our younger audience who may not that familiar, is what we do. We pump the sample. We send a very short, high-intensity pump to the sample and then look for the spectrum change for the probe signal. In our experiments, we fixed the pump pulse to 400 nanometers because we thought that that is the best absorption for this sample that we used. And then for the probe pulse, we look for the visible range. So basically, we are pumping, we are creating an energy, we are populating the electrons, and then we let it go and look for what's happening on the probe. That's why actually we can control, this is really good that we can control the delay between the pump and probe. So we can pump and we can decide how much we would like to observe and see the change on the delay. But if you would have further questions, I would be happy to answer at the end. So what we did, so these are then our results. And we obtained, just keep in mind briefly that this is the change in the reflection compared to the linear case. That's why in the beginning it was so important for us to get really good results on the linear cases. And this is the change in the transmission compared to the linear case as well. You may see here that there's a change both in the transmission and the reflection. And then what happens here is that when we pump, the energy is redistributed. Especially in this conduction bank electrons change with this femtosecond excitation of this light source. We change all the energy distribution in the system. Now we are coming back to the case where we look for the spectral change. Now it's not the delay anymore. Just keep in mind that this is now the spectral change. And again, I'm plotting here the change of the transmission and change in the reflection. Here, you can see that we have a couple of different lines, and each of these lines correspond to different fluence value. So we can change the intensity of the pump, and that is what you can see here. We wanted to do that because it will be quite useful later on when we want to do some calculations, and I'm going to show you there as well. So here we can easily say that as a conclusion of these two data, that the distribution change in the conduction band electrons with this pumped system there will be changes in the reflection and the transmission. Am I over time?
Yeah, I was going to ask if you could wrap it up in a minute or two.
Sure. And then we showed that based on these calculations, we showed that the permittivity value is going to change, and then this also gives us a change in the wavelength of the epsilon near zero. And just to say that this change is quite remarkable, although in terms of it might show little. It's a quite remarkable and quite comparable with what has been obtained with the indium tin oxide so far. These are some calculations. This is done by the two-temperature model. This has been quite a common model that is being used for these kind of transient absorption spectrums. What is most important, remarkable thing here is that you may think that all the electrons comes from the gold, and then that might be all the nonlinear effect is coming from the gold for this kind of system, but that's not the case. Because if it will be just gold, this is the G, this coupling constant that is for the gold. But when you actually use this for the gold, you cannot match it with the observed data. Therefore, then we saw that this effect is mostly due to this epsilon near zero effect of this sample. And then one last result that I promised, that there should be an ultra-fast change in the sample. That is what's happening here when we pump here, that you can observe that the relaxation back is quite phenomenal. So it can come back to the relaxation in 3.3 picoseconds, and if you would consider that for ultra-fast switching, it will correspond to something like 0.5 terahertz of switching rate, which is really important. So some of the take-home messages, I don't want to hold you more, but then the most important is that we showed for the first time that we can use this ENZ metamaterials and obtain a nice, good tuning range with this metamaterials, and then you can obtain a nice dynamics of the hot electrons using the two-temperature model. And the relaxation times and the rising times are quite high. That gives you very good systems for the optical switchings and modulators operating in the visible range. And for more details can be found here. And then with that, I would like to thank all my team members and all the funding agencies. And I will be happy to take some questions.
Okay, thank you so much. First, we can maybe take questions from the audience. There is one from Cenk Ceylan, as far as I...
Sure, I can read it. So thanks Ceylan. So for the supplies light emitting by monoatomic gold, what think about metamaterial coupling? Monoatomic gold. Well, I think I didn't get the question very well. Alpan, did you get it?
I'm not so sure. There might be a typo in the...
Okay. So if you're asking, Cenk, that if what happens if we use the monoatomic gold layer, that might be an interesting question. We haven't done it. I think you're talking about maybe single crystalline gold layers. I don't have an answer yet, but it might be an interesting.
Okay. Any other question from the audience? Because I do have one I'd like to ask if the time...
You seem excited, Alpan. Ask it.
All right. In the implementation of the transmission line or transfer matrix method,
yes.
The layers are too close to each other, so that there will be some induced polarizability of each other. I mean, when you use that, you typically take the bulk values and use it in kind of in the far field in a straightforward fashion. But when things go into near field coupling, then there are strong induced polarizability effects. So do you take into account those effects when implementing the transfer matrix?
I think no.
So bulk values are used in the matrix elements, as far as I understand.
Pump values, you said?
Material parameters are used for the bulk.
Yeah, so we started to first investigate this method itself, first of all, and we did all the calculations for the linear case. And once we confirmed that for all the calculations with the experiment and inverse transfer from this linear case matches nicely with this calculations, then we implemented to the nonlinear case. You're right, actually, there might be some effects coming from this to this equation, and I think which has been elaborated in one of recent papers in Nature and Getas, but we didn't observe much difference using directly this one compared to adding different like local effects, etc. Therefore, we just stick with the just Maxwell-Garnett equations for the effective permittivity, and for the effective permittivity using just gold and titanium dioxide properties would enough. I think it might be more effect if you would use a structured case, like if you would structure this that might have some nonlinear and local effects there.
Okay, thank you so much. By the way, it's a very modern architecture I can see in the background.
It is. You should come and see.
Yeah. Süleyman Hocam, please consider.
Okay, Humayra, thank you very much for your valuable contribution to our event.
Thank you for invitation. Thank you.
We see your face-to-face event in near future.
I hope so. I hope so. Let's hope that this COVID goes away and.
Thank you very much.
Okay. So we can, thank you so much again. We can continue with the last talk of this session. There is going to be other sessions, of course. Please don't leave. Our next speaker is Dr. Matteo Degani. He's from Department of Physical Chemistry in University of Pavia in Italy. And I didn't see too much of information from the conference page, but maybe he can explain a little bit what he's involved in recently himself, as he is together with us.
Yes, can you hear me?
Yes, yes, perfect.
Okay, so I'm gonna present my work. Can you see my screen?
Mm-hmm.
Okay, perfect. So, good morning, everyone. Thanks for the kind invitation. Today, I will talk about efficiently inverted perovskite solar cell by dual interfacial modification. The outline I will follow is this one. I will start with a short introduction in which I'm gonna talk about solar cells, and I'm gonna talk also about the material I'm using to fabricate the devices. Then I will talk about the objective of my work, and I'm gonna present experimental results and then conclude, and finally I will present the conclusions. So the motivation of my work fits in the global changes to make energy in a more suitable development. Why solar energy? Because solar energy, among all the renewable energy sources, have the largest and the biggest amount. The largest and biggest source, that is the sun. Even converting only even less than 1% of the solar energy, it will be enough to satisfy the human energy demand. And according to the International Energy Agency report, solar energy will cover up to 40% of global energy demand by the 2050. The challenge in solar energy is a revolution in PV technology, since silicon technology that nowadays covers 90% of the market is not a good solution, since it's energy consuming and really high and have a really high cost due to the process that requires a really high temperature. So what we need is a new technology that is low cost and adaptable, that can satisfy the demand in everyday life. Hybrid perovskite solar cell can be a good solution for this revolution, since they saw an increase in efficiency in less than 10 years that no other solar cell seen before. And also this technology, among these high efficiency, this technology is based on low cost process and low cost materials. So talking about this material, we can represent the structure like in this figure, where the with the A position is occupied by the organic cations like methylammonium or formamidinium or cesium. The B position is occupied by lead or tin, is the metal cation. X position instead is occupied by the anions that are halides. We can represent the bulk structure like in the 3D form, like in this figure. These materials have really good optoelectronic properties for PV application, since they absorb in all the visible range. But unfortunately, these materials have a huge problem about stability, since in presence of moisture or oxygen degrades, causing a drop in the PV performance. Exists another family of perovskites, the so-called 2D perovskites, that we can obtain substituting in the small organic cation with a larger one, like phenylethylammonium or butylammonium. The properties of this other family of perovskite is completely different, since they are more robust in terms of stability. They don't suffer so much about moisture or oxygen. And as shown here, the PV performance is not dropping in time as the other one. Instead, Instead, the PV performance are not suitable for PV applications, since the narrow absorption, as we can see in this graph. So the goal of my research is mix 2D and 3D perovskite, these two structures, to get a high efficient solar cells thanks to the optoelectronic properties of 3D perovskite and stability of 2D perovskite. The starting point of my work was to build this device. It's a PIN structure where we can find the active layer perovskite with this formula that is called the triple cation, that is in a sandwich between a whole transport layer, in this case PTAA, and electron transport layer, PCBM and BCP. For fabricate this device, I use a whole solution process. So basically, I'm depositing layer by layer all the materials with steps of with the spin coating technique and annealing steps. And only the metal contact is deposited by evaporation. Two steps that I need to mention are the so-called DMF wash, that we need this step to improve the wettability of the PTAA surface, since the high hydrophobicity. If we don't do this step, the perovskite layer doesn't stick, and so the performance of the device will be really low. The second step I need to mention is the anti-solvent step. This consists in a deposition of an orthogonal solvent on the top of perovskite to improve the crystallization of the perovskite layer. As is shown in this short video, the deposition of the perovskite is made by the spin coating technique, and the layer is almost transparent. But then, after the anti-solvent step, we're gonna observe that the layer is gonna change color because of the crystallization. And after the annealing step, we're gonna observe a blackish layer, like the one reported, shown here in this figure. So this is the anti-solvent step. from almost transparent, the film became brownish, and after the annealing, it's gonna become blackish. So with this technique, it's easy to get a good photovoltaic device with an efficiency above 20%. So now my work started to how mix 2D perovskite, 2D perovskite in the 3D one. The first way, the cations I used are these one. The first one is PAI, is a pioneer of 2D perovskite. Meanwhile, the second and the third one are more recently synthesized. To mix them, I dissolve in the DMF, in the so-called DMF wash, a small amount of these cations. And as shown here, the wettability of this PTAA layer improved. Since I used the same amount of perovskite solution, in the first case, using a pure solvent doesn't spread on all the surface. Meanwhile, in the second, using the new using solvent, dissolving the A cation, the perovskite solution fully covers all the substrate. And in the PV performance, we observe an increase of the fill factor. The second way we mix the 2D perovskite in the 3D is dissolving a small amount of the cation in the anti-solvent. So we will deposit on the top of the perovskite layer. And after making this device, we observe in PV performance an enhance of the VOC, as is shown in this box chart. So doing dual interfacial modification on the bottom part and also on the top part, we expect to observe an increase of VOC and the fill factor. And actually, what we managed to get is an increase of the efficiency above 23.5% efficiency. That is the world record for this kind of structure. To understand this improvement, we did other characterization that I'm gonna present. So the first one is the XPS measurement after the DMF wash. We use this cation because it can be easily detected since there is the presence of the fluoro element. So in this sample, after the deposition of the A cation on PTAA, we perform XPS and we observe the fluoro peak in a clear way. So we can say that actually we can confirm the presence of this cation on this surface. We perform also in the top part the XPS measurement to observe if also in this case we have the presence of this cation, always with our FPAE since it's easy to detect. And what we observe is also in this case we have the peak, but and also we perform with an argon cluster ion beam an etching on the sample to observe if this cation diffuse in the bulk of the perovskite, in the triple cation perovskite. And what we observe is that after 30 seconds, the fluoro peak disappears. This allows us to say that the A cation only stays on the surface of the perovskite. And is not diffusing during the annealing stem, for example. And also with this etching time, we can estimate the thickness of the A cation layer, and it's even less than 1 nanometer. We took SEM pictures, and as is shown here from top view and from cross-section view, there are pinholes and voids in the sample. Meanwhile, after the treatment, dual interfacial treatment, we don't observe anymore any hole, or they are only few of them. And even in the cross-section, the layer is there is full adhesion of the perovskite layer on PTAA. This allows us to motivate, to to explain the increase on the fill factor. Since there are no more voids, no more pinholes, so the fill factor increase. We perform also X-ray diffraction, and from these and from these comparing the first peak 100 to the second peak 110, we can observe that the ratio is increasing. That means that the crystal orientation is higher after the dual modification, like represented in these figures. So in the first case is shown the reference, in the second one is shown the dual interface modified sample. We perform also PLQE and the ELQE measurement. From photoluminescence, we observe respect to the reference, the other sample show an enhancing emission, and these allow us to hypothesize less non-radiative recombination. Then we perform also ELQE measurement to quantify how much is the quantity of non-radiative recombination present in the samples. And with this formula, we quantify this non-radiative recombination. And as is shown in the table, the non-radiative recombination of the reference is higher respect to the passivated samples. We also managed to quantify the parasitic resistance through this equation. We perform a fitting plot to quantify the shunt resistance and the serial resistance. And as expected, the shunt resistance in the dual modified samples, there were an enhancement. And for the series resistance, they were becoming lower, as is shown in the graphs. This is according to what expected, since there were an enhancement of the fill factor. Then we perform a stability measurement under continuous illumination in different with a stability box. And the first step was to perform it in a nitrogen atmosphere. And after that, we perform in a dry atmosphere. And even after 900 minutes, there were no drop in the PV performance, even if there weren't any encapsulation. So in conclusion, we can say that interface engineering is crucial to have a high quality perovskite solar cell. And the modification we perform give us the perovskite layer became more oriented in the direction 100 with less no recombination, and also enhance the quality of the fill. These improved the efficiency of the perovskite solar cell up to the world record for this kind of architecture. This work is already under some revision, so I hope it's gonna publish soon, and so everyone can read and have more information about it. So I would like to thank you, the German group where I did most of the work, that is the University of Dresden. And I would like also to thank the Italian group in Pavia. So thank you for your kind attention, and I'm open to questions.
Okay, thank you, Matteo, for the very ambitious work and for this nice talk. I would like to just remind the audience before the questions, please don't go anywhere. There will be a photo session, okay, just after the session. So we can take questions to this talk from the audience. I see no questions at the chat box, maybe. Oh, yes, there's one. Okay, Matteo, can you read it, or shall I read it loud? Yeah?
Yeah, I can read it. So I think, yeah, perovskite is the future since the low cost and the low cost process, since the most expensive part of perovskite solar cell is the glass. And I mean, obviously in my work, we use solution process and we made everything about with spin coater technique that is not really scalable, but in any case there are many other options, and yeah, I strongly think this is going to be the future.
Okay, thank you. Any other question from the audience? You said you talked about the stability even without any encapsulation.
Yes.
Are there any encapsulation prospects? Do you work on that also?
Yeah, we are working on that, but it's a kind of a tricky problem because depending on the glue and depending also how we used it, we can have a drop of the PV performance. For example, I use also a UV curable glue that destroys the perovskite after 2 weeks. And yeah, it's, I mean, it's protecting, but then it's destroying the sample. So it's a bit, it's a waste.
Maybe you need to develop yet another interface.
Yeah, definitely there is, we can, I mean, there are studies about engineering also encapsulation and having, for example, with polymers, fluoropolymers, for example, and they are really promising. So obviously the dry atmosphere is only a proof of concept, but then I think also encapsulation will be a crucial point on the development of perovskite solar cell.
Okay, one other thing that came to my mind is people talk about tandem perovskite cells, tandem with the silicon solar cells. So 2-port, 4-port tandem cells. Do you think these interfacial layers are compatible with tandemization of the perovskite cell?
Well, actually, Oxford is working really hard on that, and they are developing they developed recently a really high performance cell, and I think can be. I mean, the interfacial is going to be crucial also for to build tandem cells, because also there are a lot of recombination and can be really hard to get a good efficiency if you don't have a proper interface engineering.
Okay, so people are working on that.
Yeah.
All right, thank you so much. I think I don't have any further questions and I don't see any more from the audience. So I thank you once again, and I would like to thank all the speakers of this first morning session. We can, I think, go ahead with the photograph.
Okay, thank you, Professor Beck. Hello again. I have authorized the participant to open the camera now. Please, can you open your camera and smile, please? Okay, nice. And I will wait. All participants, please open your camera. Okay. Ella, we need people. Please open your camera, dear participants. Andrew, Tuba, Alp, please open your camera. Yunus, dear Professor Rasim, can you open? Yes. We need people. Okay. Now is okay. I take print screen. 1. Okay. Wait a minute. 1 more. Print screen. Smile, please, again. Okay. 1 more, please. Only 1 more, please. Okay. Yes. Now is good. And coffee break time. Thank you very much.
So the second session will resume at 11 hours, Turkish local time. Okay.
the meeting point of the roads between Europe, Asia and Africa, and a perfect interweave of cultures, Ankara. A culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire, and became the capital of the Republic of Turkey. You can find the opportunity of treading the path of history by visiting the year-round open museums and open-air museums in Ankara, which serve as a bridge between past and present, remaining intact, defying thousands of years. are many historical and modern mosques in Ankara. The roof of Hacı Bayram Mosque was built in such a way as to embrace the wall of the Temple of Augustus, as if to prove the centuries-old coexistence of religions in fraternity. You should never depart from Ankara without seeing the traditional Ankara houses. Ankara is also one of the most important stops on the historical Silk Road. The inns, caravansarais and traditional bazaars of that period provide a safe transport, easy access and a wealth of purchasing opportunities. Historically important Turkish baths and spas are the health and tourism sources of Ankara. Ankara is also a university city boasting 5 big state and 10 private universities. Ankara is also a city of art, life and entertainment. The state opera and ballet performances, the plays staged by the state and private theatres, the concerts by the Presidential Symphony Orchestra, as well as national and international festivals keep its people occupied for a whole year. Seymens, the swashbuckling heroes and traditional dancers from central Anatolia, may show up in all corners of Ankara. All institutions and organizations complying with Atatürk's motto, sound mind, sound body, have spearheaded the construction of many sport halls in Ankara. Ankara also draws attention with its parks and recreation areas. It is located at the heart of many of Turkey's tourism riches. Ankara is the easiest city in terms of transport. Ankara is also easily accessible by air, land and rail from any country in the world. The Turkish cuisine is one of the world's most famous cuisines. The Ankara specialties constitute the select examples of Turkey's culinary marvels. Ankara is the homeland of the Ankara goat, the source of clothes vying with silk for quality, the Ankara rabbit, whose wool is as light as Angora wool, the world-renowned Ankara cat, and the flower of love, also dubbed the flower of the prophet. Its shopkeepers, the carriers of a tradition of 1,000 years ago known as Ahilik, the Guild of Turkish Craftsmen, are sincere and hospitable. They are generous, alms givers, and like guests, with their tables open for everyone. They are, in short, humanists. Ankara, of which Atatürk voluntarily became a fellow townsman, is a monument of peace, with its cultural foundation and a center of tolerance. With its history and natural riches, eating culture and tourism, agriculture and animal husbandry, its politics, sports people, art, and its residents is a leader capital breathing life into Turkey. A culture of paradise of 5,000 years. Ankara, the heart of Turkey.
Sizdeyiz Mehmet Hocam. Merhabalar.
Okay. Okay, I'm now opening the second session of the second day, and sorry for the for Hasan Efoğlu, who was chairing this session, but he has an evaluation meeting in TÜBİTAK, so I'm going to be chairing this session. So we have got 5 speakers. And the first one is plenary speakers, Professor Muhammed Misyus. Muhammed Misyus is a professor of semiconductor materials and devices in Department of Electric and Electronic Engineering at the University of Manchester. So before I leave the microphone to him, I would like to give a few words about him. We always, as a research center in Gazi University, we are taking many opportunities to talk with him for his advice. So we are very pleased about this. And his research activities are centered on the device fabrication of complex multi-layer compound semiconductor films for application in opto, wireless, and magnetic sensing devices. And he has an award actually with Professor McKelly in 2015 from Royal Society Brain Mercury Award for manufacture and of tunnel devices. And he's been giving regularly invited talk. He's been more than 240 publication, and we are very pleased to talk on challenges in vertical cavity surface emitting lasers manufacturing for quantum applications. Professor Misyus, please go for it. I leave the microphone. Thank you very much.
Okay, thank you very much for this nice introduction, and also thank you very much for the committee for inviting me to give this talk. Just a quick word. Let me just start my stopwatch so that I make sure. Let me share my screen. If I can. Let me just see. Sorry, I'm struggling with this. Yes, so share screen, and I found it. And please tell me whether you can see this.
Yes.
Okay, very good.
Exactly.
Can you see one slide, or do you see two slides?
Two slides.
You see two slides. In that case, let me change this to that.
Yes, exactly. This is nice.
Hopefully should work. Oh.
It's gone.
I have no idea. What about now?
Yes, it is. It is. Now it's good.
So let me try and get rid of this. Okay.
So, Professor, you have 50 minutes, please. Yeah.
Yeah. So hopefully I will try and finish this well before 50 minutes. Just one thing though. I'm using my laptop for my presentations, and I'm using the camera from my laptop, but I've got a big screen on my right where I'm doing the presentation. So if you see me looking right, don't worry about it. I'm not trying to avoid the audience. It's just that the, the presentation is on the right for me.
All right, no problem.
So like I said, thank you very much for the invitation. And what I would like to do is to talk about a special class of lasers, which I'm pretty sure a lot of people are maybe not familiar with, but certainly have heard of. And these are the vertical cavity surface emitting lasers. I'm just going to talk a little bit about, when they started, the journey they've made to now, where they're used in mass production. I will talk about their optical properties, electrical properties. I will talk in particular about distributed reflectors, which are of course an integral part and a key feature of VCSELs. I will then talk about VCSELs, how we combine cavity, DBRs, gain region to create a VCSEL. And then I will talk about relatively new applications for VCSELs in quantum technologies. And by quantum technologies, I mean timing, like in atomic clocks, or atomic magnetometers for measuring femto Tesla fields at room temperature without cryogenically cooling them. Then I will talk about new ways of measuring these VCSELs, which are basically on wafers, how we do the mapping, and how we extract the VCSELs we need, and then I will conclude. So VCSELs were first reported about 44 years ago by Kenichi Iga in 1977. So it's been 44 years from absolute start to mass market and mass adoption, for example, in high-speed datacom, gesture recognition in your mobile phones, etc. And now, like I said, new applications in quantum technologies. What is quite interesting about the VCSEL is that when it was first proposed by Iga in 1977, they made a structure where they used mirrors, metallic mirrors. So they demonstrated surface emission, but these devices had enormous threshold voltages, threshold currents, almost 1 amp at cryogenic temperature. But quickly within a year, this was reduced to 36 milliamp, which is now more practical. CW, so works at room temperature using dielectric mirrors. And finally, in 93, the threshold current was dropped to 0.2 milliamp, which now ushers and using transverse gain guiding using oxide confined structure. And this has really led to the explosive growth in the use of VCSELs. So in contrast to its edge-emitting laser or EEL, the VCSEL is more complicated to grow or synthesize and fabricate. But because it's a surface-emitting device, the beauty about it is that you can do on-wafer measurement, and it's so easy to create 2D arrays. And of course, in large volume applications where arrays are used, for example, the VCSEL absolutely dominates as the optical source. So like I said, either in facial recognition in mobiles, for example, or LiDARs, where a lot of work is going on at the moment. So the VCSEL has really now captured not only big markets, but I think we're going to be seeing more and more applications of VCSELs. So the VCSEL itself, like I said, is quite a complicated structure. It's composed of hundreds and hundreds of nanometer scale thin films, which are usually grown using either MOCVD or MBE on up to 6-inch wafers. The key challenge really for this is how to deposit this thin layer within a fraction of a monolayer, and how to accurately engineer the Fabry-Perot wavelength, which dictates the emission wavelength. And this needs to be over multiple wafers. We need the uniformity to be less than 2 or 3 nanometers. In a VCSEL, the nice thing about a VCSEL is that we can make them very, very small. And the way we do them is we put the cavity, which is very small, in between 2 highly reflective mirrors. So these are usually distributed rack reflectors made from compound semiconductors as well. So, for example, in a VCSEL, the cavity length is very small. It's usually about 200 nanometer, maybe less. But it is sandwiched between 2 DBRs, which have incredibly high reflectivities. You're talking about reflectivities which are greater than 96%. The VCSEL is also a the optical mode in the VCSEL are longitudinal, and therefore the emission is through the surface. Because it's longitudinal and because the cavity is so low, the longitudinal modes are very widely spaced. Therefore, the VCSEL is a true single mode device, longitudinal device. But because we also have to confine the refractive index and the current in the transverse direction, we also create transverse mode, which then, and then we end up with a structure which is single mode longitudinal, but can be multi-mode transverse. And the only way to have a truly single mode is to make this oxide aperture very, very small, 2 to 3 micron. Compare that with an edge-emitting laser. An edge-emitting laser emits from the edge, but look at the size of the cavity. It's enormous. It's 300 micron. And we use the semiconductor air as the mirrors. But because the gain region is so huge, then we don't really need high reflectivity mirrors. And the 30% reflectivity of a normally cleaved edge-emitting laser is sufficient. But in terms of volume, please notice that the edge-emitting laser is thousands and thousands of times larger than a VCSEL. So to quickly summarize the advantages of the VCSEL, very short cavity length, it's coherent and high power density light. The beauty about the VCSEL again is that the light is circular when it comes out, as opposed to an elliptical shape for edge-emitting laser, which means you need less optics to correct for the beam. The optical power can vary from less than milliwatt to hundreds of milliwatts to even kilowatts, all within very small die. The wavelength of the VCSEL is set. The emission wavelength of the VCSEL is set by the cavity mode, and this changes very slowly with temperature. So therefore, we have temperature stable wavelength. In an edge-emitting laser, the laser emission is due to quantum word recombination, and basically it is the temperature variation is the semiconductor temperature variation, which is obviously very fast. And like I said, VCSEL operate in single longitudinal mode, unlike edge-emitting lasers. And cost. The really nice thing about VCSELs is that the manufacturing process is very similar to that of LEDs, including the packaging. So therefore, you can do all your measurement testing on wafer. You cannot do that with edge-emitting lasers. With edge-emitting lasers, you make the wafers, you fabricate it, then you need to cut the wafers into bars, then you need to flip the bars, coat anti-reflecting coating on the sides, and then to testing. So testing is very operator intensive, and therefore costs are much higher. So that's what a generic VCSEL structure looks like. So we have a top DBR, usually p-type doped, a bottom NDBR, and then we have a cavity. Now the cavity usually would have, in this particular example, I'm putting 3 quantum wells, but we also oxidize this so that the semiconductor aperture is very small. So when we apply electrical pumping, the current is confined to this very small area. So therefore, we always have very high density current flowing. The cavity length for lasing is lambda over 2 times an arbitrary parameter. So therefore, cavity length in VCSELs tends to be very, very small. like I said, 200, 100 nanometer compared with 300 to a millimeter in energy emitting lasers. But the thing to also keep in mind is that the gain, the optical gain in a VCSEL is simply given by the gain medium, which are the quantum wells, but the quantum wells are very, very thin. So the total thickness of the quantum well is only about 15 to 20 nanometer. Whereas for the edge emitting laser, the gain length can be hundreds and hundreds of micrometer. So what that means is that for a VCSEL, we need, to absolutely confine the light, we need the DBRs to be highly reflective. So we rely on highly reflective DBRs, and if we design it, and these are distributed Bragg reflectors, which means each DBR is made up of a quarter wavelength of high and low refractive index material. And then, of course, we arrange them in periods, many periods. And depending upon where we want our light to emanate, we can make one DBR much more reflective than the other. So, for example, here is, I'm just giving you an example here of how we calculate the power reflectance. So, for example, a typical 850 nanometer datacom laser would have 20 dBrs at the top and something like 35 period dBr at the bottom. So if you calculate the power reflectance, which is basically just the contrast in the refractive index of the quarter wavelength layers, you can see that if we, in the case of aluminum, 12% aluminum algas and 90% aluminum algas, you see we have a nice index contrast. And if we calculate the power reflectance, you can see that with 20 period, we can achieve about 96% reflectivity. With 35 period, we can achieve 99.99. So in this particular example, light would emanate from the top DBR, since the reflectivity is lower than the bottom DBR. Here, I'm just showing you the bandwidth spectrum, wavelength spectrum of what happens as we to the reflectivity as we increase the periods. So for example, this example here is reflectivity when we have 15 periods, then 18 periods. Sorry, 10, 15, 18, 20, and here I've zoomed on this, and you can see that the reflectivity increases very rapidly with the number of dBRs we are putting. And you can see that the bandwidth is about 100 nanometer in here. The bottom DBR, which has 34 repeated period, you can see is far, the reflectivity here is virtually 1. I mean, it's, if you remember the calculations we went through, we ended up with 99.99. So you can see that in this particular case, very high reflectivity, and you can see that the bandwidth is 90 to 100 nanometer. Now, the cavity itself will also have its own reflectivity and absorbance. And in this particular case, when we combine the quantum wells with spacer layer in the cavity, you can see that we have absorption at near 850 nanometer where we want it to be. Now, when we combine cavity, quantum wells, and DBRs, this is what we end up with, which is the full, which is the full VCSEL cavity. So you can see that reflectivity is pretty high, apart from this dip here near 850, where we want the laser light to emanate from the VCSEL. But if you look at this, you can see that in the entire bandwidth, there is only one peak, and that's what makes the VCSEL single mode longitudinal devices. Now, the attraction of VCSELs, of course, is that they are also electrically pumped, and you don't need much current, you know. If you recall at the beginning, I said, you know, with about 0.2 milliamp, we can get a VCSEL to laze. So here, what I'm showing ways of creating the DBR. You can create the DBR here either as an abrupt structure in blue or as a graded structure. Here I'm showing the X composition of the various layers that go into the VCSEL. This here is the entire VCSEL. So you can see we have the bottom DBR, we have the top DBR, and we have the cavity with the quantum wells. So if you look at the top DBR, like I said, we can either have abrupt interfaces or graded interfaces, and same in the bottom DBR and in the same in the cavity. Now, actually, you do not want abrupt interfaces, because abrupt interfaces in high aluminum content algas would give rise to blocking transport, which would make your devices resistive. So what we do, therefore, we actually design graded interfaces. So we make the DBR more complicated by creating the grading, but at the same time, we remove any obstacle to the transport of carriers. So this is the full VCSEL band diagram, graded and ungraded. And now let me just go and zoom on this. So you can see that in the top, so in the top DBR, you can see that the band discontinuity, if we have an abrupt interface, the band discontinuity is about 0.2 eV. When we introduce the grading, we reduce it to less than 0.1 eV. And that makes enormous difference in the resistance of the VCSELs, and therefore its efficiency, energy efficiency. And here I'm showing the band diagram of the entire structure. So I have P at the top and at the bottom, cavity in the middle with the quantum wells. And blue is abrupt, red is graded. And you can see how now we are absolutely reducing all these blocking layers in the structure. And of course, we're also reducing the electric field inside the cavity, which is a good thing for reliability as well. Here, what I'm showing refractive index contrast across the entire structure. So this is top DBR, low and high refractive index, top and bottom. And in the middle is the cavity. So the cavity, here are my quantum wells. But here what I'm showing, I'm also showing the standing wave or the electric field intensity. And you can see that we design it in such a way as the highest electric field is where our gain is maximum. In other words, around the quantum lines. Okay, so let me just go back here. So what I was talking about is really VCSELs as they are used nowadays in mass market applications, be it in high-speed datacom optical links, or in facial recognitions, or in LiDAR. But more and more, there is now new applications coming on stream where VCSEL can play a big role. So let me just talk a little bit about the quantum applications that can and are benefiting from the use of VCSELs, but also what challenges they introduce. So the VCSEL, like I said, by its nature, is a tiny, tiny volume resonator. And they're extremely efficient, you know? You don't need much current to get them going. So the characteristics of the VCSEL really makes them ideal as emitters in a new generation of atomic clocks. So for example, if you look at the hyperfine structure of rubidium or cesium atom, you can fine tune your laser so that you synchronize with the D1 structure in cesium at 894.6 nanometer, or D2 transition at 852 in cesium, or the D1795 nanometer. Actually, it should be 795.00 nanometer rubidium transition. And these transitions are extremely accurate. So 851 will not work, 894 will not work. So unlike telecom or facial recognitions where you can afford for the VCSEL emission wavelength to change by a few nanometer, in here you cannot. But the promise in atomic clocks, for example, is that you would replace big, bulky lamps with a tiny semiconductor laser. And so, for example, in atomic clocks, the idea is you would bypass GPS altogether. So in the long term, you could imagine people having atomic clocks in their cars for navigation. Or in atomic magnetometers, you will have very high sensitivity magnetometers working at room temperature and able to measure magnetic fields due to heartbeats or brain activities, which are all now done in gigantic facilities and at liquid helium. However, what are the challenges? The challenges, of course, for this application is that the VCSEL must be single mode, so multi-mode will not work. And you have to have absolutely very precise wavelength. Now, what does that mean? Well, it means that in a VCSEL, to have this prescribed accuracy in wavelength emission and to achieve high yields in a 4-inch wafer, for example, would mean epitaxial growth accuracies of plus or minus 0.1 nanometer and uniformity across a 4-inch wafer of plus or minus 0.1 nanometer. These are impossible to achieve at the moment, and they are 10 to 20 times higher than what is typically available in MOCVD or MBE. Also, if you remember, the most efficient VCSELs at the moment are oxide aperture VCSELs, 2 to 3 micrometer to give you single mode, but you need to control that to about 0.1 micrometer, again, which is again very demanding and almost impossible to achieve. Thus, it is clear that we will have very low yields on, when we are doing manufacture on 4-inch wafer. But I will talk about how we get around this problem. So again, to talk a bit more about the advantages that this VCSEL give you, like I said, they're small and they're extremely efficient. So, and for long-term operation, we operate this VCSEL with maybe 1 or 2 milliamp, and we make sure DC power consumption is never more than a couple of milliwatt. Also, because we're looking at super fine structure of the cesium and rubidium atom, we need the emission wavelength to be incredibly narrow, much less than 100 megahertz. Typically, we want 20 or 30 megahertz. And again, when we are driving the VCSEL, the current source that is driving it must also be incredibly stable. And the noise, of course, must be near the short noise level ground at high frequency, in the 300 to 300 kilohertz detection frequencies, which are usually frequencies employed for atomic magnetometers and the atomic clocks. Now, let's now move to actual devices. So here is an image of a VCSEL. The size here is about 250 micron by 250 micron. So you can see they're very small. And here is one VCSEL that is operating, and you can already see that the emission, the beam shape is circular. I hope this will work now. Here, what I'm going to show you is this VCSEL being driven by a current source here. So this is current, this is the corresponding voltage, and I would like you to keep an eye on both the current and the emission here to see that the threshold current is actually quite low. It's about 0.2 milliamp. So let me start the video and see whether you can see it. Oh, maybe. Ah. I don't know why it doesn't want to play. This is so annoying. I'm sorry about this. For some reason, it doesn't want to. Let me just. Sorry, it doesn't want to play, which is a pity because. Let me just go back to it. Because. Sorry about that. I just cannot. For some reason, it just doesn't want to play.
Okay, you can start it, yeah.
So here are examples of single mode emission from these VCSELs. You can see we have relatively high power, 0.5 milliwatt, but we can go to 1-2 milliwatts. The side suppression mode from here to any other mode here is greater than 30 dB, which makes them ideal and for these quantum applications. The other thing I wanted to talk about is that, of course, you take the dye, you put it in a TO can, but as you can see here, you have a bit of tuning with the current. So, for example, this particular VCSEL is emitting at 887.546. at 1 milliamp. But you can see that by changing the current all the way to 6 milliamp, I can shift the wavelength by about 6 nanometer. So you have a bit of tuning. Obviously, the drawback here is that you would be dissipating a lot of power here. So in atomic applications, what tends to do is that your cesium or rubidium gas would be in a small cell and you would heat the VCSEL. So you would probably only use 1 or 2 milliamp and then just heat up the VCSEL temperature to shift it to wherever you want to go, so that you still keep a low power dissipation across the VCSEL for long-term reliability. Now, let me show you data on full wafer. A full wafer, here is an example of a full wafer. You can see that in MOCVD, for example, there is always a range of wavelength across the wafer. You never, if you specify 850, in the design of the VCSEL, like we showed before, you always end up with a range of VCSELs. True, some of them dominate. For example, here, the dominant wavelengths are from 846 to about 849. 6, 7, 8, 6, 7, 8, 9. Nevertheless, that's quite a wide range. So to pick up the so this is how they change, but across the wafers, how do they actually move? Okay. Oh yeah, another thing. Sorry. Across the wafer itself, you're going to have die or devices which are single mode, and here I hope you can see the green dots. This is how they are distributed across the wafer. Or you can have multi-mode, and this is how they are distributed. So the only way really to characterize the VCSELs is basically to measure every single die on the wafer. And remember, you can have up to 100,000 die on the wafer. But we can do very fast measurement of wavelength, power, and modes, and we can do a whole wafer, in a matter of maybe 15, 16 hours. Now, if you remember, I talked about the wafer having a range of wavelengths across it, but unfortunately, again, these wavelengths are distributed in a funny way in the wafer, simply to reflect the growth dynamics in MOCVD, for example, because these are MOCVD wafers. So you can see that wavelength between 843 and 844 tend to occur near the periphery of the wafers. 844 to 845, can you see there now we're getting in more inside. 847 to 848 is roughly in the middle. 40, sorry, that should be 46 to 47 here. But you can see these are the dominant wavelengths we're talking about here, Then 50 and 50 to 51 are small. Basically, this is a map of the wavelength variation. But as you can see, it's how these wavelengths are on the wafer is not obvious. So this is why you need to measure every single die, really, then to pick up the VCSELs that are fit for purpose for the quantum applications. And here is an example of power distribution. Again, the power distribution goes from very low power all the way to 2 milliamp, but this is for a 2 milliamp drive current, okay? So again, you can see how efficient these devices are. But you've got a nice Gaussian shape here. like I said, in mass market application, this is absolutely fine. In quantum applications where you might need a certain power, then the only way of doing it really is to, like I said, measure every single device and then select the device by wavelength, by emission mode, and by power. Now, the VCSEL is a surface emitting device, and unlike an edge emitting laser, like I said, the beam is usually nicely circular. Even though the oxide aperture, when you oxidize the VCSEL, the oxide aperture itself is not circular. You can see the weird shapes that you get during thermal oxidations. But in general, you would end up with this type of beam shape. And if you measure the divergence is usually, you know, anything from, I would say, 10 to maybe 15, 16 degrees. So they're, you know, fairly collimated. However, sometimes, oh, sorry. This is the type of beam shape you would have from a fully packaged die on a TO can. But of course, we can also look at the beam shape on wafer. Now, why would we want to do that? Well, because sometimes, and depending upon really the shape of the oxide and the manufacturing process itself, sometimes you end up with elongated rather than circular beam shape. So in this particular case, you've got about 15-degree divergence, but the beam is really not circular. But this you can then select at wafer level. So at the wafer level, you can select which VCSEL is suitable for your atomic clock or for your atomic magnetometer in terms of single mode emission, in terms of power, in terms of the right wavelength, and in terms of the beam shape, and also another parameter I'm not talking about here, which is polarization. And finally, what we can also do with these structures is that we can do full physical modeling. So knowing the thicknesses, the composition of all the layers here, of the DBRs, the cavity, the quantum well, the oxide aperture, we can actually do physical simulation to predict how this VCSEL will behave. And you can see here is an example of a VCSEL which has a MESA size of 32 micrometer, and you can see that measured and simulated curve are, I mean, the fit is very, very good indeed. You know, so using this, you can make predictions on what your device look like, what you know, what type of or size of power it emits, etc. So I think I will finish here, and basically the takeaway home messages. What are the messages really I wanted to drive home here is that, first of all, VCSEL have now come of age. 44 years since they were first proposed, they are now absolutely dominant in a large range of mass market electronics applications. Sensing, high-speed datacom, laser heating, LiDAR, etc., etc. In quantum applications now, VCSELs are the preferred optical sources for atomic clocks and atomic magnetometers due to their high modulation bandwidth, because you can do direct modulation, low power consumption, among many, many other parameters, okay, which is long life, reliability, etc. But in quantum applications, the VCSEL has to be extremely, the emission wavelength has to be extremely accurate to match the D1 transition wavelength of 795 nanometer in rubidium or 894.6 nanometer for cesium. So this, of course, places enormous manufacturing constraint during growth fabrication. The other problem is the cell, which has the gas, can also, the temperature can vary from room temperature to 70 degrees C, which of course also shifts the emission wavelengths. So there are a lot of constraints we've got to get right. However, because now we are able to test every single VCSEL on a full inch wafer, where we can have up to 100,000 die, we can select only the devices that are fit for purpose in terms of wavelength, mode, power, stability, etc. In fact, I would argue that it is a good thing to have a wafer which is not highly uniform, because then we can choose, we have far more freedom in choosing which devices will fit the atomic clock or atomic magnetometer. Whereas if we were able to have super high uniformity on the wafer, if we just miss it by a little bit, the whole wafer could be gone and we could end up with a zero yield. I think I'm coming to about 45 minutes, and I think I will stop here, say thank you very much, and I will be happy to take any questions.
Thank you very much, Professor Monsieur. We are very happy to listen your nice talk. And thanks a lot. And let me see if there is a question. I'm waiting if there's questions coming up here. Maybe in YouTube, can you check YouTube, please? Yashar, Nihan, if there is no question.
Let me stop sharing.
Okay.
Yeah.
Any question?
There are some questions.
I cannot see the question here.
I cannot see any question.
Okay, I think Professor Süleyman Özçelik would like to give some comment.
Sure.
Dear Messieurs, thank you very much. Congratulations for your warm talk. And thank you for your valuable contribution to our event.
No problem at all. It's a pleasure. I wish we could be face to face.
I hope we will be face to face in near future.
Absolutely. Usually, every summer we go to Izmir for a week holiday, but I think we missed it last year and we will probably miss it this year as well.
Hopefully next year you will get it.
Yes.
Hopefully, yes.
Have a nice days. Bye.
Okay, bye.
There is one question, I think it's come.
Sure, go ahead. Sure.
What we think hologram whistles?
Well, sorry, I don't understand the question.
Is this question for you? What do we think hologram we see?
Okay, does the question mean what do we think about the use of VCSELs to generate holograms? Yes, absolutely. Because like I said, the beauty with VCSELs is that they are small, they are very power efficient, and in a lot of applications, they are replacing big, bulky lasers, even in heating. So yes, VCSEL definitely will be used in holography, and who knows, very soon we might have 3D holographic TVs, that use VCSEL.
Excellent. Okay, very nice. Okay. Also, the question came from Cenk Ceylan. He also gave his thanks. Yeah, thanks. Okay. Thank you very much once again, and
no problem, my pleasure.
Thank you very much for your contribution to our conference. Hope to see you in Izmir, in Ankara, in Antalya, wherever
Absolutely,
as
absolutely.
talked by
Okay, thank you.
Professor Süleyman Özçelik. Okay, then I'll see you later, and I'll move to next talk. Yeah.
Okay.
Thank you very much.
Okay, bye-bye.
All right. We will now invite a speaker, Dr. Beatriz Olmos Sanchez from Institute for Theoretical Physics, University of Tübingen, Germany. And now she's going to talk on collective coupling of an array of atoms near a nanofiber. Please, I leave the microphone to you. Go for it. Thank you very much.
Hello, thank you very much. Just let me share my screen as usual. We are all now used to this.
Okay, good.
Hopefully you can all see it.
Yeah, I can
Good.
see. Means everybody can see. Okay, you
Perfect.
will have 30 minutes. Yeah, okay, bye.
Yeah. Okay, so yeah, thank you very much. Oh, sorry. Thank you very much, of course, first to the organizers for giving me the opportunity of presenting this work to you that we have been doing. Yeah, what I will be talking about will be mostly what we have been doing in my group in Tübingen during the last year. It is a bit of a change of gears because it's a theoretical, program here. So yeah, but I will hope to keep you entertained for the next 30 minutes. So I will be talking about, I chose a rather general, rather general title on purpose, collective coupling of an array of atoms near a nanofiber. And okay, the things that I will be telling you about are in these two published papers last year, and this one that's currently under review. Good, so as I say, I'm a theoretician, so if I talk about guided modes, and I will talk to you in a second, or nano atoms coupled to a nanofiber, what I see in my head somehow is this. So this is my nanofiber here, and I have here some atoms. In particular, I will be talking about atoms in an array, but that will come later. I just want to tell you a bit, okay, this is the system that I will be talking about. When I look at atoms, I will be looking at two-level systems. So an atom with a ground state and an excited state. And I will be driving them with a laser that I will consider here to have some Rabi frequency omega and some detuning with respect to the transition of these two-level systems that is given by this detuning delta. Good. So again, in general, what do I consider? Well, I consider that these atoms are close to a nanofiber. In general, it could be some sort of waveguide. Okay. So why do I choose this? The reason is that there are these guided modes here in play. So what does that mean? That, okay, when I have an atom, for example, excited to in the excited state, that atom will inevitably decay eventually after some time to the ground state. But now in doing so, it will emit a photon, and that photon can be either emitted into the unguided modes of the environment. That can always happen. You have a single atom away from this nanofiber, it will always emit to these unguided modes. Or, but in this case, because you have the nanofiber or the waveguide or whatever structure around, it can also emit the photon into these guided modes. And in particular, what is interesting about these guided modes is that once you have the light emitted into these modes, you have the photons, so to say, where you want them, because they will just travel to the near along the fiber. And then you can, for example, think of putting here a detector, and you can actually analyze the light. You can check when the photons arrive. You can do some homodyne detection, whatever you want. Okay, so that is basically the idea. And moreover, what is interesting about the systems is that the chirality is broken here. So the chiral symmetry of the emission can be broken. What does that mean? So when I talk about chiral emission, what I mean is that there can be a higher probability of the photon being emitted into one direction than into the other. So this is what I see in my head as a theorist, but I see there are a lot of experimentalists here in the audience. So, okay, what is in practice, what is being done? This is not science fiction, and this is also why we became interested in this kind of systems. For example, there are these, you see here, there are people actually putting atoms near these nanofibers. You can see that these nanofibers are here, these tapered optical fibers, and then you kind of stretch them a lot, and then you have these atoms very close nearby to this nanofiber. typically a few hundred nanometers away from these nanofibers. But as I said, this is not, okay, the things that I talk about here are referring to the nanofiber, but most of the things that I say here can be actually exported into other kind of nano waveguide structures. For example, here I show you some photonic crystals, some waveguides here, and then also some photonic crystals in 1 dimension and 2 dimensions. The ideas are basically the same, that you can have these atoms or these qubits or whatever you want, and then the idea is that the photons are emitted hopefully into this guided mode. So this is why, okay, this is basically what my summary slide, if you want. But because I don't know how much people know about this, I tell you what happens first with a single atom. So you have a single atom, and as I said before, we consider this a 2-level system. We have it next to a nanofiber. This nanofiber is obviously very long. And as I said before, you can have your total emission rate. I'm going to be calling this large, this capital gamma, is composed out of 3 contributions. One is this gamma R and gamma L, which is the emission rate into the guided modes, to the right and to the left. And then I have this gamma U, which is the emission rate into the unguided modes. Obviously, what I would like, so this is this h is the distance, and this d the dipole moment of the transition that we are of the particular 2-level system. So now, what I would like, obviously, in the ideal situation, is that most of my photons are being emitted not into the unguided modes, but actually into the guided ones. Because those, as I say, I can put a detector on one side, on the other, and I can, so to say, play with that light. So the problem here is that if you have a single atom close to a nanofiber, there's only so much you can do, so to say. So you can play with the polarization, you can play of how close you put the atom to the nanofiber, that is also limited up to a point. And what you can see is basically, and you can also play with the radius of the nanofiber, but eventually what I call here the beta factor, and the beta factor is okay, I define it here as gamma R plus gamma L divided by the total emission rate, but it's basically telling me what is the probability that if I emit a photon, it's emitted into a guided mode, okay? So I want that percentage, so that number between 0 and 1 to be close to 1. And what one sees is that in reality, if you take regular parameters that are used in experiments, what you find is that the maximum beta factor usually goes, if you're lucky, up to a 25%. So another thing that you want also is you want the directionality of this emission to be something that you can, that you can manipulate. Okay, so you have, for example, the thing that you can play with here is not only the distance of the atom with respect to the nanofiber, but also the direction of this dipole moment, the polarization of the light that it's So ideally, if you had some sort of elliptically polarized light, you could be able to make the light completely chiral so that it's only emitted into one direction. But in practical terms, what you usually have is either linearly polarized, circularly polarized light. And what you can see is that typically this directionality can be controlled, but only up to a point. And ideally, what I want to find is a situation in which this directionality parameter that I'm defining here, which is nothing but something that is 1 when all the light is emitted into one direction, and -1 when the light is emitted into the other direction, that is either 1 or -1, and that I can control it up to a point. So we see that this is kind of limited for one atom, but we can do better. And the way that we can do better is actually exploiting collective interactions that appear between atoms. So in this case, many is better. Many atoms is much better than having just a single atom. And now again, because I'm a theorist, I have to take this system and I have to simulate it. But in order to do that, the good thing about this is that there is one equation that solves all my problems. So I will have to show you some equations here, but as I say, it will be just the one basically. So what is this equation that rules them all basically? So what do I say? What do I mean by all situations? So here I kind of take a step back and I say, okay, I have atoms, they are coupled to the environment, and okay, most of you, I'm sure that you are familiar with this, but still I thought for completeness, I say this. Atoms are coupled to the environment, let's say the radiation field in some way. You could have nanostructures there, you could have whatever. Okay, the idea is that you have some sort of quantum optic system where you have atoms and you have some sort of light field around it. This radiation field actually can be traced out because I'm only interested in particular in what happens to the atoms, so to the internal degrees of freedom of the atoms, and I'm not really interested in knowing what happens to the full environment. And then out of that, I can obtain this equation, which is nothing but a Limrad equation. And this is the equation that is going to rule all of my systems. Now, of course, the devil is in the details, and now you will have to obtain precisely what this H Hamiltonian here, this Hamiltonian here, and this D are. And also this, although this happens to be valid for all the situations that I'm going to be considering here, and in most of the quantum optic systems, it's not always true, so one has to be a bit careful. But this equation will be valid here under the dipole approximation, under the Born-Markov approximation, and also, we have to do a rotating wave approximation. So, but you have this equation. Now, what does this equation tell me? So this rho is nothing but the density matrix that describes all of the degrees of freedom of the atoms. Okay, so this is just the atoms, the ground state and excited states basically talking to each other. Now, this Hamiltonian is basically a coherent effect that arises again out of the atoms being coupled to the environment. And in particular, what appears here is this H that looks like that. So this sigma, the sigma L and sigma J are nothing but ladder operators. So basically what this describes, even though it's written here, is a flip-flop or dipole-dipole interaction. You can see that, okay, when this atom is up here, it goes down, emits a virtual photon. Okay, so this is kind of a funny trick, but okay, this emits a virtual photon and it's not emitted into the environment, but it's actually caught by another atom. So what you have in practice is that you look at the atoms and the atoms are actually taking their excitations and they are kind of, sharing them among the system. And this is something that happens just because the atoms are coupled to the environment. That's it. And then the second term, this over here, this D of rho, determines the collective decay. So this would be decay if the atoms are very far away, for example, from each other, and there is no nanofiber whatsoever. This would just tell me the atoms are being, the photons are being emitted from each atom independently with a single atom decay rate gamma. In practice here, what happens is that one has collective decay. What do I mean by this collective decay? So here the important thing is actually this matrix here. Now the diagonalization of that matrix tells me the different decay channels and the decay rates. Now, if I have two atoms, let's say, the same as before, and I look at this matrix, what I will have, it's a 2x2 matrix. And this 2x2 matrix has in the diagonals the single atom decay rates. So this is the one of the first atom and the one of the second atom. But then I also have off diagonals. And in order to obtain the natural emission modes of this system, I need to diagonalize this matrix. Now, I have some off diagonal elements in general. So 1, 2, and then this is also 1, 2 that appear here. Now, what can happen? Well, I diagonalize this matrix, and then what I obtain is that I have two collective emission modes. One of them has emission rate gamma plus gamma 1, 2, and the other one has the same, but with a minus sign. Now, when the atoms are very far away from each other, and when the atoms can be considered as independent emitters, what happens is that this gamma 1, 2 is just equal to 0. Hence, each one of the emitters are the natural emission modes, so to say, of your system, and they have each emission rate which is equal to gamma. But when the atoms are very close together, actually, or when they are somehow related by something, like the nanofiber will be in a second, then what happens is that this gamma 1, 2 can be up to gamma. And let's say in that particular case, let's say that this gamma 1, 2 is equal to gamma as well, then what you get is that when that happens, this is actually 2 gamma, and this is actually 0. And this is what in the literature, so that's not a pi, sorry, that's a gamma. And this is what in the literature is usually known as superradiant states and subradiant states. So you have states that if you manage to excite them, they emit very fast, much faster than a single atom would do. And some states in your system that are subradiant, which means that they decay very, very slowly. They can actually be very, very long-lived. So, as I say, this is a general thing that happens for atoms coupled to the common environment. And the specifics of how these rates and how these dipole-dipole interactions occur will depend strongly on the atomic dipole moments. So the polarization of your system, for example, is not the same. You can think of it as basically as dipole antennas, small dipole antennas. You have 2 atoms, two of them like that. They don't have the same interactions, for example, as if they were like this. So vertically, so that's one thing. Then it depends very strongly on the radiation field structure. So it's not the same to have them in free space or if you have them in waveguide QUD, which is what I will be touching upon, but also in surfaces. We have also done some work here. And it will also depend strongly on the geometry of the atoms. It's not the same to have a disordered gas or an ordered array in 1D and 2D, etc. So you can touch, so to say, a lot of knobs in order to obtain different situations for these dipole-dipole interactions and for this collective decay. So this is kind of the roundabout slide. Now I come back to the system that I was interested with. I have my collective light matter coupling on a waveguide. So what I am going to consider is an array of atoms that are coupled to some waveguide or a nanofiber. I'm also going to consider that this is driven by some laser whose momentum is shown at an angle theta with respect to the array. Okay, so this will become important later. And then I also consider that I have a detector, and I'm going to put this detector on one side or on 2 sides. I will see in a second. So now the equation that rules all of this situation is the following. So what I have here, for example, so it has several parts. 2 of them you have seen already. So this one and this one I have shown you already. This extra part, this extra laser, this extra Hamiltonian just describes the laser. So this is just a laser field. Then I will also have this other part, which again, as I said just before, it describes these dipole-dipole interactions, these exchange interactions among the photon, among the atoms. And then I have this collective dissipation. The good thing about this now is that if I have this nanofiber, actually I can take now both, actually, not only this, but I can also take these coefficient matrices here. And actually I can break them down into the contributions of the guided modes, so the right and the left, you can see that here, and the unguided modes. So this is nice because then I can really separate somehow all the contributions to these dipole-dipole interactions that come from the coupling of the atoms to these specific guided modes and the ones that are coming from the rest of the environment, the unguided ones. And why do I want to do this? Well, I want to do this because they are really, really different, these kind of these contributions. The unguided ones describe decays and describe interactions that decay with the distance. They are still long range because they can be up to 1/r actually if they are far away, but typically it's like 1/r cubed. So depending on that distance, you get still some decay of these modes. So that means that obviously, as we know, that if you are in the radiation field and you have in free space 2 atoms, eventually you can put them apart enough so that these unguided modes don't, the couplings, so to say, don't play a role anymore. But now the guided ones, on the other hand, they are all-to-all. They do not depend, they are really translationally symmetric. They do not depend on how far the atoms are really from each other. They will mostly depend on the relative phase between 2 atoms with respect to this nanofiber. I will be coming back to that in a second. But the important thing is because the light is mediated here through the nanofiber, okay? So it goes, yeah, it really gets exchanged between two atoms independently of the distance between the two atoms. Good. So this brings me to showing you now. I showed you before, what I told you before is, okay, if I have now two atoms, these are the collective decay rates, but I can do that also for a larger size of system. And here, for example, I plotted that for 15 atoms. And now what you have here is the distance, the nearest neighbor distance between two atoms divided by lambda. And yeah, this is what you obtain. You obtain that there are many decay rates that are super radiant, and then you have a few that are subradiant. You are dividing by the single atom decay rate here. But most importantly, what you find is that there is this one over here that does not depend on the distance. And actually, this one is a superradiant mode that it's a guided mode. And actually, this one over here has a phase gradient that depends on the distance between the atoms. And what was our idea then? Let's excite that superradiant state in order to collectively enhance the beta factor and the chirality as we wanted to do. And how do we do this? Well, we drive the chain with a laser field that exactly imprints the phase pattern that gives rise to this superradiant state. So what we are doing is basically taking the laser and exciting exactly that superradiant state. That superradiant state will mean that if it is excited, most of the photons, because it is a guided mode, will be emitting into the guided modes of the nanofiber. And on top of that, we found that there is a matching condition that one can obtain analytically, and this superradiant phase matching condition or geometric Bragg condition is given by this. You can find this angle of the laser that you have to obtain in order to get that, that superradiant state right. And this K0 is nothing but the K of the laser, the momentum of the laser. Kf is the modified momentum due to the traveling inside of the nanofiber because it has a different index. And m is just an integer. So if you drive that, you obtain this superradiant state. And this is what we did. And now what we do is we put a detector and we calculate numerically what is the amount of photons that comes into this. And then we will compare it with the total amount of photons emitted, and we will see that indeed we get a collective enhancement of the emission into the guided modes by exciting this at this angle. And this is what I'm going to show you here. So this is the angle theta, and this is the A over lambda. So for different values of the distance between the atoms. And as you can see here, this is the collective beta factor. So how much is emitted into the nanofiber compared to the total emission. And as you can see here, usually these blue lines is what you obtain for a single atom, something like 50%, something like that. But there are these extremely sharp lines, which give you, up to 80% enhancement. And this is for 15 atoms. And these lines actually correspond exactly with this geometric Bragg condition. So this is exactly what this line that I plotted here looks like. So indeed, this gives you an enhancement of the guided emission. You can actually increase this by increasing the number of atoms, and this is what we do here. We show that indeed, the more atoms you have, the better. Obviously, you have to be careful that you hit that mode, basically, but this is how it works. And also, as an extra, what happens is that you can actually increase also the chirality and get it very, very close to 1. So this directionality that I was telling you about before, so that you can also increase. What does that mean? That out of this scheme, what you get is that not only you increase the amount of photons that are being emitted, but you actually emit most of them into one direction only. Independently of what one atom alone could do, you are able to emit all of the photons into one of the directions. And the next thing we also saw is that the spectrum of the light is actually not, changes very, very sharply as you have, as you go into these particular peaks. So you can see that if you go to any random place here, you have just that your spectrum is just a Lorentzian. This is the total amount of photons emitted. This is the amount of emitted photons into the guided modes. And here, what you can see is that, okay, this is a function of the detuning, and you can see that the spectrum has actually 2 peaks. And what we did in the next part of the work is to analyze, okay, what happens here exactly? And yeah, why does these 2 peaks appear? And what we found is that the spectrum actually changes dramatically around the geometric Bragg angle. So the angle of the emission minus this geometric Bragg angle. And then what we found is that if you look at this amount of photons emitted into the right mode, so they're into the guided mode, what we find is that there are these 2 huge peaks here. And this is what happens if you are very far away from that Bragg condition. So this is just a Lorentzian, so to say. This is what we observed for the geometric Bragg angle. But then we also found something more interesting, is that if you go away from that, you can actually do better. You can emit even, look at this is 500 and this is 120. So this is, you can emit many, many more photons into the guided modes by modifying this geometric Bragg angle. In order to understand better what happens here, we just used a simplified model. And I'm not going to go too much into details because I feel I am almost running over time. But basically, yeah, we took something very simple. Just we considered just that you have simple emitters, and then we consider the different of the light paths that cross each emitter. But most importantly, what we found is that this difference in the angle comes from the fact that the light, every time the light is emitted into the nanofiber and it passes another atom, it experiences an extra dispersion or absorption due to the fact that there is another atom nearby. And if you consider that, what you obtain out of that is a closed relation for this emission into the right mode. And okay, we found a number of different possibilities, but the most important result, and this is what I want you to see, first of all, is that we were able to find an analytical expression for this modified Bragg angle, at which you have an extra, so to say, emission into the guided modes, and also an extra emission altogether, which is, as you can see here, matching exactly the numerical values. And also what we found is that at that particular point, this is really, I don't know, that's what I find extremely exciting about this, is that the amount of photons that are emitted into the guided modes grows proportionally to n, to the atoms in your chain. So instead of going into a saturation value, which is what happens with any other angle, at that particular angle, what you get is that the amount of light that is emitted into the guided modes grows proportional with n. And then we did some checks on the robustness with respect to the directionality of the emission of the one single atom, and also some robustness when you remove some atoms. This is a collaboration with experimentalists, and they tell us, okay, usually what you have is a chain, yes, but you have to take into account that you don't have always perfect filling. So we did that, and we realized that, okay, our scheme is extremely robust against also these kind of experimental imperfection sources. And with this, I leave you with my conclusions here, and I'm happy to take any questions.
Okay, thank you very much, Dr. Sanchez. And it was very nice to see you here, and hope to see you in next future in İzmir, in Ankara, in Istanbul, in Antalya. And let me see if there is a question. There is no question at the chat section, and we have 1 minute left. Actually, if there's a question, please go for it, dear audience. Is there any question in YouTube? Okay then. Thank you very much once again, and your contribution to our conference, and hope to see you near future. Thank you. And we move next. We move to next talk. Okay. Our next talk is gonna be again invited speaker, Professor Alexander Vladimirovich Volyar, and he's the head of the General Physics Department. Before I leave the microphone to him, I want to give a few words about him. Thank you very much for joining us and your contribution to our conference. And he's been working in the physics department in the Crimean Federal University, named after V.I. Vamadesky in Ukraine. And he's been working and he's publishing more than 170 scientific articles in the sphere of nonlinear optics, fiber and singular optics. Now he's going to talk on geometry of structure, spiral beams, the structural stability and energy flows. Please, I leave the microphone to you, Professor. Thank you very much. Please go for it.
Good day, Ankara. Good day, participants. But first of all, I'd like to thank the organizers for inviting me for such a remarkable conference and giving me opportunity to talk about our modest achievements. I'm from Crimea. From Crimea Federal University, or more exactly, from Institute of Physics and Technology. And my report is geometry of structural spiral beams, structural stability, and energy flows. Recently, looking through last year's issue Optics and Photonics News, I read a large article by Andrew Forbes on dynamics of complex composition of water beams. It's not that the article very surprised me, but after talently united a great number of physicists from different parts of our planet. I have here sounding ideas of Michael Berry, Yoji Chen, Mark Dennis, Victor Kotlyar, Victor Sofer, and many others. And I also tried a small contribution in this new area of physical optics. Thus, we will talk about structural stability of water beams compositions, namely of shaping, figured lines, letters, and even words. My co-authors from our university, Michael Britko, Yana Akimova, postgraduate student of mine, and Associate Professor Yuri Egorov. And from Russian Academy of Science, Professor Evgeny Abramочkin and Research Officer Evgenia Razueva. And what does structural stability means? A very strong mathematical definition. We can say that dynamic system remains structurally stable until external perturbations lead to appearance or disappearance of new critical points inside mapping the dynamic system. In terms of wave optics, structural stability is often associated with light acoustics. A simple and useful example of such acoustic is elliptic umbilic. According to Mike Berry, the elliptic umbilic can be obtained by directing Gaussian laser beam onto a water drop placed inside a triangular diaphragm. Right after the water drop, we observe a complex patterns of diffractive spots. These patterns change along the beam axis so that the complex diffraction pattern encompassed by bright light line. It is the light caustic. Light caustic outlines the surface in the space along the beam axis that came to be called stability surface. This is something like beam passport, digital beam passport. If we parameter the complex diffractive pattern, we see a regular structure of optical vortices with different signs of their topological charges. The vortices form something like rhobohedrical crystallographic vortex structure. When we cross the caustic boundary, the vortices disappear. In this sense, a complex vortex beam remains structurally stable until external perturbations lead to creation or annihilation of optical vortices inside the caustic. In other words, as long as the shape of the stability surface remains topologically equivalent, the vortex beam will be structurally stable. Can we redistribute the energy flux inside the structural beams in such a way that the vortex diffraction pattern disappear while the caustic itself remains structurally stable? Frankly speaking, such structurally stable beams have been revealed as far as in the end of the last century by Abramashkin and Volosnikov from Russian Academy of Science, and called them spiral vortex beams. However, nobody studied the caustic properties as yet. Thus, we decided to find out what part the wave caustic play in shaping and stabilizing the spiral vortex beams. Some mathematics. Drawing continuous closed curve on the complex plane, we at once obtain a generatrix of the spiral beams. Now, substituting the generatrix in the parametric form, we obtain substituting integral quotient presented here. Then we obtain complex amplitude of the spiral beam, that is modulus of amplitude and phase distribution. We have studied a great number of spiral beams, in particular such as spirals, stars, crosses, snowflakes, polygons, and even words. In particular here is a holographic rating of this word. As well known, the caustic is formed by straight rays emitted by stationary points of the wave front, in such a way that the rays outline some bright line that we call the caustic, the light caustic. In this example, this is a geometrical caustics. We have obtained general equations for stability surface. In particular, here is a stability surface for triangular beam. At the experiment, we observe intensity distribution in different parts of the beam length and plotted only a maximal value of this distribution. As a result, we obtain two types of stability surface for triangular and tetragon beams. Sorry. You can see here theoretical stability surface for triangular, tetragon, pentagon, and star beams. And what is interesting, the generatrices of these beams as straight light rays. Projections of the straight rays onto the observation plane from the caustic. Here you can see the different shapes of the caustic for triangular, tetragon, pentagon, star beams. But the shape of this caustic changes when we move along the beam axis. But what about similarity with an elliptic umbilic from whence we began our talk? As I said above, elliptic umbilic has three acute angles where derivatives of the generator function are undefined. As a result, we cannot observe, cannot plot the caustic line for such beams. But in order to avoid this difficult, we try avoiding the dark lens on the caustic line. As a result, we have chosen the generator function in the form of the golden triangle with the control parameter, the golden ratio. You can see here theoretical shape of our triangle. The area triangle is very large, so that the caustic line is very thin. As a result, the brightness of the line is rather high. And what is the interesting speckle pattern inside the caustic? I clean it out. What still provides structural stability in the spiral beams? Generally speaking, the spiral beams contains a great number of Laguerre-Gaussian vortex beams, infinite number of Laguerre-Gaussian beams. And in order to keep such a huge number of vortices in steady state, it is necessary to fulfill at least two selection rules. The first, a necessary condition of is a strong relationship between topological charge of each Laguerre-Gaussian beam and radial number, written in such a simple equation. For example, for triangular beam and other polygon beams, the radial number is 0, whereas for the triangular beam, the topological charge, more exactly, sequence of the Laguerre-Gaussian beam in the series have 3 times m plus 1 for tetragon beams, 4 times m, and so on. And the second, a number of vortex trajectories that intersect the surface pulled on the caustic is equal to strongly specified number, call it the quantization number. For example, for snowflake beam, we have quantization number equal to 79, whereas for ordinary triangular beam, not the golden triangle, for ordinary triangular beam, we have only 7 quantization number. Thus, we are dealing with a special manifold of wave caustics shaped by featured matching of mode, amplitudes, and phases. The caustics have a great number of properties, but I focus on a major properties. As I said, the caustic, the spiral beam, contain a large number of spiral beams. This is a mapping phase pattern of the wavefront. At this point is the optical vortices. The acoustics embraces only a finite number of vortices. But outside the acoustic, we meet an infinite number of vortices. So that the topological charge, the entire beam, spiral beam, tends to infinity, whereas the beam that we can experimentally to measure it, topological charge have a finite value. For the topological charge of the triangular beam, we have 7, and for the tetragon beam, we have 8. In contrast to that, the orbital angular momentum have finite value for entire beam. You can see here diagram of the orbital angular momentum via quantization number. However, where did the speckle pattern, the fractal pattern, inside the caustic go away? Also, a mode matching suppresses the speckle pattern inside the caustic. A set of caustic points of the wavefront, here, that fork on the pattern. Control distribution of the energy fluxes that call it the structural thickness, according to Dennis and Barry. You can see here mapping the energy fluxes inside the triangular beams. The streamlines is distributed in such a way that to push the light out of inside and outside the caustic, so that the streamlines takes a form something like the triangular strips. The same pattern we observe and for tetragon beams, where caustic follows the tetragon contour. The main streamlines are turned into the straight skew rays placed on the stability surface. What happens if we delete the structural darkness both inside and outside the caustic? This can be relatively simple to do. As an experiment, we just diaphragm energy fluxes inside and outside the beam, remaining only thin triangular strip or tetragon strip with phase variant contour. The colors follow the contour phase values. And we observed a very extraordinary phenomenon. Right after the spherical lens, the triangle spiral beam disappears. It's destroyed triangle. Whereas near the focal plane, the triangle is restored. In order to destroy again after the focal plane, but approaching to the double focus, the triangle is recovered again, and the rest remains the same through those other beam lengths. The same phenomenon we observe also for tetragon beam. The caustic then disappears, then is restored again in order to finally take a previous tetragon shape in far diffraction zone. Thus, the wave caustics of spiral vortex beams will kind of remember the fine structure of the darkness, but the physical principle of such an amazing phenomenon remains as yet to be seen. And at last, I'd like to invite all of you to our annual conference, Digital Singular Optics, to be held in Crimea on the coast of the Black Sea in the end of the summer and in the beginning of September. And so, thank you for your attention.
Thank you very much, Professor. Now, let me see. There is I think there is a question here, and we have some minutes. Okay, from Gökhan Demirer, one of our scientists here. Just for his curiosity, is there an energy fluctuation on light pattern
Sorry?
Is there any energy fluctuation on light pattern?
Oh, I see. We talk about fluctuations. Yes, we have a great number of fluctuations, but I talk about average value of the beam stream.
Okay, Gökhan is all right? The answer is okay? Okay, he's giving his thanks. Okay, any further question? Let me see. So there is no any further question, Professor. Thank you very much for your contribution to our conference, and hope to see you face-to-face meeting in near future after this pandemic finish. So thank you. And next,
Thank you.
thank you. Let's move to the next talk. We have a speaker here, Professor Alpan Bek, and he's from Middle East Technical University, Ankara, Turkey. Now he's going to talk about pulse infrared laser crystallized silicon and germanium thin films. Alpan, please go for it. Thank you very much.
Hey, thank you so much for the introduction. Am I being heard properly?
Yes, okay.
I'm not following if my computer switched to full presentation mode or not, so okay, I think it works now. All right, so today I'm going to talk about pulse infrared laser crystallized silicon and germanium thin films. Those who were in the first session, I briefly introduced myself. I lead the nano-optics research laboratory in Middle East Technical University Department of Physics, and this talk is going to be mainly based on the thesis work of my students, Ceren, and my former PhD student, Kamil. Okay, so why do we need to crystallize thin semiconductor films at all? Let me give a very brief motivation. First, normally, well, there is already an ongoing research of the crystallization of thin silicon or semiconductor films in general in order to reduce the material size in device fabrication, because the thin films, however, suffer from their low material quality due to the fact that during the deposition they form an amorphous material network. They lose their crystal form. In order to improve the optical and electronic properties, crystallization of these thin films is essential. But however, typically in literature, we see that the semiconductor thin films are classically crystallized at high substrate temperatures reaching around 700 to 750 Celsius in order to maintain high quality of these crystals. However, when you think about the inclusion of this thin crystalline film technique into our technological devices, the material fabrication costs should be reduced. So elevated temperature processing has to be avoided as much as possible. So we don't we would like to avoid heating of the substrates at elevated temperatures. So for production lines, room temperature is always beneficial. And moreover, the choices for device fabrication on substrates are typically limited now to glass and even to elastomeric materials. And so these materials, glass and organic substrates, are really, they show low resistance to elevated temperatures at the range of 700 Celsius. So we need to really find ways to crystallize these thin films on substrates which are not compatible with elevated temperatures. And typically it's possible by irradiation of strong light. It can be laser light, it can be superluminescent LEDs or LEDs in general, but the order of the optical powers reach several kilowatts for this sake. And it's better to keep the optical powers used for this technique also as low as possible. And when you check the device quality, so-called thin semiconductor films crystallized on substrates, the thicknesses reach actually up to 15 micrometers. And so actually, it turns out that these cannot be regarded as thin films anymore. So if you would like to really go for an application in thin films or ultra thin films, you should provide high crystalline quality for semiconductor films up to a micrometer thickness or so. So it's essential to develop these high quality crystalline films for both wider applicability and also reduction of the material and processing costs. And several applications that can come to mind are those of the thin film solar cells and thin film transistor devices, in which both of the devices contain a thin semiconductor film supported on a substrate, typically glass or other materials are used. And however, now if you see the amorphous silicon response range for the solar cells is limited to UV up to certain wavelengths around red. But if you have a multicrystalline silicon film, it does have optical absorption up to near infrared wavelengths. So if you think of using these two materials in tandem, you would have a larger coverage. So just only having amorphous silicon would limit the spectral region. So very, very brief theoretical approach. It's an extremely shortened summary of what goes on when a thin semiconductor amorphous film is irradiated with lasers or light. So first of all, we use pulse lasers, and we do use infrared pulse lasers, moreover. Now, you first irradiate the sample with your laser pulses. What happens is that the photon energy converts into phonons and other kinetic energy of the charge carriers. And that formation of these thermalized electrons, free electrons in the material, takes place within a very short time. It's like around femto to 10 picoseconds regime. And then in the remaining time, the energy from these thermalized electrons are transferred to the lattice, forming in form of phonons. And after the heat buildup takes place at a range which is above the melting temperature of the film, the film initiates to melt. But after it's melting at the spot, there is also a heat diffusion of the material from its boundaries into the neighboring regions, the amorphous regions, also to the substrate, and there's some convection to the air. So all these heat loss mechanisms cause a reduction of the temperature of this liquefied or molten material. It starts to crystallize eventually. And at a certain regime, it's found that the latent heat relaxation from the crystallization of the film induces an interesting effect, which I can summarize here, called giving rise to a crystallization regime which is called explosive crystallization, which is as follows. This is the infrared laser pulse. Again, we generate a liquid phase silicon here in the center of the beam. And around the rim, the temperature starts to drop due to the heat loss to the environment. So the crystallization starts actually from these surrounding regions. Now, as the crystallization takes place, there is also an emission of the latent heat at the boundary, which causes a very narrow strip here around the rim of the spot to liquefy again, to melt again. So there turns out to be a kind of a front, a liquefaction and recrystallization front, which is very quickly expanding radially out. The same happens also inwards in the spot. So at a very short distance, that's why it's called explosive, you suddenly generate crystallized domains, okay, in this picture. So there is a lot of literature based on that. Now, this is, of course, interesting dynamics, but it turns out that this dynamics is not controllable because of the super fast crystallization. The formed crystallite size tend to be very small, which is not beneficial for device fabrication. You would like to extend the crystallite domains as large as possible to reduce interface formation between the domains, and then good conductivity of electrical properties of the film. So therefore, one needs to modify this explosive crystallization. And this is what we studied actually. With one difference, we haven't used a round spot focus in our system. We generated purposefully a line focus, and it's a kind of Gaussian in both sides, but their width are quite different. So it's like a few tens of microns wide, but a few millimeters long. It's a very extended ellipsoid, if you like. When you use this sort of beams, line focus, you start crystallizing the film at multiple nuclei. When you now sequentially move your focal line across the sample, you can give rise to nucleation and sustainable growth of the crystallite domains. And we back up our explanation using some thermodynamic simulations. This narrow ring you see around corresponds to that super cooled liquid silicon phase, which is due to emission of the latent heat due to crystallization of the central areas. Okay, so here are the quick view of the results. So we use line foci, which we send them in pulses, which do have certain overlap with each other. So these are not, how to say, neighboring each other, but they do have substantial overlap, which I can't show here, but you can imagine here that the line focus is like that, horizontal. Then you repeat the pulses by an overlap, and the overlap factor is actually quite large. What you see in these different optical microscope images are the crystallized silicon film with different overlap factors, starting from 99.2 up to 99.9% overlap of successive line foci. So you start rastering your focal spot downwards or upwards. And the dark regions you see around here are the amorphous regions, not crystallized regions. What you see here is that there is a reduction of the multiple crystallization sites with increasing overlap. And moreover, you can take these crystallized films now to electron backscatter diffraction microscopy, and you can map the formed crystal domains. The lower row corresponds to the map of the silicon crystallites, which correspond to these different overlap factors. And as one can see, one can provide quite long, almost macroscopic scale, long crystal domains, single crystal domains are being formed by increasing overlap factor. And if you check, this is 400 microns, so this is a little larger than that. I have a better figure here. So this is the same sort of EBSD image, but taken over an extended range. So the length of the y-axis is around 2.5 millimeters now. So you see even single crystalline domains reaching lengths of around several millimeters at high overlap factors. One consequence of growing larger crystalline domains is the buildup of the stress, because as you decrease the number of interfaces, you give less space for the crystal to relax, and therefore the stress starts to build up, and this can be monitored by Raman scattering. And when we do a Raman study by plotting the Raman peak center and the peak width as a function of a laser scan speed, smaller scan speeds correspond to high overlap factors. You see the Raman peak starts to broaden a bit more than it does at fast scans where the crystallites are small, and the Raman peak maximum it also shifts towards lower wave numbers. So in a similar fashion, we have studied thin germanium films as well. And germanium films are also interesting because they're used in some other technological applications than that of the silicon due to its different band gap. So they are more IR sensitive materials with respect to silicon. So we wanted to study also crystallization of thin amorphous germanium films in order to provide a domain for possible infrared sensing applications. And moreover, germanium has higher carrier mobility and a lower contact resistance as compared to silicon. So device fabrication out of thin crystal germanium can be highly interesting. In our system, we use a laser at wavelength of 1064 nanometer, which is of course still larger in energy than the band gap of germanium, but it is close enough to the band gap. For silicon, this wavelength is below the band gap. For germanium, it's above the band gap, but it's slightly above. So what this enables is that when you irradiate the beam through the film, not all of the energy is immediately absorbed at the top surface, but there is substantial remaining part of the laser beam reaching the entire thickness of the germanium film, so that temperature increase and crystallization and nucleation can take place at the lower interface rather than the top interface, because there is also some substantial back reflection at the lower interface, which gives an elevated temperature profile right at the lower interface. And when the crystallization starts from lower interface, we believe that the crystalline quality is better than the region in which parameter range in which the crystallization starts from the top surface. So we have worked on 300 nanometer thick germanium films, and here are similar results to that of the silicon. With the high overlap factor, you see overlapping crystal domains. One particular difference is that the crystal domains grow in a fan-like shape with germanium. as the EBSD shows. This is interesting, but still one can do a similar analysis using Raman spectroscopy on the germanium film and compare it to that of the crystal germanium, bulk germanium. We see it's nicely crystalline, and where the amorphous germanium doesn't show any peak here. This is the crystal version. And you see the crystal formation depends very finely on the optical fluence. If you are above the threshold just a little bit, you start giving damage to the film. So one should adjust the fluence of the laser very, very carefully. That's the message. And then XRD study on the film shows that the crystallites are mostly oriented towards 220, which is in agreement with the literature. So with that, I come to my last slide. We do have a model of how the stress forms on this germanium film. We think there's a strong compressive stress just between the glass substrate and the crystal film. But at the top surface, the stress is rather tensile than compressive. And this is our model for understanding of our Raman spectra. And I think I can skip the summary if the time doesn't permit. If not, maybe very quick understanding. So rather than staying in the explosive crystallization, it's beneficial to go into slow quenching regime, which is demonstrated both experimentally and theoretically. And thinner films than classical 10 micron or more is feasible at room temperature using infrared pulsed lasers. And crystalline domain formation at the macroscopic scale is observed. And for the amorphous germanium, we can even crystallize large domains for films as low as 300 nanometer in thickness. And the crystalline size, which we obtain this way, have a very large aspect ratio. If you compare the thickness versus the crystalline size, the aspect ratio is huge, 30:1. I think that's an important improvement on the current status. So these are my acknowledgements.
Thank you very much, Dr. Alpanpak. There are two questions actually here. We don't have time, but I want to ask you, maybe you can quickly answer. If you can read from the chat section, but I have to read again. From Yashar, he's giving also thanks. Have you considered the possibility of other structure or component forming during laser interaction? This is the first part of the question. And the second part of the question is, could it be interesting to engineer electric properties or some other physical properties to the ion exchange process during the molten phase with other desired ion from outside?
It could be, yes, it could be possible if you introduce some gas in the environment in a control and rather than the room ambient atmosphere. If you have a controlled atmosphere, you can think of including ions, because what you essentially create upon incidence of the laser pulses on the film is a small plasma plume, and these ions in the controlled atmosphere can be deposited or even included in the film. But well, we are not going that far, because our motivation is to do this task, to fulfill this task at the room conditions, at room temperature in the ambient conditions. We do actually see in Sim's study, which I wasn't able to show here, there is quite the amount of carbon which is included in the material from the simple carbon dioxide in the atmosphere.
Okay, next question from Gökhan Demirel, and he's also thanks you for amazing talk. He was wondering, is it also possible to control crystal axis of the sample, like some part 111 and some part 001?
Really interesting. It would be really interesting if we had that sort of control. So far, we haven't. We universally observe overwhelmingly 2-to-0 oriented crystalline domains. It might have to do with the thermal conductivity in between our substrate and the film. So by tuning the thermal conductivity of the substrate and the film, one may have that sort of control. I reckon, I cannot really say for sure, but it would be a nice study in itself. Yes.
Thank you very much, Alpan. I have to stop here. I have to move to the next talk. Okay. There is no any further question. So once again, thank you very much. Thank you very much. And let's move to the last talk for this section. Dr. Erkan Aksoy from Institute of Physics from Izmir, from the Department of Photonics, and he's going to talk parallel-based efficient TADF down conversation WLETs. Please go for it. Thank you very much.
Thank you very much, Hocam, for introduce. Can you see my screen now?
Yes, it's beautiful. Yeah, it's good.
Good. I'm gonna click. It's working.
We have 15 minutes, please. Yeah.
Okay. Thank you very much. Hello, everyone. Thank you very much for coming to listen here today. And also, I would like to thank all organizing committee for this really good conference. First, I would like to introduce myself. I am Erkan, and photonics researcher at Photonics Department in Izmir Institute of Technology. And also last year, I completed my PhD thesis from at Ege University Solar Energy Institute. And during my PhD thesis, I visited to Durham University Physics Department for focus on external dynamics properties of some parallel derivatives. And today, I'm going to talk about parallel-based efficient thermal activated delayed fluorescence conversion white organic light emitting diodes application. So this is my outline. I'm going to talk about my motivation and why I'm working with parallels, and also give some brief examples of parallel-based photonic application. So also in this experimental part, I'm going to share our experimental results and finish my presentation. Parallels, especially palladiums and palladium tetraester derivatives, are really excellent materials due to their unique photophysical properties. And also they have high molar absorption coefficient in visible region, high fluorescence quantum yield in solution phase, and their chemical modification from Bay or emit positions are really easy and low cost. And also due to their thermal, chemical, and photochemical stability, they have been used in many different photonic applications. So for example, OLEDs, organic solar cell or perovskite solar cell, and some frequency of tone conversion work, and also some sensing photonic system. And this is a simple PDI structure, and also its absorption and emission spectrum looks like this. And this is generally important for organic solar cell application because of their high absorption spectra is at this point, and it is the peak of the solar radiation. And some popular photonic devices using the PDIs are organic solar cells, organic light emitting diodes, and frequency of tone conversion. And PDIs are used as an emitter in the emission layer in OLEDs. And to explain briefly, OLEDs are multi-layer devices similar to, looks like a sandwich system. When the potential is applied, they emit light as a result of electrons and holes recombination in the active layer. And also we define this as electroluminescence. And generally orange and red parallels are used in OLEDs to obtain white light with combination of blue host material. And other popular application is the solar cell, and parallels have been used in active layer as an acceptor material to alternative to Fullerene derivatives due to their high electron mobility, high electron affinity, and also strong n-type characteristic. And this is a simple DOM conversion system. It is this system has a very simple and effective working principle. For example, there's a blue light source for excited phosphor materials, and a yellow, orange, or red phosphor material is coded on the top of the blue light source. And after the energy transfer between the phosphor and blue light, white light is obtained recombination of blue and phosphorus wavelength, looks like this. And currently, some of the conversion white LEDs have this working principle. For example, cerium yak material using in this DOM conversion layer. But there's some disadvantages of them. So those are the cerium yak's converter efficiency is just 75%. And also it's emitting just a yellow emissive, and also just can obtain cool white light. Also the phosphor material needed to too much levels like gram levels, and also it's make it very high cost. So, and in the literature, in recent years, some organic fluorophore groups have been developed for the alternative to cerium yak, and some of these are polyfluorine, BODP, or perlene derivatives. Also, compared to others, the PDI has a much higher photo stability. But however, PDI have a serious problem because of its polycyclic aromatic structure. This is aggregation cause quenching, so it means they can completely lose their photoluminescence if they don't have any steric group to prevent aggregation. So this limits the use of the materials. And to prevent this, PDIs are generally doped in a polymer host and dispersed in inert transparent polymers, for example, polystyrene or Xenex derivatives. And in organic electronic or in emissive material, they can exhibit emission from two different excited states after light and material interaction. So these are singlet and triplet levels. And also singlet excited states are commonly show high emissive and show generally a few nanosecond lifetime, also fast-lived. But triplet excited states are commonly show generally non-emissive with oxygen, and also they show long level if make the gas. And yes, in this fluorescence or phosphorescence material in the OLEDs, if all OLEDs make 75% triplet exciton, which fluorescent molecule can't use this, but they can use 25% singleton exciton. So also it make very low high device efficiency. But phosphorescence material-based OLEDs can use triplets too, but they have problems due to high energy state for blue phosphorescence OLEDs. Often, some organometallic materials or small molecules which containing heavy atoms like bromine exhibit phosphorescence, but the single state levels of blue phosphorescence generally high materials must be even higher than the blue triplet levels. So therefore, 25 extons are accepted by single state, and because it accepts the high energy, the molecular bonds can be broken and it causes the device to die quickly. And this one is TDF OLED system, and also these TDF materials can use a singlet and triplet states. Also, they can use 100% extons in the devices, and also they can emit from the single state, and they have less problem compared to phosphorescence OLED when using the blue TDF materials in OLEDs. So today I'm going to talk our report work, and also in this work we have synthesized some high fluorescent orange and green pellets, and we have used them as a dome conversion layer with a combination of blue TDF OLED. Pellets have been separately dispersed in an optical polymer host, and it's called Xenex resin with a low concentration of pellets like 0.1%. And this Xenex pellet solution coated on top of the broad blue TDF OLED again and again. And then as a result of the optimizing the number of coating of the orange and green materials, it was obtained the excellent white color balance, and you can see blue and a bit white LED devices. And these are the material used in this work, and this is blue TDF. It was not only used as a blue light source, it was also preferred due to its high external quantum efficiency in the devices and the broad electroluminescence spectrum. And thanks to this, it became easier to stimulate the orange material. Also, you can see the black curve, its electroluminescence of TDF, and the orange one is the PDI's absorption spectrum. And if we use the blue LED, it would be very difficult to excite it to parallel because of less narrow band. It was probably the 450 nanometers blue LED electroluminescence, so it would be very difficult to excite. So the first test of wallet production was done by coating only orange material in this work, and so you can see their spectrum. And the DC layer was thickened by the coating the PDI by spin coating method. And after coated the pellets, we were examined the OLED's series spectrum, and also it was determined that the hybrid white OLED followed an unexpected way to pink, contrary to expectations. So we couldn't get a good white balance. And then when the TDF electroluminescence was examined, we seen that the blue electroluminescence were filtered strongly by the PDI, and then its CA coordination is shifted after 70 times coded the PDI. So it couldn't navigate the expected line to white like this way. In order to go to the white zone, the filtered area was supported with Perlan tetraester. Also, it's emitting the green. So you can see the filtered area. Also, the PTA spotted the green emitting in this work. So here, PDI and PTE film thickness were optimized with coating numbers of PDIs, and white light was achieved by navigating over the CIA. So you can see the optimizing numbers. So the optimal white light was obtained by coating 60 times orange PDI and 30 times the green PTE materials. It was, you can see the black curves. So obtained the white light, optimal white light. So we can say it daylight. So these optimized non-convergent layers, photoluminescence quantum yield was over the 90% quantum yield. And thanks to this, the external quantum efficiency of the devices with this non-convergent layer and also without the non-convergent layer compared show each other. And when you look at this graph, you can see that the external efficiency don't decrease with compared to green one. Also, we just compared the ZNX, just quoted ZNX, and without it hasn't any parallels for search to output the light. So you can see that the blue curve was just this ZNX coated film, and all of them optimized. We can say that the daylight can show it in these devices, and this conclusion I can say that the aggregation conjugate problem of parallels has been solved with low dot concentration of PDIs, and the best parallel-based devices layer has been produced in this work with very high quantum yield, and also white light can be adjusted by the different thickness of the Dom converter with different materials, and there is an effective Dom conversion hybrid devices produced, like CIA coordination was 0.32 and 32. Also, maximum external quantum efficiency was 17.2%. Also, with perfect color stability and good color rendering. And I would like to finish my presentation here. First, thank you all organizing committee for this really good conference. Also, we know that from the first of light and light basis technologies workshop, I think in 2018 in Ankara, Gazi University. And also thank all TÜBİTAK projects and TÜBİTAK BİDAP and TÜBİTAK BİM1 projects. And also I would like to thank all co-authors for their contribution in this work. And thank you very much.
Okay, thank you very much, Erkan Aksoy. And actually, this is the last talk. And we will go for a lunch. Let me see if there is a question. Actually, we don't have time to take any question, but let me see. Okay, okay, then now we will have lunch break, and we will see back again at 2 o'clock. Once again, thank you very much, Dr. Erkan Aksoy, and see you then. Yeah, see you then at 2 o'clock. Bye. Have a nice lunch time.
Hi, Yasha.
Hi, Andrew, how are you?
Good, good, good. So I'll introduce all the speakers of this session.
Yes, do you have the program just now?
Yeah. Yes.
Yeah. The first speaker will be Professor Alonso. His talk will be plenary talk. Then
yes, no, it's fine, Yasha. I've got it. No problem.
Okay. Okay.
Okay. Well, I guess it's time to begin. So welcome everybody back to this afternoon session. So we have 4 talks, and we kick off with a plenary speaker. It's Michael Alonso. I think everybody who works in structured lights and waves in general knows Michael's work. He's made many, many seminal contributions. I think he spends a foot in Rochester and a foot in Marseille. But Michael, thank you very much for agreeing to speak here at this very nice event that Yasha has organized. And I'm going to hand over to you to introduce your topic and your surely wonderful talk.
Okay. Thank you very much, Andrew. Can you guys hear me and see my presentation? Good. Excellent. So yeah, thanks, Andrew, for the very nice introduction, and thank you, Yasha, and everyone, the organizers, for this invitation. It's a great opportunity to talk to you guys, share a bit of what I've been doing. We all wish we were in the same auditorium, but well, the time is what it is, and in the future, I'm sure we'll meet in person at some point. But in the meantime, these meetings like this are a great opportunity to share our work. So as Andrew said, I have one foot in Rochester and another one in Marseille. I'm currently in Marseille at Centrale Marseille and Institut Fresnel, but I'm also affiliated with the Institute of Rochester in the US. So I'm going to be talking about the Poincare sphere and some of its generalizations for different uses in optics. So we're all familiar with the Poincare sphere for polarization, but I'm going to show you how it can be generalized beyond polarization and even for polarization for other uses. So let me start by just reminding you what the Poincare sphere is. So if we have a paraxial laser beam, let's say monochromatic, let's assume for now, coming towards us, and we know that the electric field at each point is going to trace an ellipse, and intensity corresponds to how big this ellipse is. Phase corresponds to at each time where the arrow of the electric field is while running around this ellipse. Those two properties we don't call polarization. What we call polarization is the shape and orientation of the ellipse. And for this, we only need 2 parameters. One, which I'm going to call phi, which tells us about the orientation of the sphere. So this phi goes from 0 if it is horizontal, and then I define this angle here as phi over 2, so that when we get to pi, it is vertical, and when we go to 2 pi, it's horizontal again. On the other hand, the ellipticity, how round or not this ellipse is measured by this angle theta, and we can measure this angle. Well, define this angle as the angle of the box that contains the ellipse. And again, it's defined as theta over 2, so that when we have circular polarization, theta is pi over 2. When theta goes to 0, this gets more and more linear. And then if we change the handedness of the polarization, well, we can think that the box reverse and it goes to minus pi over 2. Now, these 2 angles, one from minus pi over 2 and one from 0 to 2 pi, you can think of them as latitude and longitude as coordinates over a sphere, and this is an abstract representation that we call the Poincare sphere. So we characterize each shape of the ellipse as a point on the surface of the sphere. So these are the polar coordinates. The Cartesian coordinates happen to correspond to something we call the Stokes parameters that are measurable quantities. So what we measure is the intensities of each component and the correlations between the components. That gives us what we call a 2x2 polarization matrix, and we can decompose it into these 4 Stokes parameters. S naught is the intensity. We can normalize the other 3 to S naught, and they correspond then to the Cartesian coordinates here. And in fact, this definition lets us expand the meaning of the Poincare sphere to partially polarized light, light that is not purely monochromatic, if the electric field traces something that is not a monotonous ellipse, but it fluctuates more in time, this degree of randomness corresponds to a radial coordinate here. So when we have light that goes as much to the left as to the right, for example, we're close to the sphere. We can think of it at average, the points that are dancing around the surface of the sphere, and their center is somewhere inside the sphere. So the three polar coordinates, spherical coordinates on this abstract space tell us about three different aspects of polarization. So this is the standard Poincare sphere. Let me then just remind you of a couple of other ideas from paraxial optics. One is that of geometric phase. And the idea, I'm going to show you the simplest example. Imagine that you have a, let's say, right-handed circular polarization beam, and it hits a half-wave plate. The half-wave plate is going to reverse the handedness of that polarization. It's going to make it left-handed. And then if I have a second half-wave plate, it's going to come back to right-handed. And the phase of this intermediate beam and this final beam has to do with the orientation of the fast axis of this half-wave plate, which correspond to how we go from right-handed to left-handed. That is, how we go from the North Pole, which, remember, corresponds to right-handed circular polarization, to the South Pole. If we come back and forth the same way, then we say that we have a zero phase between the initial and final field. But if we rotate, say, the second wave plate, and then we come down one way and up the other way, that causes a phase on the final beam that happens to be proportional to 1/2 of the enclosed solid angle on the Poincare sphere. So the geometric phase is an extra phase that a beam can accumulate, not due to the optical path length it has propagated. That's what we call a dynamical phase, the dynamic phase, but to this transformation of the internal degrees of freedom of the polarization between the initial and final states. And the Poincare sphere provides a nice interpretation for this. I should say that here I'm using the simplest case where I use half-wave plates and such that they do a transformation of polarization along what we call geodesics, great circles. So in this case, this interpretation of the enclosed solid angle is strictly true. Must be said that when the polarization does not transform with wavelengths along geodesics, then the interpretation has to be changed a little bit. Whether we call it geometric phase or not is a matter of interpretation. But suppose that I have some this is a Poincare sphere, and I have some initial polarization at some point on the sphere. Then I have a wave plate, a first wave plate, that causes a rotation of this point on the Poincare sphere. That's the change of polarization. And the angle of rotation is the angle of retardance. And the direction, the axis around which we rotate, is the point on the Poincare sphere corresponding to the fast eigenpolarization. So suppose that we go from here to here, and then I use a different retarder with a different eigenpolarization, different retardance, that brings me back to the beginning. So I started and ended at this polarization. The phase that I accumulate is no longer the enclosed solid angle, but it does have a meaning. One way to see this meaning is to go and observe this sphere from the point of view of the incident polarization, and then the projection onto this plane of the two axes of rotation are at an angle. And that angle happens to be this extra phase that we accumulate. So if I do a projection here and then I look at it from a different point of view, you can see that from this point of view, I project, and the projection of the two axes that are telling me about the wave plates gives me this angle, which is this extra geometric phase. Okay, that is the concept of the Poincare sphere for polarization and geometric phase for polarization. However, beginning, I think, in the late 90s, Miles Paget and Johannes Courtiel realized that you could use the Poincare sphere to describe other aspects of optical fields, and they treated this as a block sphere. So it's a way to represent a two-vector complex vector. And if you think of a beam, Laguerre-Gauss beam, for example, a pair of Laguerre-Gauss beams of order 1, and all the different superpositions that you can achieve, those gives you a family of beams that, like polarization, corresponds to a distribution on the sphere. So for example, let me show you that here. All points in the equator correspond to what we call a Hermite Gaussian beam with different orientations. Just like for polarization, it corresponded to linear polarizations with different orientations. The North Pole corresponds to a donut beam, a Laguerre-Gauss beam, with a given orbital angular momentum, a given vorticity, like this, so that the phase grows in a given direction. And the South Pole corresponds to a very similar beam, but where the vorticity goes in the opposite direction. So instead of the vertical axis on the Poincare sphere being the spin angular momentum, it is now the orbital angular momentum. And all the other intermediate points correspond to different beams. This representation was very limited to this very small family of beams, but it has since been generalized in many ways, as I will describe, to more generic, what we call structural Gaussian beams. These are beams that have a given transverse profile that is preserved as the beam propagates. It just grows hyperbolically. Without, I should say, without rotating. This morning we saw a talk where there was a description of beams that rotate on propagation. Those are very interesting, but are not the ones that we're talking about here. So the more common examples are the Hermite Gaussian beams, the Laguerre Gaussian beams, and also the Ince Gaussian beams. So I'm going to be talking about these types of beams. These lines that I show here that are delimited the regions of high intensity from the darker regions. I will be discussing this in a little bit. We will call them caustics. The other thing that I wanted to say about these beams is that they are given by a total order. So we define a total order of these beams as the number of nodal lines they have. It's a way to define it. So for example, the Laguerre Gaussian beam, it has a given number of phase oscillations, or in this case, nodal lines in the azimuthal direction, and a given number of radial lines. Or the Hermite Gaussian has a given number of nodal lines in the vertical direction and in the horizontal direction. So we'll call this N, the total order of these beams. So many people generalized the concept of the Poincare sphere to define these types of beams, in particular for a subclass, which is called the generalized Hermite Laguerre Gaussian beams. So for example, here we have an N equal 4. The phase goes around 4 times. So the North Pole is still a Laguerre Gaussian beam. And the South Pole is the counter-propagating Laguerre Gaussian beam. On the equator, we have Hermite Gaussian beams. And elsewhere on the sphere, we have beams that are intermediate to them. And in fact, the first speaker this morning talked about these beams, not from this point of view. These can be written as Hermite Gaussians evaluated at complex arguments. And in fact, in a recent paper, we found that this complex argument, making another connection to polarization, can be written as a Jones vector that maps onto the sphere. So we use different theoretical tools from polarization to describe not polarization, but beam structure. So this generalizes the Poincare sphere for beams that I mentioned before in a way that this is no longer log sphere. That is, this beam is not a linear combination of these two. It's a more complicated transformation. And also for each given N, there's not one, but many spheres, depending on the, for example, the radial order here. So this beam only has one dark point at the center, but we can create for another family of beams with the same capital N, a different sphere where the Laguerre Gaussians now have order 1 radially. There's no trivial way to transform these beams into these beams, but there's a trivial way optically to transform this beam into this beam or into this beam through the use of cylindrical lenses. So for polarization, a rotation of the sphere is enacted optically by a wave retarder. For beam structure, a rotation of the sphere is enacted by combinations of cylindrical lenses. So one can generalize this to account for any type of beam, and perhaps the more general way to do this is to use Majorana's construction for spin systems, where for any beam of order n, you can represent the beam structure through a collection of n points, not just one point over the sphere, but it's n points over the sphere. If you use n points over the sphere, there's a simple way, an elegant way to map a distribution of n points, here shown as the corners of solids, just to make it easier to visualize, to the shape of the beam. And the symmetries of the beam are going to be encoded somehow in this and the symmetries of this collection of points, which is often called a constellation. So one particular example that we looked at is the beam associated with the Platonic solid. So where the corners, and please ignore the red points, just look at the purple points here. The corners correspond to the corners of the 5 Platonic solids. So for example, here we have a beam associated with this cube that has 8-fold symmetry. But if I make it pass through appropriate combinations of cylindrical lenses, I enact a rotation of the sphere, and I can make it have instead 4-fold symmetry. Or if I use a different transformation now and put a corner on top, I can get a beam with 12-fold symmetry. And there's a nice relation with ray optics as well that is explained in this paper. So, these Majorana constellations, these collections of points, are the appropriate generalization of the Poincare sphere representation for beams. However, we wanted also to see a more intuitive representation to understand high-order beams instead of rays. So what I'm going to spend a few minutes talking about is how to understand the Poincare sphere of beams, thinking not in terms of waves, but in terms of rays. So remember, these beams are beams that propagate and keep their cross-section under propagation up to a natural growth and natural expansion due to diffraction. So we need to think of families of rays that have the same property. So such families are, for example, given by this. So if I have a family of rays, which are straight lines, that define what we call an ellipsoid, a rule hyperboloid, sorry. The cross-section in this case is an ellipse, and as it propagates, the ellipse gets bigger, but it has the same shape. So this seems to be a nice way to represent a family of rays associated with that keeps its profile under propagation. Now this family of rays can have different orientations, and it can be more flat or more round. So therefore, and it can even reverse its handedness. It has a handedness, and it can go in the right-handed sense or in the left-handed sense. So it is natural now to represent it as a point on the Poincare sphere that represents, like for polarization, the orientation, the ellipticity, and the handedness of the family of rays. And again, the vertical axis here corresponds to the orbital angular momentum. The more round this is, the closer we're to the top. Now, if I want to compose, for example, a Laguerre Gaussian beam, I need more than this family of rays. True beams need a 2-parameter family of rays. So I need more rays than just this. I really need all the rays with the same orbital angular momentum. So I'm going to use all these families together that correspond to different points on the sphere at the same height. And now I accumulate them. And as I accumulate them, I can see now something that resembles a donut, so like a Gaussian beam. And it's dark at the center and it's dark outside, just like our Gaussian beams are. So we see that this ray-based Poincare sphere representation is not a collection of discrete points, is a curve, is a continuous succession of points like this. And the more close or open this curve is, the thicker or thinner the donut is. Essentially, the different radial orders of Laguerre Gaussian beam. Let me try to explain these two figures, but for that, I'm going to go and show you something else here. So actually, let me go back here. And what I'm showing you here is this point. If I look at its projection onto the equatorial plane, so just this flat plane here, oh, it gives me a point here. And this elliptical family of rays, if I just look at its cross-section at the initial plane, it gives me this ellipse here. So again, as I go around, whoops, sorry, wrong slider. As I go around, this point rotates and the ellipse rotates. Now, when I start accumulating things, I see that I start forming, I start accumulating the ellipses and I start forming envelopes of this. And this is what I'm going to call the caustics. So when I go around, I have all these families of rays and I have the envelope of all these ellipses of rays, which are near the brightest parts of the beam. So it's an outer caustic that separates darkness from light, let's say, and an inner caustic as well. So what I wanted to see, what we wanted to see is there a connection between the shape of these caustics and hence the shape of the beam and this abstract Poincare representation? Well, to answer that question, let me show you here a more general case. So now I'm just going to look at that, at this projection over the equatorial plane. And suppose that I have not a circle, but some arbitrary shape here. So this is the curve, the projection of the curve that defines the beam. And what I'm going to show you here is 2 points. So if I look at this point, I can find a little circle that touches this point and touches the edge of the equator, and it has its center here. There's another circle that touches this point and touches the edge of the unit circle, and it has its center here. As I move around to different points, these circles are going to change, and their centers are going to start drawing some lines. So if I move around, I see that this circle changes, and their centers start to draw some curves. So I go around this shape, and then I come back to the beginning. So each one of these two circles drew a little curve. On the other hand, the beam, we accumulated all these ellipses, and we can see the caustics, the outer caustic, and the inner caustic. So these are the things that we see physically for the beam. Now, is there a connection between these two curves, abstract curves we drew, and these two? The answer is yes. It turns out that if I treat this unit disk as a sector of the complex plane, and then I take the square root of that, and then which is also a complex plane, and I look at the coordinates here, these curves go to the caustics. That is, if I use a mapping like this, I put a grid here, and I do a conformal mapping from this space to this space, these two curves transform into the caustics. So what this is showing us is that by using this ray representation of the in the Poincare sphere, we can see that the two caustics of a beam that set its shape are not independent. They have an intimate hidden connection through this representation here. Because if I know this caustic, I can map it to this plane. I can find the black curve for which this curve is what we call a medial axis, the location of the centers of these circles. And then once I determine this curve, I can find the second curve and then come back and find the second caustic. So the two caustics of the beam are not independent, they're intrinsically interconnected. So if I come back to my picture here, what I'm showing is precisely that for the Laguerre-Gaussian beam. This circle projects into a circle here, which is this black circle. And then the little circles here draw this medial axis, this curve of the centers, that is the blue curve, that maps onto this caustic. But there's another family of circles that go like this, whose centers are this brown-orange curve that map onto the internal caustic. Now, the more interesting thing comes when we consider sending this beam through cylindrical lenses. And again, for this Poincare sphere, pairs of cylindrical lenses enact rotations. So if I send this Laguerre-Gaussian beam through a pair of cylindrical lenses, we're enacting a rotation around this axis, and we see that this circle has a projection that is no longer a circle, it's an ellipse, off-center ellipse, and this changes the shape of these two medial axes. This one looks like a little fish, and when we do this mapping, they go into this deformed inner caustic, this deformed outer caustic. The beam changes its shape, and if I keep transforming the beam like this, at some point, I'm going to hit, I'm going to make this circle vertical. Its projection is then a straight line. And by geometrical magic, these medial axes become parabolas that map onto straight lines. And we get a Hermite Gaussian beam. So we can understand with rays why Laguerre-Gaussian beam can transform into an Hermite Gaussian beam when we use the appropriate set of cylindrical lenses. And before, when I moved this slider here, I was changing the radius of the circle. That changes the aspect ratio of this rectangle. So it changes the type of Hermite Gaussian beam that I'm talking about. So using this ray representation of these beams, we can understand a series of things. For example, the geometric phase for beams. This is something that was measured by Kiko Galvez for the first time, and then by several others using interferometry. But here we can get an intuition of how this works with rays. So if I have a Laguerre-Gaussian beam like this, these are its rays, and we transform it. So I'm going to see, I'm going to represent this by the center. If I transform it with cylindrical lenses, I go to a Hermite Gaussian beam, then to a Laguerre-Gaussian beam here, and then I bring it back a different way. I get a Hermite Gaussian beam with a different orientation and come back here. I get back the same initial beam, but with an extra phase. And the interpretation of this extra phase, which is proportional to 1/2 of the solid angle, is quite intuitive now. If I compare the beginning and the end, the family of rays looks the same, but if we see that the green family of rays here, at the end of the transformation is not at the same place, it's somewhere else. So the whole set of rays trace the same shape, but each ray is changing where it is. So this geometric phase, then it does not come from each ray accumulating a longer path length, but from a change of the role that each ray is playing on the beam. So it is truly a geometric transformation of the beam. Rays do not end where they began, and because they started with different phases, that's going to change the overall phase of the beam. I see that I'm running a bit late, so let me just tell you that there's a similar interpretation for the GUI phase that beams accumulate under propagation. Well, I can show you very quickly. If you let the beam propagate towards you, rays travel on straight lines, and we can see how, while each dot, which is the cross-section of a ray, is moving on a straight line, the pattern is growing. and the role that each ray is playing on this pattern is different. They seem to be cycling. And this cycling of rays along the ellipsis explains this gooey phase. It also explains phenomena like the self-healing. If I block this beam here, so I block some rays, after I let it propagate, those block rays are going to move out of this feature and new rays will come in and replace them. Okay. So using these ideas, we propose and show that you can measure for these type of transformations, both the geometric and gooey phase of a beam by simply blocking part of the beam and seeing what happens to the shadow. So let me come back to polarization. So now we've seen that the Poincare sphere and its generalizations can describe not only polarization, but also beam shape. Now let me forget about that and come back to polarization. And much of this work was motivated by talking to a colleague at Rochester, Tom Brown, who came up with this very simple device, which is a glass window subjected to stress with trigonal symmetry that creates a very interesting and simple birefringence pattern. We noticed that when you send a beam with, say, right circular polarization through this window, what comes out is something that we call a full Poincare beam, which is a beam that has all possible polarizations on its cross-section. If you fill it in a slightly different way, you get something that's a bottle beam. So you can create a beam that is very dark at the center and where the intensity grows very quickly in the 3 dimensions. But what is more interesting about this device, in my opinion, is an application in interferometry, in imaging polarimetry. Suppose that you have a point source emitting light with some polarization, and you form an image of that point source. We know that imaging systems are not perfect, and the image of a point is going to be what we call a point spread function, an extended patch of light. If you put this glass window on the pupil of this imaging system, and then you filter out, let's say, the right circular polarization component, the point spread function is going to acquire a shape that tells us what the polarization is. So if the field has, let's say, right circular polarization, you would get a blob. If it is left circular polarization, you get a donut. If it is linear, you get something like a croissant. And depending on the orientation of the polarization, this thing changes orientation. Even if you change the degree of polarization, there's a change in the shape of this point spread function. So we use this idea for several applications where we image sparse objects, in particular with colleagues here in Marseille, Rignon and his group. We use it to characterize multi-core fiber bundles that they use for endoscopic applications. So these are fibers that have hundreds of cores, independent, with very, very little crosstalk. And the idea is that you can inject light into each one of these cores and phase that light appropriately so that you can, on the other end, focus light and steer a beam, etc. However, they did not know what happened to polarization along each one of these cores as it transmits from one end to the other. So we just image this using this window. So you can see here that the little croissant shapes here that are telling us for different illuminations what happens to the polarization. So you can measure in a single shot, even in real time. We even took measurements where we're manipulating the fiber to see sensitivity to manipulation. We can see how the polarization coming out changes, and we can see what paths it fills in the Poincare sphere. But for the rest of the talk, I'm going to talk about non-paraxial polarization, which will require further generalizations to the concept of the Poincare sphere. So normally we think of paraxial beams where only the X and the Y components of the beam are important, but not the C components or Z components. But if we have a strongly focused field or an evanescent wave, or we're very close to the source, we cannot just throw away these Z components. And now we have a 3-vector. When we had a 2-vector, that means 4 real quantities, the real and imaginary part of each one of the 2 components. Of those 4 degrees of freedom, 1 was total intensity, 1 was a global phase, and we were left with 2 that were the 2 polarization parameters, the coordinates over the surface of the sphere. Here we have a 3rd number, which means that we have, after removing intensity and global phase, we have 4 independent quantities. How can we represent this? And let me just consider for now full polarization, so fully monochromatic fields. So is there a good way to represent the 4 degrees of freedom of polarization of a non-paraxial field? Well, John Hanna in Bristol used, again, Majorana's construction to come up with a very, very elegant description of polarization in terms of a sphere, which I call the Hanna-Majorana sphere. So to represent a polarization ellipse that now can be oriented in not only in the X and Y directions, but also in the Z direction, we can use 2 points over the sphere, no longer 1 point, but 2 points. And these 2 points have a nice geometric interpretation. So if I have this ellipse that goes like this, the 2 points correspond to the 2 points of view from which I can look at this polarization ellipse, and it looks like a right-handed circle. So this is one, the other one is here. So these are the 2 directions from which I can look at the sphere, and it looks like a right-handed circle. I could also think of putting a Rayleigh scatterer at the point where I want to measure the polarization, and I look at the far field scatter field, and the 2 Majorana points are the 2 points at which the scattered light has right circular polarization. So this is a very nice, elegant way to represent non-paraxial full polarization in terms of 2 points over the sphere. Well, you can also think of it in terms of fitting a cylinder on the ellipse and seeing where the axis goes. It has 2 small problems. One is it's a technical aspect that I'm not going to discuss, has to do with how it treats the normalization of intensity. The second one is more interesting, has to do with geometric phase. One can generalize the concept of geometric phase to non-paraxial fields. And one would hope that if we have a transformation of polarization, these 2 points would move around, enclose a solid angle, and this geometric phase should be related to that solid angle. It is, but in a non-trivial way. So to address that problem, in recent work with Mark Dennis and Kostya Pliok, we looked at geometric phases in 2 and 3D, and in particular to a new representation of polarization that does respect this property of geometric phase. So I'd like to say that the idea is taking Majorana's representation, so this is Mr. Majorana, and giving it some features from Poincaré. So when we find the right mixture, we have the nice properties of the 2 representations, and essentially we get another representation where the polarization ellipse is represented by 2 points, but now we have this nice property of geometric phases being related to solid angles. So let me show you this. This is a definition of the geometric phase. And for example, if I have a transformation of polarization, continuous transformation of polarization, these 2 points move around. And when we come back to the beginning, they enclosed 2 solid angles here. And half of those, the sum of those 2 solid angles corresponds precisely to the geometric phase. So I call this sphere the Poincarana sphere, because it's a mixture of Poincaré and Majorana. I should mention that, as we will see in a minute, there are cases where I can consider a transformation of the polarization ellipse, where I come back to the initial polarization, but the ellipse, this major axis started here, ends up here. And in this case, the two Poincare points do not trace each a closed loop. They together trace a big loop. But still, the geometric face is 1/2 of the solid angle enclosed in this loop. And this distinction between the two cases I mentioned is related to something that has received some attention recently, which is to do with Mobius strips of polarization. So, for example, this is one of these full Poincare beams that is strongly focused, so it requires a Z direction. And I look within the loop what the orientations of the ellipses are doing. These are the major axes. And as I go around, also, I see what the 2 points on the Poincare sphere are doing, and each one trace a loop. This point here is what we call a C point, a point of circular polarization. And if I make the ellipse a bit, the loop I'm looking at a bit bigger, like this, so that it goes around that, I notice that there's a topological change here. Before, this band of the major axis of polarization was not a Mobius band. But when I cross that point, something's happening here, and we go to a Mobius band. And similarly, something happened here. We went from having 2 loops to having a single loop. So this geometric description reflects the topological features of the field, in that having a Mobius and non-Mobius transformation corresponds to having 2 or 1 loops over the sphere. Let me conclude with a brief word about partial 3D polarization, which gets unfortunately much more complicated. Now we need to think of correlations of each one of the 3 Cartesian components with themselves. That gives us a 3x3 Hermitian matrix, and we can define this describe this in terms of a generalization of the Stokes parameters. The regular Stokes parameters for 2x2, you can think of them as the coefficients of an expansion of the matrix in terms of Pauli matrices. Here we use their generalization, which is what is called the Gell-Mann matrices. But those are mathematical technical details. Essentially, what happens is that we need 9 real numbers to define this matrix. But one of them, which I call S0, is like the total intensity. So that is used to normalize the other 8. And then we can define an 8-dimensional vector that is a hypersphere. That is the one generalization of the Poincare sphere for partially polarized 3-dimensional light. Of course, visualizing 3 dimensions is very difficult. So that makes this treatment not so intuitive. This numbering scheme for these parameters is something that I propose in recent work. I think it lets you understand things a little bit better, because you can look at the different subspaces. In particular, it turns out that you cannot inhabit the whole interior of this hypersphere, and the true shape that you can inhabit is very complicated. But if you look at the subspaces, you can find the regions that you can occupy for the different parameters. But that's not important for now. What I wanted to conclude with is an actual application of these parameters in fluorescent microscopy. And this is work that I've been doing with a group of Sophie Fasley here in Marseille that was published recently. And it's a way to use this stress window that I described before to image multiple fluorophores, fluorescing molecules in a sample. but where we want to determine not only their X and Y coordinates with super resolution, but also the height and the 3D orientation. So these molecules are gonna have an orientation. So we need two angles to find the orientation of these molecules, and they might even be vibrating. So we assign a solid angle to tell me how much these are vibrating. So we want to retrieve these 6 degrees of freedom, X, Y, Z, two angles, and an angle of vibration. So we call this method coordinate and height super resolution imaging with dithering, that's vibration and orientation, which gives me the nice acronym CHIDO, which is a Mexican word for cool. So the idea is to form an image through this window, separate the image into two corresponding to two circular components, and look at the two images. So what happens in this case is, again, we encode in the point spread function of the two images all this information. So of course, X and Y would just make these move like this. But if I change the orientation of the molecule that I'm showing here, the 2 point spread functions would co-rotate by twice the angle as the molecule. I can also change the orientation of the molecule off the plane, and that will give me a different change on the point spread function. I can make it vibrate within a cone, and that gives me a different change on the molecule. And another interesting thing is if I come back to this, if I change the height, the 2 point spread functions rotate, but in opposite directions. So I can distinguish height from orientation. And these point spread functions happen to be linear combinations of the point spread functions for associated with each one of these Stokes parameters. So really they're an alphabet. I have an alphabet of point spread functions, and their coefficients are these 8 Stokes or 9 Stokes parameters. So there's a natural connection with what I was discussing before for 3D polarization. So just to finish real quick, let me show you some experimental results. These are emulations with fluorescent beads where we use polarizers to emulate the direction of the molecules for different orientations. You can see the point spread functions co-rotating. If I change the height, they counter-rotate. And here I can show you how we can retrieve from measuring these point spread functions, their height and their orientation. So it works. Still, we have work to do, but it does work. We've applied it to single molecules, and we can see how we can recover positions, heights here in color, and orientations, cone angles by comparing the observed point spread functions to the theory. So in summary, the Poincaré sphere is more than polarization, it's more than a block sphere, that it's more than something to represent a qubit, let's say, a pair of complex numbers. Its generalization involves higher dimensionalities, sometimes can be expressed as, in terms of a sphere with many points. There are Poincaré spheres for the ray optical description, which corresponds to paths over the sphere, and they reveal many geometrical aspects of a beam. And finally, by using birefringent windows, we can apply this to measure polarization, both paraxial and non-paraxial. Finally, I thank my co-authors, so current and former students and postdoc, my collaborators Sophie Presley and Hervé Rignon and their groups here in Fresnel, my collaborators Tom Brown and Nick Van Mevekes in Rochester and their groups, and Mark Dennis and Konstantin Blioch. And finally, thank you and the funding agencies that allowed this work. Thank you very much.
Thanks, Mikhail. We actually are dead on time, so I don't see any questions in the chat box. Does anybody have an urgent question that we want to throw to our speaker? Otherwise, I think we're going to have to move on and maybe you can communicate directly with Michael if you have some queries. Is there anything? I don't think so. Then, Michael, I think I'm going to have to move on to the next speaker then, but thank you very much for the excellent talk.
Well, thank you. And yes, if you have any questions, just let me know. Okay, so I'm going to stop my screen sharing.
Great. So do we have we go on to 3 invited talks in this session. The first one by Frank Coppens. Frank, do you want to load your talk?
Yeah, hi.
Great. Frank, I'm going to hand over to you because we're running a little bit behind time. And so perhaps you can get going and introduce, you're from ICFO, and yeah, we look forward to the talk.
Okay, excellent. So you can see my screen and my camera, right?
Yes, perfect, perfect.
Okay, very good. I actually changed my title a bit because I decided to speak a bit more about the applications of two-dimensional materials into optoelectronic and nano-optoelectronic devices. My name is Frank Coppens. I'm from ICFO, the Institute of Photonic Sciences. We are based near Barcelona in Spain, and we are an institute of about 500 people that is highly international and focusing on anything that is related to light. And in my group and several other groups, there's strong activities on two-dimensional materials. And the most famous one is, of course, graphene, but there are now thousands of two-dimensional materials. And this field is rapidly evolving, as I will also show you today. There's a lot of interesting fundamental science to be studied in these materials, but there's also a strong push for applications. And I wanted to update you a bit on the progress on those applications. This is really going to be a broad overview. If you have any more detailed questions, ask them, or please contact me or look on these websites shown here below. So two-dimensional materials are materials that are only one atom thick, and the one that you probably all know is graphene, which you can isolate from graphite. Graphite is a bulk material. That's what we have in our pencil. And if you peel off from the graphite thinner layers, and you can actually do this in a very simple way. You can even do this with just Scotch tape. You can peel off small layers, and some of these are very thin and look like this, which are then called graphene. And that's basically a lattice of carbon atoms, nicely organized in a crystal. This is important. And this crystal, in this case, is a honeycomb, a hexagonal lattice, but you can also have different kinds of lattices. Now, you can also think of the same type of honeycomb lattice, but just replace some of the atoms. And a famous material here is boron nitride, where one of the atoms is replaced by boron, the other one by nitride. And because the system is not symmetric anymore, a band gap opens, and the sublattice symmetry is broken, that's how they call it. And then a band gap opens and you get an insulating material, which is completely different from graphene, which is basically semi-metal, where you don't have a band gap and the conduction and valence bands touch each other. And then you have a bunch of other semiconducting 2D materials where the band gap is somewhere in the optical range, 1 electron volt, 2 electron volt. And a famous one is MOS2, molybdenum disulfide. There are many types of 2D semiconductors that are based on a metal atom and a charge-Gizen atom. So there are a lot of applications you can develop with these materials. For graphene, I will mention many, but flexible electronics is the first thing that came up. Then if you want to make transistors, graphene is not great. For that, you can better use a 2D semiconductor, as you can see in this picture here, and transistors have been made really at the nanometer scale. And boron nitride is an atomically thin, strong insulator. It can be used, for example, as an encapsulant or tunnel barrier. Now, this is already from a couple of years ago, but recently a lot of progress has been made in isolating 2D materials with more exotic properties. So this is an example of a topological insulator that is a material where the conduction is only taking place in the edges, and in the bulk it's an insulator. And you can actually see nicely in this plot here that this material shows quantized conductance, even up to elevated temperatures. That really shows you that this is a topological insulator. You can make monolayer magnets. That was a long time an open question. Can you make a magnet only one atom thick? And yes, that's possible. And you can also make superconductors that are only one atom thick. Here is an example shown. A bismuth-based system. There are cuprates now that are two-dimensional, but also actually you can make graphene superconducting, which is quite exciting. I will show you in a minute. So all of these materials have unique properties, electronic and optical properties, but the beauty here is that you are not limited to just using one material. You can actually combine these materials into what we call heterostructures just by stacking them in order to build the device you want, right? A device almost never consists of a single material. It always consists of a combination of materials, right? You need a semiconductor, you need contacts, you need a gate, you need encapsulant. And if you do this all with two-dimensional materials, you create a very clean system. The interfaces between these materials is very clean. And the reason is actually that these systems don't have any chemical bonds out of away from the surface. There are no dangling bonds. And the connection between the materials is also not a chemical bond. It's actually just a van der Waals force. So actually a mechanical force that keeps them together. So that means that you can build these heterostructures using any material. You don't need to find materials that have similar types of lattice constants as, for example, you have at molecular beam epitaxial growth. So you can really build any heterostructure you want. And to show you that these are very clean, here's a transmission electron microscope picture that shows indeed the atomic planes without any distortions or contamination. Now, up to just a few years ago, people thought that this was the story, and that's already a big story, that you can just stack these materials, but you can actually do something more. You can also twist them. And if you take two crystals, and in this case, I'm showing this for honeycomb lattice. If I take two honeycomb lattices, like a graphene, and I twist the crystals, I obtain another periodic structure, and that's called the moiré effect. I'm sure you have heard of it before. You can see nicely in this image a periodicity appearing that is, that is, one second. This periodicity is depending on the angle, and electrons that are moving in the system actually feel this periodicity, and that will dramatically change the electronic properties, but also the optical properties. And the most dramatic thing that was observed in 2018 is actually this experiment where they took 2 layers of graphene, they twist them by 1 degree, which is a very small angle, more or less what I showed you in the animation. And they found that the system becomes superconducting. So here's a measurement where the vertical axis is temperature, the horizontal axis is actually the amount of carriers in the system, so the doping, and then the color scale is the resistance. And they really saw that for specific range of doping, the system becomes superconducting, which is quite bizarre because you just take two materials, you twist them by 1 degree, and you're making it a superconductor. And so we're also studying a lot the optical properties, which are very different, as well as the plasmonic properties. And so now many of these twisted materials are being studied, and it has been shown that they can also become ferromagnetic, they can become ferroelectric, and other exotic effects have been seen, such as the coexistence of superconductivity and ferromagnetism. You may think that it's actually quite complicated to build these very nice heterostructures, but you can actually just do this in the lab or even in your living room with your bare hands. All you need is a microscope and a stamp and with a translation stage, and you can just pick up these materials and stack them on top of each other with just a translation stage and a stamp, which is more or less shown here schematically. So here's actually a picture of a full device. So this is a device where I have a semiconductor, and then a contact for the semiconductor is graphene, which is a good contact for 2D semiconductors. And that's the device. And you can see here again a transmission electron microscope picture that really shows you how clean these interfaces are, and that the contacts to the 2D semiconductors also are very clean. And this, what I showed you before, is all done with flakes, but actually this is also now possible in larger area materials. You can grow this with CVD grown, or even on wafer scale. And here's a video from the Jigung Park group, where they just peel off large area of two-dimensional semiconducting materials at the size of a wafer. This is only 1 atom thick. You can also stack them on top of each other and obtain heterostructures in that way, and also twist these materials. So really, this is we call it a Lego toolbox. So you can play with these building blocks like you do with Lego. You can stack them, you can twist them, and then you can build many kinds of devices that have all kinds of properties, such as light emitters, photodetectors, tunneling diodes, optical modulators, and of course also transistors or neuromorphic circuits. If you want to know more about all the applications, I encourage you to have a look at this paper that was published in 2019 in Nature, which is a review of all the 2D materials that can be applied for our well-known silicon technologies. That we of course all know silicon technologies is in all of our smartphones and computer chips. But here the idea is now that we take silicon as a existing platform that of course is very high performance. You can make very complex circuits, but the functionality is actually limited. And here the two-dimensional materials really can add functionality to the silicon. And the beauty is you can put those two just together. So you can actually put two-dimensional materials inside your silicon circuits or put them on top. And then you can add functionality, like I mentioned, photodetectors, cameras, but also sensors and memory devices, etc. And here you see actually a roadmap that's found in this paper. And in the short term, I think we're going to see more applications for sensors and photodetectors. And then the longer term, more related to computing applications such as transistors and neuromorphic circuitry. So I'm going to focus in this talk more on the shorter term applications that are related to optoelectronics or modulators that have applications in these kind of areas. This is a graph that shows wavelength and speed. And so at lower speeds, you can think of all kinds of applications in medical imaging and food inspection and gas sensing. And then for the higher speed applications, you can use graphene photodetectors for LiDAR or for silicon photonics for ultra-fast communications, or even free space communications just in the air, or at a smaller scale, chip-to-chip communications. So the type of photodetectors that I like to highlight here, they cover the whole wavelength range. So not just visible light, where our silicon cameras work really well, but also infrared light and terahertz light. And all of these wavelength ranges have delivered graphene-based or two-dimensional material-based photodetectors with very good performance. So let me start here with visible and shortwave infrared light. That's a wavelength between 500 and 2000 nanometers. That is based actually on a hybrid system where we put a semiconductor on top of graphene. This can be two-dimensional semiconductor, can also be a bulk semiconductor. In our case, we also like quantum dot technologies, which are quantum nanoparticles, particles that are 10 to 50 nanometers in size. You put them on top of graphene. And what happens is that the semiconductor absorbs the light that you can see here in this picture. And then there is an interface with the graphene. Usually there is an electric field. And as you can see here, the holes will follow the electric field in this direction. They go into the graphene and the electrons go away. So effectively, the light is now actually doping the graphene with holes, and that gives a rise to the changing conductivity. And that's what can be measured. So this is like a photoconductive device. And it's amazing, the sensitivity is huge. It can lead to millions of amps per watt. It can also respond to reasonable time scale, millisecond time scale, which is not good for data communication, but it's good for imaging applications, for example. And the system has a gain, a photo gain that is shown over here, that is around 1 million. Now, this is already from a few years ago, but a lot of progress has been made since then, which is to really integrate this photodetection technology with silicon. And actually what we have done is to take an image sensor very similar to what you have in your smartphone. This image sensor has millions of transistors that amplify the signal from all the photodetectors on top. But we basically removed the silicon photodetectors and we replaced them with graphene photodetectors. And we put hundreds of thousands of photodetectors on one of these chips. And each of the photodetectors has a connection to the silicon circuitry such that you can really make an imaging system. And the advantage here is that you can now make an imaging system that works for a much wider wavelength range than the normal cameras in your smartphone. And so we have done that. So here you can see the chip, and you can see also some objects that were imaged with a camera. But what is important here is that we also had a scenario where there was an object behind fog, and usually an iPhone camera is not able to see through the fog. But if you take a photo with our camera, you can actually see through the fog and see the object behind it. And that is because this camera works also for infrared light, and infrared light goes very well through the fog. And so this is very interesting because that means that this type of camera can be used in automotive, right? And actually this has inspired us to work with clients on this topic. And here's a company, Veoneer, that delivers cameras to big automotive companies like BMW and Volkswagen. And we have created a spin-off company that is building these cameras for self-driving cars that hopefully then will also work in bad weather conditions, like fog I mentioned, but also when it's rainy weather, and even when it's very dark, because infrared light is also available in the darkness. Now, I want to move now from shortwave infrared detectors to mid-infrared detectors. Mid-infrared range is what we know very well, where the thermal imaging it shows you these thermal imaging images. I have some pictures here, but also the other applications in gas sensing or in medical imaging. The issue with current mid-infrared imaging systems is that they are quite power hungry, especially the good ones, because they need cooling, and also the wavelength, the resolution is limited. And we can overcome all of that with graphene and two-dimensional materials, because we can again here make a really CMOS integrated system. So we can integrate it with silicon. Now, the mechanism for mid-infrared detection is actually a bit different. It's based on the photothermoelectric effect. And maybe some of you remember the thermoelectric effect. So the thermoelectric effect is basically the effect where you have a difference in temperature between two materials, and that generates a photovoltage. Now in graphene, we actually don't need two materials. All we need to do with graphene is just take graphene that has doping, difference in doping in two different regions. And we can do that, for example, just by applying a voltage between graphene and a gate. And when we have different doping in different regions, it also has different seebeck coefficients. And then if we heat up the system, it generates a photovoltage. So basically the process is that light is absorbed in graphene, then electrons get heated up by this light, and that generates then a photothermoelectric effect that generates a current or a voltage. Now this works really well for any wavelength. So you can do this with visible light, infrared light, and also terahertz light. But the thing is, there's always a junction here where the photo signal is strongest. And that's at the interface of these two regions with different dopings. So what you actually need to do now is actually guide the light to that junction. Because if I usually have infrared light as a large wavelength, so there's illumination everywhere, that doesn't work well. So what we have done here is that actually we combined this system with an antenna for infrared light. And this antenna channels now the light into a very small region. And here you can see actually the electric field from this antenna. And that's exactly that's exactly where the PN junction also is. So the junction for the photo detection. So we really have here a system where the light is concentrated and enhanced in this gap of the antenna. And then the graphene here provides the conversion between light and electric field. So this works for infrared. It works also quite fast. We are comparing here with commercial MCT detectors that have a time scale of nanoseconds, and we find similar types of speeds. So it's fast, it's sensitive, and we're also now building an imaging system to make basically a camera. I'll skip this benchmarking table. I just wanted to mention that the same trick you can apply to terahertz. You can you make the antenna of different size. That's a resonant for terahertz frequencies. Here we can see the imaging of a terahertz beam, where you can actually see the area pattern of this terahertz beam, and that shows you that terahertz detector is quite good. It's also fast. It's really fast, actually. It's actually picosecond time scale. And so this is very interesting because terahertz has many applications in imaging, but also it has many applications in data communications. And so for free space data communications, this is the fastest terrace detector you can find in the world and can be used for ultra-fast data rates. I wanted to mention that all of these detector technology can also be put on flexible substrates. And here's an example of a flexible photodetector where we put it on top of the skin and it's actually able to measure all kinds of health markers, such as the heart rate and the oxygen concentration in the blood. I can explain later in the question and answer session how that actually works. If you're interested, but also it can measure UV exposure that is relevant, for example, for skin safety. But also these type of photodetectors you can now actually put everywhere you want. You can kind of hide them. So one of the interesting applications, actually, you put photodetectors on your glasses. And so why do you want to do that? Well, we know that in the future, augmented reality is going to be a big deal. We know this still from the Google glasses. And eye tracking is an important application there. And now you can actually, with these graphene photodetectors, you can put them on the glasses. You don't even see them, but they are actually able to detect your eye and also the motion of your eye. That in that way, you can do eye tracking and measuring the motion of the pupil. And here actually is an example of an image sensor that's based on a photodetector array that is flexible and transparent. And here you see a video of this image sensor of a moving checkerboard pattern. You can also do some testing with a moving eye pupil, and these images shows that it's actually able to move to measure the movement of this pupil. And then finally, there's also a lot of activities in graphene for on-chip photonics for 5G and 6G data communications by making modulators and detectors. Speeds of more than 50 or even 100 gigabit per second have already been demonstrated. And this is all a system that is fully compatible with silicon photonics and it can be integrated in a very cheap fashion. And the thing I wanted to highlight here is just some new work where we developed a modulator that is based on graphene, because the graphene allows you to change the absorption just by a voltage. So this is actually an optical waveguide with 2 layers of graphene on top. And when we apply a voltage between these graphene layers, you can modulate the transmission of the light through this waveguide. Because the electrical control of the optical absorption of graphene is so efficient. And so here you can see some of these devices, which are basically just waveguides. Here you can see the waveguides that then have transferred on top these graphene layers. And here you can see the measurement of the transmission of light through the waveguide as a function of voltage. That shows you that you have a very efficient modulation of this transmission. And also, if you measure this as a function of speed, you can see that even up to 80 gigahertz, there's not even a drop of the signal. So actually, the speed of the device is faster than 80 gigahertz. But we don't have the exact measurements. We need higher speed setups in order to quantify this. I think my time is up. I wanted to say some things about integration and large-scale production, but I will just leave you with these pictures. I wanted just to advertise that in the graphene flagship program in Europe, there is actually now development of a pilot foundry where a large-scale production of graphene devices and two-dimensional material devices is already in progress and should be available by 2023, such that all the spin-off companies or larger companies can really bring these devices and applications to the market. And I think my time is up, right, Chairman? Is that correct?
Okay, thank you very much, Frank, for your nice speech, for your nice talk. There was some issues with the Professor Andrew Forbes. I will continue the session. I thank again for your very nice speech. Is there any question? I don't see some question here in chat box. Somebody has question. We have time for a very short question. No. So there is no question. I want to thank again Frank for your coming, for your accepting the our invitation. I would like to go to other session.
Thank you very much, Zafia, for organizing this very nice conference. I enjoyed it.
Thank you very much. On behalf of the chair of the conference, Professor Süleyman Özçelik, also all of the organizing and scientific committee, I thank you.
Okay, thank you very much.
Thank you, and bye-bye. So, the next speaker, next invited speaker is Professor Benedetta Marmiroli from Graz University of Technologies, Austria. Hello, Benedetta.
Hello.
Oh, I have your voice clearly, and also the video is okay. Can you share the PowerPoint slides? Okay.
Can you
in
see?
this time, I
try again.
And in that time, I'm going to give you some information about the Dr. Benedetta Marmiroli. Benedetta Marmiroli got her master in material science at the Graz University and her PhD in industrial engineering at University of Ferrara, Italy in 2002. She currently is senior scientist for the Institute of Inorganic Chemistry, Graz University of Technology, Austria. She works at the Austrian Sachs beamline Outstein of the University of Eletta Synchrone Trieste Synchrone radiation source in Italy. She has also very good papers in different journals. We are working together, start working together also. Just I want to ask you, the stage is in yourself, and you can start your speech.
Okay, thank you very much for the kind introduction, and I thank the organizers for inviting me to this really cool conference. I'm here to present our activity in interdisciplinary research, and particularly by combining two synchrotron radiation techniques, small angle X-ray scattering and deep X-ray lithography. In fact, I am part of Austrian group of the Graz University of Technology, but we are an outstation in Trieste in Italy, where there is a synchrotron and where we have the Austrian small angle X-ray scattering beamline, and we also help Elettra in managing in the deep X-ray lithography beamline. And here comes the interdisciplinarity. I found this nice definition of interdisciplinarity on vocabulary. Interdisciplinarity like the synthesis of two or more disciplines, establishing a new level of discourse and integration of knowledge. This means that if we put together more than two disciplines, we have a result that is bigger than the sum of them. And we can really reach new kind of science. In particular, micro nanotechnology has led to merging the previously different separate fields like biology, chemistry, and material science. In particular, we have started the miniaturization of chemical and biological assays by micro nanofluidics. And this requires the development of new materials with tailored properties and a correct selection of the fabrication methods. And this, in turn, lead leads to the need for combination of microfabrication and characterization techniques. So in this talk, I will present two techniques, small angle X-ray scattering for characterization and deep X-ray lithography for microfabrication, and what can they do each for the other. In particular, deep X-ray lithography can overcome time resolution and sample environment limitations in small angle X-ray scattering by making new kind of micro devices. And on the contrary, small angle X-ray scattering can help to determine the structural morphology of the microstructure for the adjustment of their morphology for the specific applications, or you can determine the effect of irradiation of novel functional materials. But let's describe in short the techniques. The small angle X-ray scattering is a very famous technique. You just impinge a monochromatic X-ray beam. We mainly use 8 kV X-rays on the sample. The sample scatters the photons that are collected at a detector. At the end, if we integrate over the detector area, we have a curve of intensity versus the angles that can be correlated to the dimension characteristic of our sample. If we use Bragg's law, then we can find out that at small angle, we can probe large objects. And which large objects we mean structures of 100 nanometers, so they are not really so large. But for example, we can find the dimension and the size distribution of nanoparticles, of pores in porous materials, or we can determine the shape and the dimension of proteins and so on. While with large angle, we can probe a smaller dimension in the order of Armstrongs, and so we can determine the crystalline structure of our material. We can work both in transmission, but also we can work in grazing incidence like here. So you impinge on the surface and you can study the properties of surfaces, which is also very useful for example, for semiconductors or mesoporous materials, as we will see later. So this is a small angle X-ray scattering beamline at Electra synchrotron. So the sample is here, the X-rays arrive from here, then they are scattered in a vacuum tube and collected at the detector. You usually have a detector at SAC, small angle X-ray scattering, and here another detector for wide angle X-ray scattering. Deep X-ray lithography, on the contrary, is a less common technique, so I will spend some more minutes on it. There are some materials that are sensitive to X-rays. This means that when they are hit by X-rays, their molecular chains break, or when they are hit by X-rays, their molecular chains cross-link. And so, if the molecular chains break, they become soluble in a solvent called developer. If the molecules cross-link, they become insoluble in the solvent called developer. So if we are able to put an X-ray mask containing the pattern that we want to transfer between the synchrotron radiation and our material, we are able to transfer the pattern from the mask to the material with very high precision. And with very high precision, I mean that on a thickness of 100 microns, we can obtain a lateral resolution of 200 nanometers. Moreover, we are limited only by the diffraction of X-rays, so we can have very straight sidewalls after the development. And we can also, as X-rays are quite penetrating, we can have micro object of 2-3 millimeters height. And so we can obtain a high aspect ratio, where the aspect ratio is the ratio between the height and the minimal lateral resolution of the material. After the development, we usually also have a very low roughness of the sidewalls. They have optical quality, that is with a roughness less than 30 nanometer. And we have freedom of materials. Okay, the main material sensitive to X-rays are plastics. But if we are able to put the plastic on a conductive substrate, then after lithography and development, we can grow metal inside the holes of the structure. And then we can get rid of the plastic, and we have a metal object that can be used as a mold or as an electrode. So with one single irradiation, we can have many pieces. So this is a scheme of the beamline and of the X-ray scanner. The beamline is just a vacuum tube with a set of filters which are thin layers of materials. And we usually use a white beam that is all energy of the X-rays. And so we use this filter chamber to tune a little bit the shape of the beam. So you can see here, we put the mask. Here we put the sample order, we close them together, and we move them up and down in front of the beam until we reach the desired dose. So what can we do with deep X-ray lithography? Mainly two things. The first is the traditional fabrication of micro devices for which the technique was invented. And the second one is a sort of new application that is irradiation of novel material to exploit their particular properties using X-rays. And so we can have desired functionalities of the material in desired areas of the devices. For traditional microfabrication, as we are in an optics conference, I decided to show what we can do in the field of optics. That means we can do pinholes. These are metal pinholes with, it's not very clear to see, with holes of 100 micron diameter in 1 millimeter slides. And they were made for the previous European synchrotron radiation facility. And this is done by irradiation and growth of metal. Then we can do direct irradiation of plastic to make X-ray focusing lenses. Then we did some pyramid wave front sensor for adaptive optics for a telescope. In this case, we fabricated the mold. And then we, with one single mold, after lithography and electrodeposition, we are able to obtain many pieces. And then we were able to fabricate sharp glazed gratings for an anti-reflective coating. Here we fabricated with the X-ray lithography the mold to make these anti-reflective coatings. But let's go back to our combination of small angle X-ray scattering and deep X-ray lithography. First, what we can do with lithography for SACs. We fabricated a micro device, a free jet micro mixer to study fast chemical and biological reaction. And with fast, I really mean very fast, with sub-millisecond and sub-100 microsecond chemical and biological reaction. There are some reactions that are so fast, for example, the nucleation and growth of nanoparticles, like calcium carbonate, or fast mesoporous material formation, like mesoporous zirconia, or the interaction of proteins with silica nanoparticles, like lysosine. So what we wanted to do is to be able to mix our material in the micro device in very, very fast time. So we chose to use the hydrodynamic focusing principle. We put reactant A in the middle, reactant B in the side, and A is squeezed by B in a very thin stream. And as we are in the microfluidic regime, the mixing occurs only by diffusion, and the diffusion can be predicted. So we complete our mixing inside the device, and then we spit out a jet, and we investigate at increasing time and increasing distance from the nozzle. That is equivalent to increasing time from the beginning of the mixing. This is the tubular reactor concept. So in the same position along the jet, the reaction is always in the same condition. So we can also have a very slow detector that we measure if in the same point we have always the same time condition. But for this, we have to design the device. And in this, we used finite element analysis, and we found out that, that there is a very complex geometry at the cross section in order to avoid the recirculation and the formation of unwanted nanoparticles inside the cross. And we have a nozzle which is very small, and also the channel to have a very fast mixing must be thin. So we have 8 micron nozzle, 6 micron at the cross section, and 12 micron at the center of the mixer. And they are very small. And to have enough material to be detected by our SACS beamline, we have to have deep channels. That's why we were using deep X-ray lithography to do the micro channels. And these are them. So you can see the sharp walls and the very precise geometry of the cross section. We just tested the hydrodynamic focusing with fluorescing in the middle and water in the side. We characterized optically the jet, and we found a system to align the microjet, which is 25 microns wide, with the X-ray beam, which was also 100 microns wide. So it was quite a nightmare. First, we investigated the liquid jet itself, just water. And we found out that the jet itself has a signal. Why? Because there is the jet breakup. So from there is the formation of droplet. And we could detect it with the calculation of the invariant, which is proportional to the electron density contrast and to the volume fraction of our nanoparticles. We also found out that the jet has a constant signal. So after a while, after this is the breakup, and then yet it has a constant signal. So we can use it as a background in subsequent measurement of the reaction. And then we made a reaction. This is this one, the reaction of formation of calcium carbonate, which is really very fast, but we were able to detect the points. This is the intensity versus Q curve. And you can see that we were able to detect the evolution of the reaction. Here there is the invariant growing. And the first accessible point was 75 microseconds, which was the fastest to our knowledge for this kind of nanoparticle measurement. So we really were able to overcome some limit, time resolution limit of the Sachs beamline. We can also fabricate micro reactors and micro wells for the precise positioning of elements. In this case, we were doing it for metal organic frameworks that are on the forefront of technology now, because they are crystalline compounds made of metal ions acting as joints and organic linkers as structs. So we have very, very porous crystals. And so they have interconnected cavities, narrow pore size distribution, the high surface area, low density, and you can adapt the surface chemistry and their pore size. So they are perfect for separation, storage, delivery, catalysis, and sensing. The problem is to position them where we want to have them to make micro devices. In this case, there were this activity was done in collaboration with users, which are experts in material science, and they were able to produce these alpha hopeite microparticles that are the seeds for the MOF. We provided this array with this array of wells made of SU8, which is very chemically resistant, and we were able to grow the metal organic frameworks in precise areas inside these micro wells. And here there is the wide angle scattering pattern of these MOFs to determine their structure that was exactly the same that the freely grown metal organic frameworks. So also in this case, we were able to overcome the limits. Then what happens if Sachs is used for lithography? We can study the properties of materials that have been irradiated with X-rays. Also, this is always in collaboration with users which are experts in material science and come at the beamlines. First of all, we found out that we are able to pattern mesoporous materials. Mesoporous materials are materials which have interconnected porosities of 550 nanometers, depending on the chemical composition. They are usually prepared by sol gel, putting a surfactant inside an inorganic precursor. So the surfactant is arranging the inorganic precursor around them. And so we can obtain, after usually thermal treatment, our porous structure, because with the heating, we can remove the surfactant and cross-link the inorganic solvent, the inorganic template. what we found out that we don't need temperature to do this. We just need X-ray radiation. So with X-rays, we can destroy the surfactant and cross-link the inorganic template. And then we irradiate and we put in a solvent and we remove the surfactant. And we found out by G-SAX measurement, grazing incidence SAX, using SAX on the surface of our material, that we have an ordered structure after irradiation also. And so the pores are arranged in our case, in this silica, in an hexagonal structure. And these are used. This is important because with X-ray lithography, you can make micro patterns of mesoporous materials. So, for example, we can have microdots of mesopores, and in the microdots we can put biological elements. For example, we can put we made a test by putting some fluorescein in microdots of mesopores, and the fluorescein was staying there. So we can really manipulate small quantities of biological elements. We used the small angle X-ray scattering to determine which was the best irradiation dose. And we can do this because we increase the irradiation dose and we measure the structure that we obtain. So the best dose is the one for which we have this hexagonal structure and which is the less irradiation dose that we give. And we were finding the optimal irradiation dose because that is this one, because after this one, the structure stays constant. And then we are trying to move on and use these mesoporous materials to feed water to biological elements put on them. This is our current study now. We are working on this in the humidity chamber at the Austrian Sachs beamline. And I can also say you in advance that it is working, that we can use mesoporous materials to deliver fluid to the biological elements upon them. But then we can also go on playing. So if we, in these mesoporous materials, in the sol gel with the precursor and the template, we put the precursor of nanoparticles with one single irradiation, we can remove the template, destroy the template, cross-link the inorganic part, and grow metal nanoparticles inside the pores and on the surface. In this case, this is an example by using gold nanoparticles, and we were able to pattern them. We were studying with the grazing incidence small angle X-ray scattering the dimension of the nanoparticles. And this can be very useful, for example, for catalysis. In this case, we have gold, but we did it also with silver. And with silver, we can use it for surface enhanced Raman scattering using this plasmon excitation. And so we can also use for biological studies. Then we are not limited only to metal nanoparticles. We are also able to nucleate, for example, ceria. Ceria, it is a scavenger. So it takes the radicals when instead of giving them to the surrounding environment. So if we put some cells or biological element over ceria and of the mesoporous material where there is cereas, it is protected against, for example, the photodegradation due to the UV component of the light. And we were able to prepare ceria in micropattern areas of the mesoporous materials. We were confirming it by doing wide angle X-ray scattering, and we were studying also the radiation and the resistance of to photodegradation of rhodamine 6G upon UV radiation with and without ceria. And you can see that with ceria, the material is resisting more. So this is a promising material, for example, for biological support. Then we can increase complexity. So we can put in our mesoporous titanium, for example, graphene. So we have an enhanced photocatalytic activity while maintaining the transparency of the titanium. So we can really play with materials. We can go towards nanoporosity. In this case, we were with irradiation tuning the porosity of thermally rearranged materials that have very small pores of the order of the nanometer, so they can be used as a gas sensor and because they have thermal selectivity to gases. In this case, usually the porosity is tuned by temperature. We were tuning it by also irradiation. And what we found is that by increasing the irradiation dose, we were making smaller pores, but bigger gases were passing. So the bigger gases were passing in the smaller pores more easily than in the bigger ones. Why? At the end, we found why, because apart from the dimension of the pore for gas sensing, for gas passing, is important also the connection of the pore. And in our case, by increasing irradiation, the interconnection of the pore was improving, even if the dimension was smaller. But the dimension was big enough to make these big gases pass. And of course, by we always check the structure with a small angle X-ray scattering. Our last achievement, also with user, was the direct pattern of metal organic frameworks using direct irradiation. So we were able to obtain micro patterns of metal organic frameworks. And this is important, for example, if we want to make a gas sensor based on a diffraction derating. We were making a test, making this ethanol vapor pass in this diffraction derating made of metal organic framework. The structure was changing due to the penetration of the gas. So the first order of diffraction and the refraction index were changing. And so we could detect how much gas was entering in the pores. So the possibilities are really, really wide. So the combination of deep X-ray lithography and small angle X-ray scattering are an example of the possibility offered by interdisciplinarity, both in chemistry and in biology. For example, deep X-ray lithography allows creating devices to manipulate chemical and biological assays, and so we can improve SAX measurement and investigate new effects like fast time-resolved measurements and confinement. And on the other hand, SAX determines the structural morphology of the structures of deep X-ray lithography and helps in tailoring novel materials for new kind of application in micro devices. So the future will be to investigate new materials and properties using SAX after X-ray radiation and to create a novel kind of lab-on-chip where these functional materials are posed in precise areas of the micro device. And if you want to come and work with us, you can have free access. So you can just apply for beam time at this website, sericeric.eu. Every 6 months, there is an international panel that evaluates the best proposal, and for making measurements or making irradiation at our beamlines. And the ones that pass the selection of the international committee that can come and do experiment at Elettra with us. I would like to thank all the group of both Austrian SAX beamline and the deep X-ray lithography staff, and thank you for your attention.
Thank you very much, Benedetta, for your nice talk and very nice picture, very glad picture from your group. And any question, please? I don't see any question here. We have 1 minute for question, short question, maybe. There is no question, then if possible, we have in this 1 minute, we can take a group image, group photo if you are ready. So everybody please open your camera, open your video camera, and just know I'm going to take a picture. Okay, Hello, Professor Yakupanoğlu, Professor Martin. Okay, everybody, please. Frank, are you there? Thank you, Miguel, again. And thank you, Christos. Okay. So, are you ready? Our colleague, Meltem and Usa, we are waiting for your taking some photo, if possible. Okay, thank you. So next session, I want to give the stage to Professor Fahrettin Yakupanoğlu. Before starting the talk, I would like to take you some information, a brief introduction about Professor Fahrettin Yakupanoğlu. Professor Fahrettin Yakupanoğlu is a full professor of solid-state physics at Fırat University Elazığ in Turkey. His academic and research interests are in the area of the nanomaterials and nanoelectronics, organic electronics, liquid crystal technology. He has published over 500 papers in highly reputed journals, many patents, and I know I am familiar with his work. He has also a company, make some devices, some very high quality devices in Turkey. Just I want to give the stage to Professor Yakupanoğlu. Can you hear me?
Yes, I hear.
Okay.
Yes, I hear. Yes.
Okay. Please share your screen, PowerPoint slides. Okay.
Yeah.
If you choose the presentation mode, I will be appreciated. Okay.
Now it's okay?
Yes, it's okay, but you can, if you choose the presentation mode or full screen of the slide, it would be appreciated.
Yes, okay. Yes.
So, okay, go on.
Now it's okay, yes?
Yes, yes.
Okay, okay. Okay.
But can you open your camera, Professor Yakupanoğlu? Okay, okay,
Now
your
it's
camera
open.
is on just now. Okay, so.
Yes, on,
Go
yes,
on.
yes,
Thank you.
okay. Okay. Good afternoon. I am Professor Fahrettin Yakupanoğlu from the Fırat University. Today, I will talk about the integrated nanostructure, electrode for photovoltaic device for enhancing photo response. Okay, now I want to why quantum dot is important. Quantum dot, as you know, it is the nanoparticle materials. It can be used in different electronic device, solar cell, photodiode, photodetector, at different electronic device. Okay, what's the necessity of the quantum dot of quantum dot solar cell? Now you know the present source of the energy supply has one problem. The problem is the environmental pollution. Okay, the environmental pollution is bad. Okay, for this we need the eco-friendly new energy. Eco-friendly new energy means the solar energy generation. Solar energy generation now, as you know, the conversion efficiency of the solar cell now is about 20%. Some companies, some people increase the efficiency until the 24%, but the theoretical limit is about 31. Okay, now the current solar cell cannot cover the demand of the energy on Earth. Okay, what's the necessity for the new technology idea? The idea is we can use the nanoparticle integrated for the solar cell. We can improve the efficiency of the solar cell and the other photoresponse device. Okay, now I want to explain you how can the quantum dot increase the efficiency of the solar cell. As you know, now you can see here the bulk. This is the energy level. This energy level. This is energy level of the quantum dot. You can see there is one description of the energy level, because the energy level for the quantum dots. Okay. Also, I want to show you some important quantum materials: one-dimensional, three-dimensional. Three-dimensional, you know, the bulk materials. Two-dimensional is quantum well. One-dimensional war you see here. Also, you can see here that the states is different for the different materials, and we can use the quantum well, quantum wire, quantum dot in different electronic device to increase the photoresponse, also photoresponse and photovoltaic efficiency. Okay, as you know, you can see here when you change the size of the quantum dot is emitted different color. Now you see smaller dot means the higher energy, it means a smaller wavelength. So quantum dots of the same materials with a different size, you can emit light of the different color. You can see here different light. In our study, we need to change the quantum, to change the size, and then to increase the efficiency of the solar cell. Okay. Also, as you know, there are many applications of the quantum dots. For example, the active LED, photovoltaic, and thermoelectric materials application. Okay. How we can increase the conversion efficiency? As you know, the power equal the voltage multiply current. This is important two parameters for the solar cell. If I want to increase the efficiency, there are two options. For example, I can increase the photovoltage, also photocurrent. If I increase it the same time to the photovoltage and the photocurrent, then I can find the high efficiency solar cell. Okay, how I can find the high voltage? Now you can see, I want to explain on the basis of the band diagram, function of the particle for the photovoltaic device, higher photovoltage from the description. Now you can see here, this is the first one, bulk material. When you excite it, this is the hold, move the top of the valence band, this is the conduction band. Then you have one voltage. This, for example, this voltage be V1. Okay, if you excite the quantum dot, now you see electron is moved and then hole is moved, then you have the voltage 2. This means the voltage 2 is higher than the voltage Y. So if I use the quantum dot nanoparticle materials in the solar cell, this means I can get the high efficiency. Also, I want to explain how we can get the higher photocurrent in the quantum dot solar cell. We can explain the Auger effect, the impact ionization. You can see here, one photon yields the 2 electron and hole pair. Then you can see here that you can get the high photo current. Okay, as you know, that there are 3 important components in the current generation solar cell: the electrolyte, synthesizer, and photoanode. If I want to increase the efficiency of the solar cell, of the photovoltaic device, also photoconducting device, also photodetector, I can change the structure of the photoanode. Important materials in the solar cell, because it controls the efficiency of the solar cell. Okay, other thing also, you for any solar cell, the efficiency is very important, also cost important, also size important. But how can we increase the efficiency of the solar cell? They change the structure of the photoanode. And now I want to explain you how can this do. Okay, now you can see here this is the nanostructure integrated solar cell. We use here the quantum dot and titanium oxide. Titanium oxide is capped the titanium oxide. Our idea is to change the size of the quantum dots and then cap with the titanium oxide, and then to increase the efficiency. Okay, as you know, many people know how can this method preparation of the quantum dot. There are many methods. You can use quantum dot, and then you can these materials in different electronic device. Now, okay, you can see here this is the structure of the functional principle of the quantum dot solar cells. You can see here when the excited electron moving from the valence band to conduction band, and then from the conduction band to the titanium oxide, and then go to the electrode. If I increase, okay, if I wait, no, okay. Okay, now my aim to how can I increase the efficiency? Efficiency, for example, you can use the linker assistant absorption mechanism. This means you need the high quantum dioxide controllability, low quantum dot coverage for electron transport property of the linker molecule. Also, you can use the different method, chemical Bach deposition, also Slur method. Slur method, as you know, the successive ionic layer adsorption and reaction. If you use this method, you reach the efficiency is about 4.2%. Also, quantum size is uncontrollable in that method. Also the complex fabrication procedure. Also, there are another method is in the hydrothermal method. This method, the advantage, facilitate one-step synthesis, narrow quantum size distribution, and then high coverage, and then you can reach them efficiency up to 3.1%. Okay. Now you can see here the method of the preparation of the quantum dot solar cell. As you know, the quantum dot synthesized solar cell, you need the titanium oxide. Also, titanium oxide is the photoanode. Also, you need some quantum dots. Also, you need some linker or aim to change them nanostructure of the titanium oxide. Also, cover the with the quantum dots. Now you can see here we prepare the quantum dots. When we prepare the quantum dots, just we change the temperature. We change the temperature, reaction temperature. Then you see the color is changed. This means this quantum dot has the different size. Now you can see here. Okay. Also, our aim to cover the quantum dots to the titanium oxide, then titanium oxide to increase the efficiency. Okay, now you can see here we change the reaction. We change the reaction temperature. The first one, the 60 centigrade degree, 100, 140, 160 centigrade degree. Now you can see here the structure on the 140 centigrade degree cubic CD SE, also between the 100 and the 160 centigrade degree. The structure is cubic CD, SE, CD. Also, more than if the reaction temperature is higher 160 centigrade degree, the structure is hexagonal structure. Okay, now you can see here. You can see here when we increase the the reaction temperature, the size is increases. You see the for the 60 centigrade degree 2.1 100 2.4 like this. Yes. Okay. Now we can control the quantum dot size with the reaction temperature. Okay. Okay. Also we change the reaction time. Reaction time, you see 1 hour, 3 hours, 6 hour, 8 hour, 12 hour. Then we check that the size for the 1 hour 2.5 nanometer, 3 and 6, 9 and 12 hour. Now you see we change the size of the quantum dots. Okay, the reaction here, the reaction at the 140 and the 160 for over the 3 hour will obtain the, you see, CDS core shell quantum dots. Okay, also I want to show you TEM image and atomic force microscopy image. Now you can see here the quantum dot homogeneously covered on the surface of the titanium oxide. Okay. Okay, now we get the PL spectra. PL spectra give this result. You can see here the most of the excited electron in the quantum dot can be injected to titanium oxide. Then we have the recombinant non-radiated emission, non-radiated emission. Okay. Also, we use the some molecular linker to increase the efficiency. The linker links to quantum dot to titanium oxide. Also, here we use the source in the sulfur source CDS. The component is CDS. Now you can see here we linker the CDS and the CDE to the titanium oxide to increase the efficiency. Okay, then we get the absorption spectra. Absorption spectra you can see here 60 centigrade degree, 100, 140, 160, 180. Okay, then we prepare the solar cell. You can see here that is the solar cell current voltage curves. You see when the reaction temperature increases, efficiency also increases, but until 160 centigrade degree. Then after this temperature, the efficiency is, you see, the decreases. Now you can see in this table the solar cell give them high efficiency for the reaction temperature 160 centigrade degree. Now you can see here the absorption is shifted. This the absorption each is shifted to higher the wavelength. Now you can see here. Okay, this means that the size is control the efficiency. The size is control the efficiency. When the size of the quantum efficiency increases, you can see here the efficiency of the solar cell is increases. Also, I want to show you also we treatment zinc as treatment. We prepare trade for the different annual time. You can see here the second. Okay, here 300 second for the 450 second. Now you can see here the structure is changed. If structure is changed, but the quantum size is about 4 nanometer and 4 nanometer for 452nd, we have the hexagonal structure, the quantum size about between the 6 and 7. Okay, now you can see here the result. Okay, this transition as the composition amorphous zinc sulfur to crystalline after the 300-second and really an important role in the efficiency. You can see here for the 300-second, we get the the efficiency is reached. The 31%. Okay, the over long annealing leads to high absorption of the light, but destroyed core shell structure. This is very important. If you want, when you want to increase the efficiency, also you keep them core shell structure. If the core shell structure is destroyed, then solar cell the current and voltage decreases. This is very important. Firstly, we should increase the high absorption to control the wavelength range. Also, this means the size of the quantum dots. If you destroy the core shell, then the solar cell resulting in the low current. This is very important. Okay. Conclusionally, I want to some advantage of the quantum dot solar cell. Quantum dot solar cell, as you know, you can prepare the one-step synthesize, also high quantum size controllability, high light conversion efficiency. Also for this, if you want to integrated nanostructure material, just you don't need to use only quantum dots. You can use the different nanostructure materials. This means that you can link with the titanium oxide. Also, you can cover the titanium oxide. Also, you can change them. Also, you can change the structure. You can change the structure of the titanium oxide. For example, titanium oxide. Then for example, you can synthesize titanium oxide in the nanorods, in the nanowire, different nanostructure. The nanostructure is very important and is very important parameters to control the efficiency of the solar cell. It is not only solar cell. You can nanostructure of the metal oxide materials is very important also for the different electronic device. For example, photodiode, photodetector. So you can use them different nanostructure. This means now I am saying you can integrating quantum dot solar cell different nanostructure materials. These nanomaterials may be to 0-dimensional, 1-dimensional, and 2-dimensional nanomaterials. Then you can change them. You can change them size. You can change the size. Today I explained how can we change the size of the quantum dot using them. For example, the solar method, also the hydrothermal method. As you know, the solar method you can change the reaction times and reaction temperature. If you change them, if you change the reaction times, in that case you can grow the size of the nanoparticle. In the hydrothermal is based. You can hydrothermal. You can experimental condition, pressure. You can change the pressure. You can change the volume of the solution. Also, number of the molecular numbers you can change. Also the reaction times. Also reaction temperature and the heating rate. These parameters are very important component to control the size of the nanomaterials. As you know, the hydrothermal method, you can synthesize your any materials in one step, just one step. You can directly get the materials. Then you can improve the electrical and optical parameters. For example, after the synthesize of the materials in the hydrothermal method. In the hydrothermal method, you also make the analyze your sample in the different temperature. For example, if you synthesize zinc oxide, for example, zinc oxide, the titanium oxide in CDO, the different metal oxide. Just you analyze the start from the 300 centigrade region, 300 up to the for example 600 700 centigrade degree. The also annealing temperature also, it is very important parameters to control the structure of the metal oxide materials. Okay, also for example, when you fabricated the quantum dot synthesized solar cell, you just use the photoanode as a one-dimensional titanium structure, two-dimensional. Also, you can change the counter electrode with the high catalytic. Then you can increase the efficiency. The another thing, if you want increase the efficiency of the quantum dot solar cell, also you can titanium oxide, as you know, it is photoanode materials for the dye synthesized solar cell. Then you can core shell structure with the titanium oxide. For the core shell structure, you can use different quantum dots. Also, you can change the size. You can change the size of the quantum dots. Then you can the reaction temperature. It is very important. Also reaction time. Reaction temperature, reaction time, it is very important to control the quantum size. When you change the quantum size, as you know that the quantum dot emitted a different wavelength. The smaller one means the high energy, and then this means the smaller wavelength. Then you can, if you prepare, for example, now you want to use solar spectra, solar irradiation spectrum, all spectrum. As you know, the all spectrum started from the 350 to we accepted until to 1100 nanometer. If you want to use them, or between the 350 and 1000 nanometer, all wavelength. For this unit, you can prepare the different size quantum dots. The different size quantum dot means the different wavelength. If you prepare one structure of the solar cell, solar cell quantum dot solar cell. For example, some quantum dot absorptive 400, and then another one 500, 600, 700, like this. Then you can emit it all solar irradiation. Then you can find the high efficiency solar cell. Okay. Consequently, I say if you want to find the high efficiency, also high photo response device, you change the nanostructure of the quantum dots, and quantum dot, this is enough for this application. Okay. Thank you.
Okay, thank you very much, Professor Fahrettin Yakupanoğlu. Professor Süleyman Özçelik here wants to tell something. If please, Professor Süleyman Özçelik.
Professor Fahrettin, thank you very much for warm and good presentation. And also thank you for valuable contribution to our conference. I hope see you face to face in near future.
Okay, thank you.
Or another event.
Okay,
thank you. Thank you. I would like to say just Professor Süleyman Özçelik. Here we have Professor Miguel Alonso, also Professor Benedetta Marmiroli, Frank, and also Professor Oliver Martin. Professor Süleyman Özçelik is the chair of the conference and also is the director of the Photonics Research Center at Gazi University. On behalf of him, just a question, Professor Fahrettin Yakupanoğlu, we don't have any time. Then I would like to ask some, in chat box also, we don't have any question. I would like to ask a very short question. You mentioned two methods, hydrothermal method and scalar method for preparation of quantum dots.
Yes.
And controlling the size of the particle. In the case of scalar method, you said we have some parameters that look like reaction time and reaction material you can choose. But maybe the selection of the numbers of cycles is more important to control the size of the particles, and also some other chemical parameters look like pH and others. We can control the size and composition. Yes, is it true?
Yes, yes, you are right. Yes, you are right. Yes.
Okay.
Okay.
So just now we will take a short break after closing this presentation. And after 10 minutes, we will give the stage to Professor Fahrettin Yakupanoğlu for the chairing the next session. We will waiting for you for the next session with Professor Fahrettin Yakupanoğlu. Thank you very much and goodbye for a short time.
Okay, thank you. Okay, bye.
So, how was Turkey?
So Turkey was... Wow. Yes.
No.
Okay. Okay. And hi, everybody. Now I want to open the new session. The first speaker, Professor Oliver Martin from the Nanophotonics and Metrology Laboratory, Switzerland. Professor has the I am checking how many paper. I think he has the high check index. He has many article in the international reputation journal. Okay. Now, Professor. Okay, we can start.
Thank you very much. I think the most important to say about me is that I'm really delighted to have this opportunity to be with you today. So thank you ever so much for inviting me. and giving me the opportunity to share our work on plasmonic and dielectric metasurfaces. And since plasmonic is the topic of the talk, maybe some of you are not familiar about this field. I mean, I see there is a fantastic diversity in this conference, which really makes it very interesting. So let me start by giving you a very brief introduction on plasmonics. And probably the simplest way to understand plasmonics is to look at the light scattered by a very small particle. So say we have a small particle, it will be described by a permittivity. And of course, what's very important is that this permittivity is dispersive. So it's going to change with the wavelength lambda. This small particle, when we illuminate it with incident light, is going to scatter light, and there will be, to describe the amount of scattered light, which is given by this equation, that's the sole equation there will be in the entire presentation, I can assure you. There are two terms. The first term here depends on the radius of the particle. Of course, a big particle is going to scatter a lot of light. And it's not just the radius, but it's the ratio of the radius divided by the wavelength. So if the wavelength becomes very small, this term becomes very large. And actually, this term is responsible for our beautiful blue skies we've just seen in the coffee break, the amazing skies that you have in Turkey. So the sky there is blue because you look at the scattered light, and blue is the shortest wavelength our eye can perceive, and therefore you have nice blue skies. In plasmonic, actually, we work with the second term here, which only depends on the material. It depends on the permittivity. Again, if I want to make this term large, what I can do is make here the denominator very small, so I can make this go to 0. And making this go to 0 can happen if the permittivity epsilon becomes negative, and especially if it is -2, then this is going to be 0, and I'll have a lot of scattered light. So this condition of having a negative permittivity occurs in metals. You have here experimental data for silver. You see in red the real part of the permittivity, and you see that the condition epsilon -2 will be met at a very specific wavelength. And at this wavelength, this term goes to 0, and there is a huge amount of light that's scattered from the particle. Now, the peak, of course, is not infinitely small, because in a metal, not only do we have the real part of the permittivity, but there is always an imaginary part. And this imaginary part is responsible for the losses, which make this resonance sometimes quite broad. But what's important to keep in mind is that we have here the excitation of this resonance. We call this a plasmon resonance because the metal, and I'll come to that in the next slide, has a lot of free electrons. And this is like a plasma, if you want, not a gas plasma, but a solid state plasma with all the nuclei at the background and these free electrons. And this occurs at a specific wavelength, which means that the particle is going to have a specific color. So with this simple theory, we can say basically small silver colloidal particles are going to scatter light, especially strongly in the blue. And if you do the experiment, this is something I did when I was in San Diego quite some times ago. Indeed, you take small silver colloids and you see that they are blue, nice strong signal there. But when we did that experiment with David Smith and Jack Mock, we were also quite surprised because we realized that some particles actually are green, some appear yellow, some even are red. And we could not really reconcile that with this very simple theory. So Jack Mock resorted to electron microscope. He managed to take the same sample under electron microscope and use the magnification of the electron microscope to try to understand why some particles would be blue and other would have other colors. So this one, which is nice blue, turns out to be a nice round particle. But this one, for example, which is green when you look at it under the optical microscope, turns out to be kind of a pentagon nanostructure. And this one, which is red here, actually is triangular. So basically we have different sizes, and for that reason we have different color. And I can hear that some of you will say, well, this is normal, we are used to that. We know that in optics, if you have an object, the size, the shape of the object is going to determine the resonance we can have. But what's very special here is that all these particles, they are much, much smaller than the wavelengths. The wavelength is maybe 500 nanometer. The size here is 50 nanometer. So indeed, we have a resonance effect, but for something which is much, much smaller than the wavelengths. And this is unusual because normally we know that when we want to make a strong resonance, we need to have an object which is about the size of the wavelengths. If you're enjoying, after a good day work, enjoying your bath, and you want to make a big wave in your bath, you're not going to slightly move your hands, but you're going to move forward and backward in the bathtub such that you create a wave which has a wavelength similar to the bathtub. So here this is very different because we have resonances, but for objects that are much, much smaller than the wavelengths. And of course, the reason for that is that what's going to be resonant is in these nanostructures are the free electrons that we have in the metal. So also, if I finish about this very brief introduction, it's important to realize that the response, say, for example, for silver, is very, very different at the nanoscale. You can have all these possible colors in these nanoparticles. Whereas if you take a big bar of silver, it will just appear gray and reflect light very well. So plasmonics is about using these effects in nanostructures, and for that to use the so-called plasmonic metals, which are actually not very numerous. These metals have a quite nice name. They are called coinage metals. So coin comes, of course, from coin. And it's true that these are often the precious metals that are used for making coins. So like gold, silver, aluminium, copper, or tungsten. And all these metals, they share the fact that they have a very high electron density, free electron density, which is in excess of 10 to the 22. The condition we've just seen for silver, which was this resonance, or the condition that epsilon is -2 at a given wavelength, for silver is here in the short part of the spectrum. For other metal, it will be elsewhere. For example, gold, which has often been the metal of choice for plasmonics, will have a resonance in the red or infrared. Aluminium can go all the way to the UV, and copper is a bit in the middle of the spectrum. Actually, at this stage, when we talk about plasmonics, we often say, by the way, our ancestors, they were putting some small gold nanoparticles into the glass paste. And these are the reason for some of the beautiful colors we can see in stained glass windows still today. So if you bear with me, at the very end of the presentation, I will come back to that question, whether indeed this is gold nanoparticles that you find in stained glass windows. But after this brief introduction, I would like to go back to the technology. We had a beautiful presentation about the technology on the beamline in Graz a bit earlier this afternoon. We do mainly clean room technology. And I'd like to say a few words about that because I think it's really important to have access to these facilities if you want to study this field of research. So I'd like to discuss two approaches for fabricating plasmonic, but we could also use other materials, nanostructures. The first one, which is the most common one, is based on a so-called liftoff. So basically, these are techniques where you use the electron beam to fabricate your structure. So you use an electron beam exposure, starting by putting photoresist onto your substrate. You expose the structure you want to fabricate, for example, a small antenna made out of 2 small particles. Once you have developed your photoresist here, you open basically the regions where the E-beam has exposed, and then you evaporate the metal. You evaporate it everywhere. The metal is going to go here on the substrate, also on the top of the photoresist, but you put your sample in acetone, so you dissolve the remaining photoresist, and you are left with only here the nanostructure you wanted. For this process to work well, there is a small trick which is important, which is to use a two-layer photoresist. And you see that when you develop the photoresist, the bottom layer is chosen such that it will open a little bit more than the top layer. And as a consequence, when you deposit the metal, there will be an interruption between the metal on the photoresist and the structure you really want to fabricate. If you don't do that, you risk having here a continuous film. And if you have a continuous film, when you will put that in acetone, it will not detach well, and you will have this type of ill-defined nanostructures. So this is the first approach. Another approach which has not been so much used, and which I really would like to advocate because I think often it is superior, is based on another type of photoresist. This is what we call a negative photoresist. So it's the same principle. We will put our photoresist on our sample, and here the regions that have been exposed, once the photoresist is developed, they will remain on the sample. Previously, we used a so-called positive photoresist. The regions that are exposed by the E-beam, they disappear. They open these cavities where we'll deposit the metal. Here, they will remain, and they will protect the material that we have deposited first. So for example, we start by depositing gold, then the photoresist, we expose it, and the photoresist, once developed, stays as a mask, and we bombard the entire structure with ions. So because gold is very soft and the photoresist is very hard, the photoresist is not going to be very much damaged, but around where it's not protected by the photoresist, there it's just going to disappear, and we're going to define our structures like that. So two different approaches, two different types of photoresist. Now, what's the outcome of that? We have here compared the same geometries with the two techniques. And you see that this technique based on ion beam etching or ion beam milling is actually superior for defining very, very small features. Like here, we can make a small gap between the two parts of the antenna, the two gold structures, which is about 10 nanometer in size. Also, we see the structure is very well defined here with liftoff. The structure is not so well defined because when the gold is deposited here, gold can be very mobile on the surface and it will diffuse a bit sideways. And so this structure done by liftoff is less precise as the one done by etching. This is also true for a more complicated structure like an heptamer, so 7 particles, which can support a phonoresonance. With etching, it's very well defined. With liftoff, we see that the different shapes are not so regular. And finally, there are things like if you would like to do a spiral, it's something you can do with etching. You can make this spiral with a very tiny gap well defined. But if you try to do that with liftoff, it's not quite possible. So I think this approach is very interesting and hopefully can be used by more people. So this is where we stand. We have a technology, we can make nanostructures, and we have a few metals that we can use: gold, silver, aluminum, copper, tungsten. But that's all what we have to play with. And this is a bit frustrating because it would be interesting to have more metals, especially say we would like to have an optical effect here at another wavelength, which would not work with silver or not work with gold. What can we do to try to create a plasma resonance at that wavelength? So this is a question we've tried to recently answer, which is, can we extend the range of metals that we can use for doing plasmonics? And something that came to our mind was the fact that we could actually make some alloys. Gold, as mentioned, is going to work well in the long wavelength range of the spectrum. Silver will work well in the short wavelength range. But if we mix these two, and if we make an alloy, for example, with half gold, half silver, we see we can have an effect in between. And this is actually a comparison. The solid lines are experiments we have performed, and the dashed line are a model that gives the permittivity of the alloy. So we've tried that, but of course, what we wanted to do is to make alloyed nanostructures. And alloy is always done at high temperature. So we thought, okay, if we want to make some very complicated shape like an antenna and we heat the whole lot, will it work? Will we be able to keep a nice shape? So for example, we want to make small samples that are a bit elongated like that. Then we do the annealing at high temperature. And actually what we end up with are just blurbs. So just structures that are perfectly round. Because of course, the high temperature process required for making the alloy will heat the structure. And once this is done, well, the shape is completely destroyed. So our challenge was actually to try to find an alloying process so we could mix, say, gold and silver, but such that it would work at low temperature. And after many, many trial and errors, actually we found a solution that works very well. The idea is to heat not too much. So we heat only at 300 degrees Celsius, but heat very long. So the alloying process, basically the diffusion of gold and silver together, will take a very long time, like 8 hours. We also notice that at the end of the process, if we give a small boost at slightly higher temperature, it also improves the alloying. What's nice about this approach, I mean, it's very simple and it's very cheap to do that, because we can decide the stoichiometry of our sample just by deciding how much material we put our substrate. If we want to do a gold 80%, silver 20%, we put 80 nanometer of gold, 20 nanometer of silver, we do the alloying and we have the material. If we want to do a gold 20%, silver 80%, we just put 20 nanometer of gold, 80 nanometer of silver, we alloy at low temperature, and this is what we get. So we have a lot of flexibility with that approach. We can make any type of alloy, and it's done at low temperature. So as a consequence, the shape of the particle is very well preserved. Here we have tried, for example, to make small triangles. These are the triangles before alloying. Here you have the structure after the alloying process. This is 20% gold, 80% silver, and you see we can keep the shape very, very well. We can make particles with a high aspect ratio, like several hundred nanometer, with just about 60 nanometer width, and after the alloying, they are very, very well preserved. We can make more complicated structures like these ones that will also support phonoresonance, and again, they are very well preserved during the alloying process. So having developed that technology and also made sure that really we were producing an alloy, you can see here, this is the film before annealing and after annealing. We see obviously that the surface is modified. Unfortunately, we are not metallurgists, so we don't really understand all the detail of what happens. But what we are very sure of is that the two materials are going to mix very well. You see that in EDX, where gold and silver are homogeneously mixed. And you see it also with XPS, where we can etch through the surface. And we see that through the entire sample, in that case, 150 nanometer thick, we have perfect mixture of silver and gold. This sample started with, say, 20, 30 nanometer of gold and 120 nanometer of silver. But in the end, it's perfectly mixed throughout the entire substrate. So what can you do with that? And well, what we have done so far was to try to make metasurfaces. And to do metasurfaces, maybe I should give a few background explanation about what is a metasurface and how it works. I think it's also very interesting because often in optics, we are interested with the strong field that can be produced by a structure. I've just shown you that a small silver nanoparticle will produce this plasmon resonance that has a very strong optical field. But actually there is something else to the amplitude, which is not just the field enhancement associated to the amplitude, but the phase. If I may, maybe I will just stop share my screen and I'll come back to that. And I would like to make a small experiment. It's a very simple experiment. It's just a spring and a mass, you see. Now, if I make this system oscillate, and I oscillate very slowly, when I start oscillating, so my hand goes down, my hand goes up, and the weight is just following. And when the hand goes down, the mass goes down. When the hand goes up, it goes up. And I do that at very low frequency. But if I go at high frequency, what happens, and you barely see my hand moving, but I can tell you that it really feels like that. At high frequency, when my hand goes down, the mass goes up. And when my hand goes up, the mass goes down. And I'll share again my screen. So what's happening here, we have a resonance. And when we go at low frequency, so we are here before the resonance of the spring, the bottom goes in phase with the top. But when we pass this resonance frequency at high frequency, here what's happening is that the top, so the hand goes down, but the bottom goes up. And this is true for a spring, but it's a general thing for any resonance system. So as you go through the resonance, there is a phase change, which means that if we go back to our first particle, for the light scattered by this small particle, when I'm at a low frequency, lower than the plasmon resonance, the scattered light is just in phase with the excitation. When I go at high frequency, so I have passed the resonance of the particle, the scattered field, as you see here, is in opposition, different phase than the excitation. And so I have something now I can use to change the phase of the light. And playing with the phase of the light is very important because you can say, I think, that any optical component works actually with the phase of light. Simple example is the example of a grating. If you have a grating and a plane wave that comes on that grating, what's going to happen is that the wave is going to emerge at another angle, which means that in that point, if I look at the phase front, the emerging phase front is the same. But if I look here, the emerging phase front is different. So I have another phase. You see it has jumped a little bit. And here, where I have the next phase front coming, at this location, there is a phase shift of 2 pi between my incoming light and the light that is transmitted. It's also the case for a lens. A lens works with exactly the same principle. If you like, on one side here, you will have a negative phase shift of minus pi, and here you'll have a positive phase shift of pi, and together they will make the beam converge to that point. And of course, the most general case is that of a hologram. There you manipulate the phase a lot, and you get this type of very complicated phase pattern. So the idea is, can we make an optical element that is going to behave like a grating or like a lens or like a hologram? And instead of having here something on the surface that manipulates the phase, we're just going to put different particles, and each particle is going to produce a different phase. And we will have the same effect on that system. So this is what we have been doing. We have basically, again, developed the technology to put on the same substrate different nanostructures with different stoichiometry, so different composition of gold and silver, such that we were able to produce different phases and make some optical effects. So the way it works from a technology point of view, you start by defining the region where you want to put your first material. You deposit your first material, maybe 20% gold, 80% silver. Then you remove the photoresist, you put again photoresist, you do again e-beam. This is quite tricky because you need to align precisely this new structure with respect to the previous ones. And then you do another metal evaporation. So you can now choose 80% gold, 20% silver. In the end, you remove again the resist and you bake the whole lot. So you do the low temperature annealing. And like that, on the same surface, you have different materials. Therefore, you have different phases for the incoming light. This is the type of sample we fabricated. Nothing very exciting, some small nanostructure, but you must realize that half of these structures are from one stoichiometry and the other half is from another stoichiometry. And they are quite well aligned if you think that they have been done in 2 successive electron beam processes. And if you shine light on that system, this is what you observe. So this works just like a hologram. You can also make something that would work like a lens that would focus the light. You see, it will basically be pretty much diffraction limited, and you will have a nice focus of light. This is through the interaction with this metasurface, which is made out of, again, 2 different materials with 2 different stoichiometry that have been organized here in concentric circles to produce the effect of a focus. So basically give the phase similar to that of a lens to the incoming light. So that was quite a bit of technology for making metasurfaces by combining different materials with different stoichiometry in that case. I'd like to go a little bit into something a bit more maybe physics oriented and talk about magnetism at optical frequency. I think there has been quite a bit of confusion with the development of metamaterials about whether magnetism can indeed exist at optical frequencies. And if you look at the book of Landau and Lifshitz, you will read that actually no, magnetism cannot exist at optical frequencies because light goes too fast and the current loops that you need for making magnetism will not be able to follow. Actually, it turns out that yes, you can do that. You can make a magnetic effect at optical frequency, and I'll explain in the next slide what I mean by a magnetic effect. And you can do that by, again, tailoring the distribution of the electric permittivity on a surface. But, and of course, if you want something that interacts well with light, then you could use a plasmonic material because that will have a very strong interaction. But there is a problem. And the problem is that even though you may create some magnetic effect, they will always be accompanied by some electric effect as well. So let me illustrate what I mean here with this small structure, U-shaped structure. It's also being called a split ring resonator in the metamaterial community. If you look at the response of that structure, we see we have 2 peaks. The scattering cross-section in black has some strong features. So a lot of light is scattered here, a lot of light is scattered here. And we can decompose the response of that system in Cartesian multipoles. So these Cartesian multipoles, if you want, they are basically the same component you use when you do Mie scattering. They are fundamental basis function, if you would like, that you can use to analyze light scattering by a nanostructure. What we observe here is that there is one of such component, which is the electric dipole in blue, which is the major component. If I zoom here, you see most of the scattering cross-section is a contribution from this electric dipole. And what we would like to promote in that case is actually a magnetic dipole. And we see here there is a magnetic response, but it's very, very tiny. So because it's completely dominated by this electric response. So we're looking for a system where we would be able to only have a magnetic mode, so only have a magnetic dipole. Here we also see another mode which has often been confused with a magnetic mode, which is the electric quadrupole, which appears here in that system. So our idea was, can we find a system where we could produce pure magnetic light? And instead of using just a single nanostructure, we have resorted to using a pair of nanostructures. This is the structures as fabricated. They are made out of silver, and they are 80 nanometer long and 40 nanometer wide. Now, the idea of having a pair of structure is that you can have new type of modes. There is a famous model that comes basically from chemistry, but has been translated to plasmonics by Peter Nordlander, which is the idea of hybridization. So if I have a single nanostructure, I will have a resonance like that, where the field oscillates like that. But now if I have a pair of nanostructures, I can have two modes. Either a mode where for both elements, the light oscillate in phase. And this will again be like an electric mode, or a mode where you see that in one element it oscillates like that, and in the other one it oscillates in the other direction. So this starts to look a little bit like a small loop of current. So that could be some kind of a magnetic mode. Of course, if the light comes from the top, then the two elements are always going to be driven in phase, and we will have only this mode. On the other hand, if the light comes, for example, from the right, it will first hit that element, and a bit later it will hit the other element. So this one will have a delay or a retardation with respect to this one. And this can cause this type of modes. So if I look at the illumination of my system coming from the side at a given angle, I can have here these two modes that appear. It will here in the theory or the experiment be manifested by very broad resonance. But if we make an analysis of these different modes, what we observe here at 45-degree incidence is that the scattering cross-section in black can be decomposed into this electric dipole mode in blue, plus here an electric quadrupole in green, and here the magnetic dipole mode, which is the mode I would like to have because I would like to have a pure magnetic response. One can look at this with this type of representation. Of course, these modes, like the dipole resonance, it can be in different direction. Here it's in the direction X. So this is why only this part is marked, but it could be in Y or Z. The magnetic resonance, which we see here, is in Z direction. It means we have a small loop, and then the axis of this loop of current is in Z direction. And the quadrupole is more complicated because the quadrupole is a tensor. So we have a basically 3x3 element. So here we have a little bit of a magnetic response, but it's still very, very limited. So can we make it stronger? And to make it stronger, we need to have a stronger phase difference between the two particles. So one way of doing that is to take particles with different sizes. And if I take a small one and a large one, I start to have a very different response. I start to see actually better here the different modes which occur at different wavelengths. And if I make the analysis of that system at 680, I see that I have almost lost my electric response, and I would see a little bit better my magnetic response here. But what's annoying is that I still have this electric higher order, the electric quadrupole response. We see it again here in this matrix. We start to have a significant magnetic dipole, which appears here in pink, but we still have an electric quadrupole here in green. And the reason for that is that these modes actually are degenerate. And I'd like to explain this here because I think this has been a source of confusion about magnetism at optical frequencies. Actually, here at the same energy, we have these two modes. This one, in which basically we really have a loop of current, which is really a magnetic mode. So this is the magnetic dipole. But we have also this one, which looks almost like a loop, but not quite. You see the field goes in that direction, and then it goes here in the opposite direction. And this is actually the electric quadrupole. And these two modes occur at the same frequency. So we need to find a way of separating them. We can do that by splitting each bar into two. So this first bar is split in two, and the small bar is split in two as well. And if we do that, then we see that the loop of current, so the magnetic mode, is going to be driven by the field either pointing up or pointing down. So that would be a transverse electric field. And this guy is more driven by field pointing to the right or to the left. And that would be a transverse magnetic mode. So by controlling the illumination polarization, now we can decide which mode we have. And if we take the transverse electric mode at this wavelength, at this energy, we can completely suppress the electric dipole. We don't have electric quadrupole either, but we have a very, very strong magnetic mode here. So we have created a system where sorry, I see muted. Was I muted all day? No, is it okay? So we have here the very strong magnetic mode here. And if you do the experiment, you will see that this small loop of current, so this just magnetic mode, is going to radiate in all directions. And this is what you observe if you put this nanostructure into a microscope and look in the Fourier plane, you will see light radiating in all directions. And this is the calculation, this is what you should have, and this is what you get in the experiment. Here we have to block the incident light. This is why there is this small part there. So basically we have succeeded in having something that's just pure magnetic mode and created by plasmonic materials, so has a very strong response. If we change the illumination polarization, then we basically have the electric quadrupolar mode here that will be radiated. So I think this is quite interesting, and what we hope to do is to combine now this type of system with molecule or quantum dots, such that we can then modify the radiation properties. You know that, for example, the selection rules of electronic system will depend on the type of environment they have, whether it's a pure magnetic or electric environment. Let me move to the last part of the talk, where will start by talking a lot about technology. I think technology is really important for enabling these type of studies. And we have seen that plasmonics provides strong electrical response. It turns out that since a couple of years, one has also started to study dielectric system, dielectric resonators. And dielectric resonators, they have actually much more rich collection of modes they can support, like quadrupole and higher order modes that they can easily support. So a question we ask ourselves is, what could we do if we would combine plasmonic material with dielectric resonators? So this is what we have done in that geometry. In order to have a strong dielectric response, you need to have a dielectric with a high permittivity. So as dielectric structure, we have chosen silicon. So we have a silicon cylinder. And as plasmonic resonator, we have used aluminum. And we need to control the coupling between the two. And to do that, we have introduced here a small dielectric spacer made out of glass. So you see the structure are about 400 nanometer in diameter, and the height is also in the order of 300 nanometer with a different material, silicone here, glass, and aluminum on top. We wanted to do some biosensing for that with that, so we made a lot of them on a substrate. You see here a top view and a side view of these structures. Let me again say a few words about how we fabricate them, because that's interesting, especially if you want to try to replicate this work. So we start with a substrate, and we then deposit the material we want to use. So we want to have silicone, which appears here in blue, then glass, which is our spacer here in green. And on top of that, we put our photoresist. And with the electron beam, we write the shape, which is like a cylinder. And in that opening, we deposit aluminum. So now we have an aluminum disc on top of glass and silicone. And we use the same technique as I've shown in the beginning, which is the ion beam etching. So we're just now going to etch this structure by bombarding with ions. And we see that actually the aluminum disc, which is going to become the plasmonic part of our structure, is going to also serve as a mask to protect the structure. So basically, because it's very hard, it will protect what is underneath from the bombardment of the ions. And as a consequence, we will define here these structures. So this is what we have here. The structure is defined through the bombardment, and this area has been protected here by the aluminum. Of course, it's a relatively harsh process, and you see that the structures are not perfect as you would have if you would etch with an acid following the crystal axis, but you get something that you can define, and also you can make it on relatively large area. So the idea here was this aluminum plasmonic disc will basically support only one resonance, which is an electric dipole, but the silicon cylinder, because it has a high refractive index, will have many, many different modes. And you see we have a zoo here of many different modes in that system. Now, when we combine them together, again, these different modes will hybridize, and we end up having many, many spectral features that you can monitor and look at. So in the experiment, we use this feature for doing sensing. So what we did, we took, for example, here, this little dip, or we took this little bump, or this dip here, or this bump here, and we changed the refractive index of the background. So either we put water, 133, or we put water with a sugar solution, 1.4, 1.44. And as we increase the refractive index, we see that these different features, they move. Usually they shift to longer wavelengths, they redshift. And by measuring the amount they shift for a given change in the refractive index, we obtain basically the sensitivity of our sensor. So this sensitivity is indicated in nanometer per refractive index unit, which means how many nanometer will the mode shift when we change the refractive index by 1 unit, which is of course huge. And this is what we get. We see that the different features have different sensitivity. The best we can do is with this feature number 2 here, and its sensitivity is about 210 nanometer per refractive index unit. So this works as a biosensor. Unfortunately, it doesn't work as a very good biosensor, because if we compare what is published in the literature with dielectric resonators, so waveguides or mushroom type of resonator, actually you can get a sensitivity which is 300 nanometers, so better than that. And if you look at just plasmonic nanostructure, the sensitivity is even better, because you get 600 nanometer per refractive index unit. So that was a bit disappointing, all that technology, and in the end you don't have something much, much better. Nonetheless, we tried to persevere a little bit, and we came with this observation, which is if we make a simulation of the structure, we see this is the silicon, this is the disk, And here in between, we have the dielectric spacer. We see most of the light is confined in the dielectric spacer. And the background, the medium we want to probe, it cannot come here because this is glass. So we thought maybe we can etch a little bit. So put basically in acid, in HF acid, and remove this glass such that the liquid could penetrate and be more in better interaction with the field of the structure. So we did that by a wet etch step to do this undercut, and these are the structures. So I'm sorry, they don't look beautiful cupcake, especially here. This is the aluminum we have on the top, and aluminum is always very grainy, but it doesn't matter too much because the field will mainly oscillate along the plane of the cap, so it will not feel too much this graininess. And here, this is in green, this is the glass we have etched a little bit. You see it's a bit more recessed. And here, this is the silicone cylinder. By doing this and providing a better access to the near field, we can have an improvement in the sensitivity, which now reach about 245 nanometer per refractive index unit. So it's better, but it's not as good as just a plasmonic nanostructure. So there is certainly a lot to be done there to understand what is going on. Just before finishing, let me come back to this beautiful picture from the Sainte-Chapelle in Paris and ask actually, now these beautiful colors, are they actually really plasmonic nanostructures? Have our ancestors put some small gold nanoparticle in the glass space? And we were privileged that not far from Lausanne, not far from my university, there is a center for stained glass windows, which is quite an amazing place because it's full of cardboard boxes with bits of stained glass that come from all around the world. And we could put our hand on a small piece of glass that comes from Germany, from the Cathedral of Ulm, which was built in the late medieval times. So we took this small piece of glass, we cut it, and we looked through the side of the glass. So we put it on the substrate with some glue, and this is through the thickness of the glass what you can observe. So there is indeed a region which is colored. And our question is, well, is that gold nanoparticles? So to solve that, we did EDX analysis through the depth of the sample, and we were looking for gold or silver. And unfortunately, we didn't find any gold or any silver through that piece of glass. But we actually found some copper, which you see here in dark brown, and you see it better here. You see it superposed to the optical image. And you see there is indeed copper in that system. And copper is actually one plasmonic material. It's not a material that's very much used because it has a very high absorption. The imaginary part of the permittivity is quite high. So it's not used a lot nowadays, but obviously this is something that was used in the Middle Ages to do stained glass windows. By doing electron microscopy analysis, we were able to measure the size of this particle. They are fairly homogeneous, about 60 nanometer plus minus 15, and they are extremely diluted. The density is very, very small. The distance between neighboring particles is almost 4 microns. So it's very, very diluted, but you see it's very efficient for producing the color. We wanted to double check that indeed this was the origin of the color. And for that, let me just make a small detour to the way we perceive colors. We have in our eye these cones. There are 3 types of cones which have different sensitivities, one mainly in the blue, one a bit in the blue and mainly in the red, and one in between in the green. And out of these 3 cones, we can actually classify any color as a point in the so-called color gamut. So any color is given here by a point in this diagram. So some spectrum, we can project it on these three cones response and obtain a point here in the diagram. So every color is identified basically by a point in this diagram. And you can determine this point from the spectrum, the response of the structure. So we calculated for a 16 nanometer copper particle its response, absorption, extinction, scattering. And out of that, we computed the color. And you see here, this is what it tells us from the spectrum. And if we compare this with the color we see in the glass, we have a fairly good agreement. So I think we can be quite confident that indeed our ancestors were using plasmonics for making strong colors, but it was not gold, it was copper. And this brings me to the conclusion. I was giving you an overview of our activities. I think different facets of them. I think nanofabrication is, of course, very important. Different approaches for fabricating nanostructures. Most publications, they use lift-off, but actually I think etching is probably often superior if you want to make very, very tiny features. Then we have the metals nature has given us, gold, silver, copper, aluminum, but why not mixing them? And it turns out that mixing gold and silver provides a lot of flexibility, and you can have more metal, so you have more dielectric functions, and you can make fun effects like hologram or metasurfaces. Still some very fundamental questions like those related to magnetism and optical frequency. I think it's a subtle question, and one could mix electric quadrupolar response and take it for a magnetic response, but it's not the same. So one has to be very careful when one goes on those grounds. And beyond just doing plasmonic, beyond using just metals, I think combining metals with other materials like dielectric, high permittivity dielectric, like silicon is very interesting and probably has some promising future. Of course, all this is only possible because I have extremely gifted collaborators. This is a group photo, especially for that presentation. We had Deb Data and Xiangshu working on the metasurface, Gabriel, Karim working also on the theory and the magnetic modes. You will find all the papers on the website, nanophotonics.ch. Thank you very much. It's been a pleasure sharing that with you.
Okay, thanks, Professor, for very nice presentation. Okay, any question? I think we have the time, 5 minutes. Maybe
it was all very clear. That's very good.
Yes, you are right.
Yes, it was really very clear, Professor Martin. Professor Fahrettin Yakupanoglu. Professor Martin was a real teacher, I think, and it was very, very excellent presentation. Just now I see Professor Süleyman Özçelik, and he is surprised, I think, yeah?
Professor Martin, thank you very much. Congratulations for your warm talk. And, thank you for your valuable contribution to our conference. Have a nice day.
Thank you. It's been a great pleasure, and I will stay in the room because I see we have a lot of very exciting talks to come. So I look forward to, and also for tomorrow. So thank you so much for having me. If you have any interest, don't hesitate to drop me a line or look at the publication, or if you would like the slide, I'm of course very happy to share all that.
Yeah, it's very nice. Thank you very much. Bye.
Bye-bye.
Bye.
Okay, thank you. I think we have 4 minutes for the next speaker. Okay. Next speaker, Professor Nejat Hamdawi from the Institute of Computer Science and Communication Techniques, SOS University, Tunisia. The title of the talk, New Concept in Ultraviolet Photo Detectors. Professor, if you're ready. Okay, Professor. If you're ready, are you ready? Are you hear me? Professor, are you hear me?
I hear you. Can you hear me?
Yes, now it's okay. Now it's okay.
Okay.
Okay. Yes,
First of all, I would like to thank the organizer for inviting me and allowing me to share my work. So I'm Najat Hamdawi from University of Sousse, Tunisia. Today I'm going to talk about the new concept UV photo detectors. And here I show the outline of the talk. So I will present in the overview some UV photodetector based on nanostructure. Then I will explain briefly why we have chosen ZNO nanostructure as active layer to fabricate photosensors. After that, I will present some results and finally the summary of this talk. As an introduction, I will introduce why UV photodetector is interesting device at the moment. The market for UV sensors is expected to grow over the next 3 years to $2.69 billion as the use of these sensors in wearables and the Internet of Things accelerators. According to a new report from Technavio, UV sensors integrated into wearables is accelerating as consumers adopt these devices to monitor daily activities and health and to enable connected communication. UV sensors in wearable device can perform functions such as preventing sunburns and skin blemishes by alerting the wearer when UV level become dangerous. When used in a smartphone, the sensors measure UV radiation and prevent users from damaging skin, which could help fight against skin cancer and other skin problems. Meanwhile, the IoT industry will be another driving factor of UV sensor growth as these devices promote automation, reducing the need for human intervention. The demand for sensors in smart homes, industrial automation, and automated cars related to the IoT will significantly increase the use and growth of UV sensor market. It exists different kind of photodetector, among them the conventional photosensors. Conventional photosensors are usually driven by external power source, which not only make the system bulky and heavy, but also limits the level of achievable miniaturization for application in areas such as IoT and biosensing. In addition, energy consumption for these photosensors, which will be dispersed and largely employed in all the world as in IoT system, will be a serious challenge that stops the world technology developments over the next years. Therefore, to meet the demand of future photosensors with the reduced dimensions and without external power source, it is highly desirable to develop a self-powered photodetector. So the new types of UV sensors is the self-powered photodetector, which can work without external power. These devices have many advantages compared to the conventional sensor, as lightweight and small size. However, to achieve high performance UV photodetectors, generally we use high quality epitaxial films deposited by molecular beam epitaxy or MOSFET techniques. But these complex fabrication methods make the cost of the UV self-powered photodetector very high. Therefore, it would be beneficial to elaborate low-cost UV self-powered photosensor devices with high performance operating at ambient temperature. So to achieve this high performance, two kinds of UV self-powered sensors are employed according to the type of the power source used. One type of photosensors was powered by nanogenerators, which scavenge energy from photosensors itself, such as self-powered photodetector based on triboelectrical nanogenerator. The other type of self-powered photodetector exploits the strong internal electric field located at space charge zone of PN junction photodiode or Schottky photodiode, which can provide energy for themselves. Compared to these two kinds of power sources, the device's Schottky type photodetector has the advantage of low-cost fabrication, easy synthesis, rapid response, and high photosensitivity. As a result, this kind of self-powered photodetector are more desirable in novel technology. Now let's shed light on the important characteristic of photodetectors. The photodetection parameters are presenting in this slide. So the response photocurrent is defined as the current generated by photodetector under UV illumination. Sensitivity is the ratio of the photocurrent and the direct current. Hence, both response photocurrent and sensitivity need to be larger for a given high performance UV photodetector. The photodetection speed of a photodetector is another important parameter which defines how a photodetector can detect UV signal or how quickly it goes to its original state after being switched off. Primarily, two parameters, response time and recovery time, define the photodetection speed of photosensors. Furthermore, an additional important photoresponse parameter is the responsivity. It measures the electric output per optical input. In addition to study the noise-related signal of a photodetector, specific detectivity, which defines the ability to detect weak UV signal by a photodetector, must be determined. Moreover, to the above key important parameters of the photodetector, low noise is also necessary for an operative photodetector. It is the decisive factor that defines detection limits for photodetector performance. This table summarizes the typical UV photodetector parameters and the mathematical relation used to evaluate the overall photodetection performance. The photocurrent is the difference between the current in dark and under illumination. Sensitivity is the ratio of the photocurrent and the dark current. The rise time described as the time required the photocurrent to reach 90% of its maximum value, while the decay time needed for the photocurrent to drop by 10% of its maximum value. Responsivity is the ratio of output signal and the optical input. And the specific detectivity is given by this equation. To date, many studies of self-powered photosensors fabricated using different semiconductors have been reported. Among them, gallium nitride, silicon carbide, and ZNO are the most frequently used active materials for self-powered photodetector. In contrast to gallium nitride and silicon carbide, ZNO can be ground on different substrate by sample process at low temperature. In addition, ZNO can be elaborated in various morphologies, such as nano-built, nano-rods, and nano-nils by easy and low cost effective techniques. Besides, it offers a high surface to volume ratio and consequently high responsivity. What is more, gallium nitride and silicon carbide UV photodetectors are inappropriate for many UV protection usage as a result of their low responsivity, less than 0.8 ampere per watt. On the other hand, using ZNO, we can easily reach a responsivity about 100 ampere per watt. So that's why we have chosen in our study this type of materials. Let's now show some experimental result of this talk. So there are several methods to elaborate ZNO nanostructure. Our nanoparticles were synthesized according to the following method. First, the precursors are well ground in an aggregate mortar. Then the powder is added to the sodium hydroxide solution in polyol medium. Thus, the whole is well mixed with ultrasound at room temperature for 13 minutes until the complete dissolution of all the precursors. Finally, a quantity of water is added to reach the hydroxide content, and the mixtures obtained is heated to the boiling point of the solvent for 6 hours. At the end of the reaction, the synthesized precipitate is centrifuged and washed several times with ethanol and once with acetone, and then dried in an oven at 50 degrees Celsius and annealed at 300 degrees Celsius for 1 hour. When we look to the XRD patterns for our nanoparticles, it's seen that all the peaks are in good agreement with the world-side hexagonal phase of ZNO materials, which mean that our samples possess hexagonal world-side structure. Moreover, the spectrum does not show any additional peaks associated to dopant. So we can say that the dopant element has been introduced into the ZNO lattice. So in this slide, we show the team images of ZNO-doped nickel, ZNO-doped cobalt, show quasi-spherical form with mean size between 20 and 30 nanometers. In the other hand, ZNO-doped copper, it shows quasi-spherical particle with mean size of 100 nanometer. After XRD and team measurement, our nanoparticle were deposited on silicon substrate using spin-coated method. But before this step, silicon substrate was cleaned sequentially by sonication in soap solution, contain alcohol, acetone, and isopropyl for 30 minutes. Then the substrate was dried and cleaned with UV ozone plasma for 15 minutes. Subsequently, platinum electrode was deposited to obtain Schottky junction. This slide displays the current voltage curves of our three diodes measured in dark and under laser illumination. The electrical behavior of the sample confirms the formation of Schottky barrier. The rectifying behavior of the current voltage characteristic proves the creation of depletion zone at the interface between ZNO and the electrode. Based on the thermoionic emission model, the Schottky barrier height and the ideality factor are extracted and presented in this table. So we notice that the barrier heights are almost identical in darkness and under illumination, which proves that the increase in current under illumination is due to the photo-generated current and not to lowering of the barrier height. And this property is very important to have stable photo detector. The photoconduction mechanism of ZNO-based UV photodetector with illumination is given in this part. So under UV illumination, photogenerated electrons holes are produced in ZNO films due to the band-band transition. After the photogenerated electron hole are separated and driven by the internal electric field. In dark, oxygen is adsorbed on the surface of ZNO grain by capturing free electron, and this process creates a depletion layer with low conductivity at the surface of ZNO nanoparticles. Under UV illumination, the photogenerated holes in ZNO can discharge the negatively oxygen ions and distract the depletion layer. After removing UV illumination, the oxygen reabsorbs on ZNO surface and capture free electron again. So, as expected, our photodetectors indicate a reversible switching between a low and high photoconduction states without exterior bias voltage when the laser was turned off and on. It is clearly seen that the photocurrent is about many order of magnitude larger than the current under dark condition, which clarify the high sensitivity of our UV photodetectors. Therefore, this feature confirms that our photodiodes device can be functioned at self-powered mode. Additionally, the time-dependent photocurrent of the devices was performed at varying illumination power density, as shown here. The devices show good feature in repeatability and stability as function of power density, and the similar line shape of pulses show an excellent repeatability of photo switching. So using the pulses measurement, we were able to determine the linearity interval of each photodiode by plotting the evolution of photocurrent as a function of laser power. So this slide presents the plot of the three devices. So it is seen that the photocurrent vary linearly by increasing the intensity power for the three photodiode. The linearity is, we can say that the linearity is in a wide range of light intensity. To investigate the response speed of our UV photodetector, the response time has been determined. One cycle of photocurrent versus time and the UV light power density of 7.6 milliwatt and at 0 voltage was recorded. The response time are determined for every photodiode, as you see here. So from the best of our knowledge, the rise time here is one of the shortest time reported for the ZNO based UV photodetector, but it is clear that these times are too long than the response time of photodetectors based on silicon, for example. So it is well known that the chemisorption-desorption process governs photogeneration of free carriers in ZNO, and here it is obvious that the decay time becomes slow when the UV light turning off, which means that the recovery time governed by the adsorbate molecules on the surface of ZNO. So the long response time here is mainly due to the existence of an oxygen absorption process on the surface of ZNO, which slows down the response of the diode, and this behavior is the major problem with which prevent to fabricate rapid photosensors based ZNO. These plots show the responsivity of the three devices. It revealed that by using ZNO nanoparticle, we can easily achieve a responsivity of the order of 100 ampere per watt. In addition, we can see that the responsivity decreases by increasing the laser power. This behavior is mainly attributed to the screening effect of the electric field by the electrons, which accelerates the process of electron-hole recombination and therefore reduced responsivity. Another important parameter which can evaluate the performance of our devices for UV photodetection is the detectivity. These plots show the detectivity of the three devices. From these curves, we note a high detectivity for all sample. Maybe this value of high value of the detectivity are due to the low dark current and low noise, as we will see now. So in addition to the above key important parameters of the photodetector, low noise is also necessary for an operative photodetector. Here the three devices show that the flicker noise is dominated. This kind of noise is related to the mobility fluctuation of electron hole. The mobility fluctuation can be attributed to the number fluctuation of electron holes at the grain boundary and to the dynamic process of the adsorbate molecules at the surface of ZNO nanoparticles. At low value of reverse bias voltage, noise spectral density can drop to a low value, as we can see, mainly for copper and cobalt doped sample. And this result can be considered as interesting compared to other results in literature. We summarize so our work in this slide. This table shows the collected data of our devices as compared to results found in the literature. The performance of our devices indicate the possibility of using our nanoparticle to develop photodetectors that demonstrate improved performance using a simple and low-cost elaboration method. And as conclusion, we can say that the elaborated nanoparticle are appropriate for this kind of optoelectronic device by using simple polyol method. Furthermore, the fabricated self-powered photodetector offer a high responsivity, fast response time, and low noise current at room temperature operating functionality. So thank you for your attention.
Okay, thanks, Professor, for very nice presentation. Now I think we have the time. We can get the short questions. Any questions? I think, okay. Okay, I want to ask one question.
Yeah.
Did you prepare your device in the form of the Schottky diode or heterojunction diode?
No Schottky diode. We have used platinum as Schottky contact to prepare our devices.
Yes, you prepare zinc oxide coated on the P-type silicon, I think, yes.
Yeah, with platinum as electrode to fabricate Schottky diode.
Yes. Okay. Can you explain the one? Can you show me the current voltage curves of your device under the illumination? Okay. You can see here the when you illuminated the reverse current and forward current is changed. Normally, in the photovoltaic diode, just reverse current should be changed. Can you explain this situation?
Our devices here is not for photovoltaic applications. So here we have not photovoltaic properties in our devices. Just at 0 voltage, so the current increase under illumination. So we can exploit this property to elaborate diode which can use it as photodetectors at 0 voltage.
Okay, thank you. Any questions? Any other questions? Short questions? I think we have the 5 minutes. Okay, I think we don't have any questions. Okay, thank you, Professor.
Thank you very much.
Professor Süleyman, do you want to say anything?
Professor Süleyman Özellik just not here, near to me.
Yes.
So no, nothing. Welcome and thank you, Necef, and welcome, Raul.
Thank you.
Professor Yakupanoglu, the stage in your, you can continue.
Okay, thank you. Okay, now the next Dr. Raul Arenal from the Institute Nanoscience of Oregon. University of Zaragoza, Spain.
Okay.
Yes, Professor. The title of the talk, Optoelectronic Properties of Low-Dimensional Materials Investigated by TEM EELC. Okay, yes, Professor.
Okay, hello everyone, good afternoon. Thank you very much for giving me the opportunity to be here and to participate to this meeting. It's a pity as we are always saying the same, but it's true that I wanted to be there in Ankara, but unfortunately, let's see another year, probably next year or never. In any case, yes, as you say, I am coming from the University of Zaragoza, and I will present you these works on how it's possible to investigate, to study the optoelectronic properties of materials using the transmission electron microscope. So Zaragoza, I don't know if you are familiar with this town in Spain, is here in the middle between Madrid, here in the center of Spain, and Barcelona. And there we have a national facility for electron microscopy. And wait a second, because it's a little bit annoying because I see everyone here in the let's see if I can stop. No, it's even worse. Here, but doesn't matter. Okay, so there we have this national facility for electron microscopy, and we have these two aberration corrected microscopes, which are the two that I am, most of the works that I will present today are coming from these ones, and in particular from this one that is probe corrected and with a monochromator, and you will see why it's so important to have the monochromator. And I wanted also to advertise a little bit this European project, the STEAM3. I don't know if you are familiar with this one, but it could be interesting for you because we are a consortium of 15 universities and research centers using advanced microscopy. And we are offering our instruments to the community. So it's working more or less like a synchrotron. So it means that you can apply, you can write a proposal, you submit this proposal, and if the proposal is accepted, the European Commission, via this project, is paying the charges of the use of the microscopes. For the Turkish, it's a little bit probably more complicated, but why not? It's probably, we have some room for third countries, so probably it's something that can be interesting for you. Okay, so that is my current team, and some of the works that I will present are also developed by Mario Fernandez once he was a PhD student in the group. Now he's a postdoc, and you see here also the funding of that I have for developing the research. Okay, this is the outline of the presentation. I will do a brief introduction about transmission electron microscopy, the different techniques, ILS, because you will see that is the main technique for all these studies. And after I will switch to 3 different examples, how it's possible to prove and to study these nanomaterials and the photonics and the physical properties of these materials, having in parallel all the information that TM can provide. So the shape, the structure, even at the atomic scale, and the chemistry and so on. And the properties that I will, or the applications that I will show are 2. The first one is how it's possible to measure a band gap, an optical band gap, in this case a 2D material, and the other one are the studies of the plasmonics, as we had a very nice introduction by Olivier Martin. So you are probably familiar with transmission electron microscopy. In this afternoon I saw several micrographs, so you know more or less that some of the particularities that we have. As I already mentioned, we have now with this with these correctors, aberration corrected microscopes, we have access to the atomic level, so we can resolve the structure and also analyze the chemistry of the materials at this low scale. And here is how it's working, more or less, a dedicated STM, so a scanning transmission microscope, but any STM is working more or less in the same ways, only that this sketch that we can see here is normally you see everything in the reverse situation. So in brief, we have our electrons that they are generated in an electron gun, and we have an optical system that is focusing in this case, focusing the probe, and we are going through our material, through our sample, and we have the interactions of these high energetic electrons with the electrons of the atoms of your material are generating several signals, several different phenomena that they are happening, and we can collect these different signals and to analyze differently them. So, for instance, we can collect the photons, X-rays, and in this case, to do EDS analysis for knowing the chemistry of the material. You can combine with the collecting here the high angular elastically scattered electrons and to form images and to have access not only to the structure but also to the chemistry, because these signals are proportional to the atomic number and to the density of the material. And we can have also the possibility to collect, and this will be the main part of the presentation, the ICLLT, so the electron loss spectroscopy. So it means that we will collect the electrons that they are losing some energy due to the interaction with the sample. And in parallel, in some cases, particular ones, you can do also to collect the visible light that is generated there, and not visible light, sorry, photons, yes, visible, so to perform cathode luminescence. Okay, but these are the combination of techniques that we can do, and that these ones that I am doing. And as you see, we have several possibilities. We can do high resolution TM or high resolution STM. So in this case, it's an example that will be useful for the next part of the presentation, where we have a transition metal bichalcogenide. In this case, is a molybdenum disulfide, and you can have access, as you see, to the atomic level, and to have the information about the phase of the material, and also to the number of layers, because it's a laminar layer material, and in this case, you have access to this information. You can also perform diffraction, and in this case, it's a carbon nanotube, but whatever it is, you can have very good information about the structure and the crystallinity of the sample. As I already mentioned, we can also perform ICLLT, and here we are more focused in the core losses. You will see later what is the mean, but we are studying the absorption edges. And in this case, I put this example because we can also investigate not only the inorganic matter, but also the organic one, and that is a hybrid system of nanoparticles with some organic moieties that can be analyzed and can be, you can see what is the distribution and so on. And as we will see also, we can perform electron tomography to have access to the 3 dimensions, because as you see from the previous techniques, we have always the information in 2D projections, but the objects that we are always investigating are in 3D, apart of the 2D materials that we will see later. But the other ones are in 3D, and this is a very important information, and particularly in the examples that I will show regarding the nanoparticles and the applications, for instance, in plasmonics. These are for the application in catalyst. They are platinum nanoparticles. I think that, I don't know, but this video seems that it's not working. But in the next one, I think that is working. So I mentioned already that I wanted to briefly describe what is ICLLT. Here we have the two regions that we can discern in a ICLLT spectrum. One is the core losses, as I already mentioned. This information coming from the absorption edges. So in this case, we have these two examples here of the boron nitride, where we can see the boron KH, the nitrogen KH, and the other one here in the manganese with the L23H. And what are we doing here? So we are doing transitions between the core states. In this case, for the KH is 1s core states to the vacuum, to the conduction states. The same here for the L23 of the manganese. In this case, we are doing this transition between the 2p to the conduction states. And after we have the other region here, that will be the main important one for the rest of the talk, which is this one of the low losses. Okay, and there we have these transitions that they are involving these the transitions between the valence states to the conduction, or even the oscillations of these valence or conduction electrons. And in this case, you can prove the interband or intraband transitions and the plasmons. And okay, we will focus in these low loss ICLLT studies, and there I will present you two. In reality, three different examples. As I already mentioned, how it's possible to investigate the interband transitions, so to measure the demand gap of a material, and also the second and third example regarding the study of the plasmons. For this kind of studies, we need a monochromator. Okay, we are accelerating the electrons to high voltages between, let's say, 60 to 300 kiloelectron volt, more or less right now. But the monochromaticity of the beam is not very good. But we have the opportunity to have these microscopes also fitted with these monochromators. And in this case, we have energy resolutions that they are in the order, in our case, for instance, between 100 millielectron volts to 160, but they are now in the market much better monochromators that they are offering the possibility to go below 10 millielectron volts. For the kind of studies that I will present today, with this resolution around 150 millielectron volts, you will see that this is good enough for analyzing the materials. So the first example is this one, that is the study of the optoelectronic properties of this layer material that we will see that is an alloy between the two different metal atoms with these chalcogenides. It's a collaboration with the group of Kazuso Enada in Tsukuba in Japan. And we saw this morning, I was early this afternoon, the presentation of Hanko Pan from the ICFO in Barcelona, and he was presenting the 2D materials. In this case, the TMDs were also introduced, briefly introduced, but I wanted to spend a little bit more of time to see what are more or less the structure and the properties of these materials. So in this case, we can say that it's a layer material, but it's not a planar one, because you have a sandwich between the metal atoms, as we can see here in this transversal view. You have the metal atoms, and after you have the sandwich between two layers of chalcogen atoms. You have mainly two different phases, this one, the 2H and the 1T, where you have here what is the configuration, atomic configuration of this, in this case, of the cell unit, where you have the trigonal prismatic configuration here for the 2H and the octohedral one for the 1T. And the optoelectronic properties of these materials are very, very interesting, because changing the phase to H1T, you are going from a semiconductor to a metal one, but also playing with the number of layers, you can also tune the band gap and also to change for an indirect band gap in the case of the bulk material, as we can see here for the molybdenum disulfide and for the bulk tungsten disulfide. But once you are going to the monolayer, you have a direct band gap at the K point. And there are other ways to tune these optoelectronic properties, as putting some pressure in the material, creating defects, doping the dopants of the layers, and we were more interested in the possibility to have alloys, as we saw before for the plasma, not really the same application, but creating alloys between the different elements composing the TMDs. We have here can be seen in the literature with the changes between the chalcogen atoms, and in our case will be the difference between the metal atoms. And once you are doing that, and you have the possibility to do these TM studies that I already mentioned, and to have access to this atomic resolution, you can see that once you are mixing the different elements, in our case, we have the formation of a heteroatomic structure where we cannot see even if in the literature you can find that there are some segregation and phase separation. In our case, it's a mixture really between the metal atoms, the tungsten and the molybdenum atoms, and you are creating this new kind of structure. Once you have that, you can see here in the literature previous works from the same group in Japan, where they were performing Raman photoluminescence measurements in order to study what is the effect of the number of layers at some point, but also the alloying degree. The alloying degree means that the content, for instance, of molybdenum, how you can modify the amount of molybdenum that you have in the layer. And in this case, it's clear that this a peak that is an exciton can be really tuned once you are going from the molybdenum to the tungsten disulfide, to the pure materials. So as I already mentioned, we have the possibility to do this kind of structural analysis and to combine with EDS and with ICLLT to analyze the chemistry of these materials. And we were playing with 5 different samples, going from the pure molybdenum disulfide to the pure tungsten disulfide, and you have the other 3 samples in the middle with different compositions. And we have access again to the number of layers. So we have access to the information of the 2 parameters that can, apart the effects and so on, but the 2 main parameters that can define the optoelectronic properties of these materials. So once you are performing the ICLLT analysis, and we have here for this sample different spectra, ICLLT spectra, we can see different peaks that can be really identified, like the A and B excitons, because the excitons are the dominating feature in these materials, the C exciton also, and the alpha and beta Van Hoff singularities. So now the question is, okay, once we have this kind of spectra, how is possible to really be sure that we can analyze or we can measure the optical band gap of the materials? So once we are performing ICLLT, we have 2 different geometries. One that we call the penetrating geometry. It means that we have our material and we are going through the material, and in this case the ICLLT signal that we are collecting is proportional to the loss function. And here the loss function, it depends on the dielectric constant of your material. But you have also other possibility to study the material, which is to have the electron beam far from the object. with this B parameter, that is the impact parameter. So it's the distance between your electron beam and the object. And you can also study the material, because you will polarize the material. And in this case, the ICLLT signal that we are collecting can be wrote in this following this expression. Is a theory that has been developed in the 80s by Echenique and Lucas and so on. And in this case, this ICLLT quantity is proportional to the imaginary part of alpha, and alpha will be the linear polarizability. Once we have our system, this particular one, the anisotropic layer material that we have here, that we can consider like several sheets, in this case of these decalcogenate materials. So in this case, we can see from the literature that this alpha that I already mentioned can be expressed in this way. With two different components, one that is coming from the dielectric constant perpendicular to the z-axis, which is the anisotropic axis, and the other one which is parallel to the z-axis. And in our case, once we see the dielectric constants of the molybdenum disulfide, we can see that for this parallel one, so out of plane, in this case, we can see that the response is appearing. If you see the imaginary, the real and the imaginary part, the response is arriving after 3 V. So below 3 V, everything is dominated by the perpendicular contribution. And in this case, we can suppress this part of the expression, and we are in the same conditions of the optical absorption. So we have that we are measuring the absorption, and in this case, we can measure an optical band gap in our system. So we did this kind of analysis for the different samples regarding also the other parameters like the number of layers, and we were analyzing the two main parameters: the alloying degree, so the content of molybdenum, and the number of layers. And it seems that we cannot say that there is a change in the band gap due to the number of layers, but it's evident that can be seen that with the alloying degree, the transition is clear, and is the same, is following the same trend that you can see in photoluminescence at the macroscopic scale of these materials. So the main information, the main point that we can highlight in these studies is that we can have access to the chemistry, to the real structure of the material, to all the parameters, and we can also prove the physical properties of the material. And the second and the third examples are regarding the plasmonics studies. I don't know how is the time, but okay. And here I am comparing different techniques, the normal ones used for analyzing the plasmons in optics, so the optical absorption and the SNOM. These are probably the main ones. And with our ICLLT STEM or even TEM technique. So in our case, we have several advantages. Apart of these ones that we already saw, that we can have access even at the atomic level to the chemistry and the structure of the material, we can excite the object, individual objects, at different positions. So that is, and also we can prove also that we can collect the information about the dark plasmon. That is not the case for the optical measurements. So the study of the plasmons with ICLLT is a long story. It's almost 40 years old. So the first studies were performed by Philip Batson in the early 80s. And here is the case for, he was analyzing or studying, spherical nanoparticles of aluminum. And he was seeing, he saw that depending on the impact factor, so where he was putting the electron beam against the nanoparticles, the response, the plasma response was different. There are other works also in the 80s by the group of Christian colleagues in Orsay. And there is an important, very important one in the field that was this paper in 2007 by the group of Christian colleagues and Mathieu Cosea, Codile Stéphane in Orsay, near Paris, where they were analyzing the ILS data, but getting information in the 2D, in the plasmon the plasmon distribution of these different objects. In this particular case, they were silver nano triangles, and you can see how this plasmon resonance that we saw in the presentation of Olivier Martin, what is the spatial distribution of these modes. In my case, I've been working more or less since more than 10 years, also with different problems, different systems. And I wanted to highlight and to present these two ones, this one in the middle. The first one is the gold nano rings. It's a collaboration with people from my institute, Manuel Arruego, Victor Sebastian, and with the theoretical collaboration of Lucas Raag from the University of Namur in Belgium. So there we were analyzing this the people that were playing with the synthesis of this originally hollow gold nanoparticles. They were doing some modification and they were getting these gold nano rings, and they were applying these materials for cancer therapy. And they wanted to know what was the real response of the different objects that they were producing. And for that, you will see that ILS is providing this kind of information. So here we have an example of one of these gold nano rings. And what is the plasmon response of this one? We can see that in the theory, there are some words of Javier Aizpurua that is describing these two different dipolar modes that can be present in these nano rings with the symmetric and the asymmetric, antisymmetric configuration, with the coupling between the external, the outer, and the inner surface plasmon modes. And in this case, we can have the information about the different objects that we can find in the sample. And in this case, you will see that we can analyze nano rings with different aspect ratio. And here the aspect ratio will be defined the difference between the outer diameter and the internal one. And you will see that in this case, this is changing really this aspect ratio for all these nano objects. And we can see that the plasmon resonance is also shifting depending on this aspect ratio. That is the theoretical the simulations that they are following the same kind of trend that we found. Once we are compiling all this information, we can see that regarding this aspect ratio, that is sigma that we are seeing here, we can see that there is a different position of the dispersion that we saw already with the plasmon response. And that was interesting to see, for instance, this ring number 7, because we found this value of 2.4 EVs. And once we were comparing with the theory, that was for the rest of the cases was more or less okay. Once because we have all these rings supported in silicon nitride substrate, so you see that there is a good match between the experiment and the theory. But for this case, the last one, the ring number 7, you can see that there is a difference between these 2.4 EVs that we can find and this one of 2 EVs. It means, and we were analyzing later, that this nanoring was not really supported in the substrate, but half of that, of this nanoring, was in the vacuum. And we can, in this case, see the effect of the 3 parameters that can, we saw before also, that can govern this plasmon response of the nano objects, which are the size, the morphology, and the dielectric environment of the object. We also saw that this plasmon resonance, there is a coupling between the mode, and this dispersion of the coupling is enhanced for these nanorings that they have a small sigma and small aspect ratio. Finally, is the second and last example that I wanted to show. Let's see if I have time. Yes, I have 2-3 minutes. That will be more than enough. Is this one of the gold and silver nanoparticles? As I already mentioned before, most of the nano objects that we are analyzing, we think that they are planar, and at least we don't think that. But once you are analyzing in the TM, in the microscope, in the optical microscope also, you see these 2D projections. But sometimes the information is missing once you are going to the 3D object, and that is okay. This example is illustrate how you can see the object depending of the point of view. So for that, it's very important to, if you have this particular nano object, to perform electron tomography. And I don't know here, I don't know, sorry, but I think that is not, I don't have access to the video, but in this video, once you have the possibility to reconstruct in 3D your object, in this case, we are dealing with core cell nanoparticles. They are bipyramids of gold and silver, and the silver is a layer that is covering the gold bipyramid, and is the thickness, that is something that we can measure also for the tomogram, is between 1-2 nanometers to 10-15 nanometers. So in some parts, it's a very thin layer of silver. So that is important information that we can collect in 3D. And once we are analyzing the plasmon response of this object, we were analyzing different objects with different, again, aspect ratio. Here the aspect ratio will be the difference between this long axis against the short one of the bipyramid, and with different configurations in terms of the chemistry, core cell or pure core of gold. And there we can see the different plasmon modes. We can see that there are 3 that they are common for all the objects, independently the aspect ratio and the chemistry, which are these A, B, and C modes. And we could also, thanks to the theory, to identify what are these different modes. You see that, for instance, this one is localized. It's a dipolar mode that is localized at the sharp axis, in the close to the sharp apex here. So the other one, the big one, is more or less, could be better seen here, is localized for all, more or less, for all the trajectories close to the apex, the long or the short apex. And the other, the C1, is mainly localized here at the short axis, and the apex over there. As I mentioned, with theory, we could interpret the results that we got. That is, again, a collaboration with, in this case, Luc Anrard from the University of Namur, that he was doing discrete dipolar approximation simulations, and we could get the information about this, the electric fields and the different plasmos modes that we were seeing. And once again, we are combining everything, we could investigate what are the origin of these modes. So if it's a dipolar, quadrupolar, or it's even octupolar mode, but also how they are, these two parameters, the aspect ratio and the cell of silver are affecting the plasmon response. And something that I forgot to mention, and we see here in the table, is that even this surface plasmon mode of the silver, that is, remember that at some point is a very thin layer of silver that could be even 1-2 nanometers. We can even see, sorry, in the experimental part, that there is, sorry, here, this peak that is coming from this silver contribution. So with that, I summarize the different words that I was presenting. I think that you will have a little bit of view that the possibilities that we have in the TM, we can have access to the structure and the chemistry, but even at the atomic level, but also to investigate the physical properties of different nanomaterials and to analyze or to study the optical band gap, as in this case of the 2D materials that I presented, or for the plasmonic response of different nanostructures as these examples at the end of the presentation. So thank you very much for your attention, and I am open for any kind of question.
Okay, thanks, Professor, for your very nice presentation. Now I think we have the time. Any question? We need some questions because we have the time.
No, if not, doesn't matter. I had one for Olivier Martin, but I couldn't, so I don't know if it's the time to interact. I don't know if this could be another possibility.
Professor Yaşar, do you want to say anything?
Nothing, Professor Fahrettin Yakupanoğlu. So thank you very much for your sharing in this session, and also thank you, Raul, for your nice presentation, nice talk, and thank you for your coming, and thank you for accepting our invitation.
Good,
so,
thank you.
Do you have all of these devices, instruments in your laboratory?
Yes, all the two microscopes that indeed we have 4 different TMs, but aberration corrected 2. So
both
yes,
HRTM and normal TM. Yeah?
Yes, these are these ones that you see here. These 2 over there, which are the, how to say, the best ones in terms of performance for the atomic resolution, and in this case even for the energy resolution that I saw before.
Okay, audiences, dear participants, if anybody wants to talk, we can open their voice also. Maybe you have some questions, your video also. Just know we have time for approximately 10 minutes. If you have any questions, we are at your service. If not, we have time for taking photo, group photo. Are you agree with this?
Yeah.
Suggestion? Okay. Everybody, can you open your cameras again? Today is the day of photo, group photo. We are ready. Please open. Professor Süleyman Özçelik, the chair of the conference, and also Usa. Just no. Okay. I should select standard side by side. No. Okay. Please smile, please.
Yeah.
Okay. Delete. Okay. Huse, please take a photo. Meltem. Ibrahim, welcome. Okay, thank you very much. Thank you very much, Raul, for your coming. And we have time for coffee break again. The last session will start after, I think, 20 minutes. We have Hadise Alayan here and other presenters also. So, Professor Yakpanoglu, you can close this meeting.
Okay, thank you. Now, today, okay, for this session, we listening 1, 2, 3, 4. Now I am closing this session. Thanks, everybody. Okay, thank you.
Dear participants, hello to everyone. Welcome to session 5 of the conference. My name is Halit Altuntaş. I am going to be chair of this session. I'm a professor in solid state physics at the University of Çankırı. So, shall we start to session 5? The first invited speaker is Professor Halime Gül Yağlıoğlu. Let me give you a brief information about her. Sorry. Professor Halime Gül Yağlıoğlu received her PhD degree in Electrical Engineering Department in the City University of New York, USA in 2001. She worked as a research assistant during her studies at the same university, and her studies were supported by CUNY Science Fellowship. She studied characterization and time-resolved dynamics of nanostructures for nonlinear optical applications during her studies for PhD. After returning to Turkey in 2005, she joined Engineering Physics Department in Ankara University as a faculty member. She has been teaching and doing research in the same department in the field of linear, ultrafast, and nonlinear optics. Professor Halime Gül Yağlıoğlu, please welcome.
Thank you. Thank you for the introduction. I guess you can hear me and you can see my slides clearly. Is there any problem?
Okay.
Okay. I'd like to thank Professor Süleyman Özçelik for inviting me to give a talk about our research in Ankara University. Today, I'm going to talk about ultrafast dynamics in solutions and the thin films. Let me talk about our laboratories. We have primitive optical material preparation and characterization laboratory, as well as the ultrafast laser and ultrafast dynamics laboratory. In this laboratory, we have, ultra short pulse tight sapphire laser oscillator, amplifier, optical parametric amplifier, and some experimental setups. So, as we know, events in atoms and molecules happen in femtosecond and picosecond time scales. And when we talk about fluorescence, that's a little bit longer. It takes about nanosecond time. For non-radiative processes, we know that they are very fast events. Collision in liquids at room temperature, takes place a few femtoseconds. Almost all processes in liquids are in the ultra-fast time scales. Semiconductor processes of technological interest are necessarily ultra-fast. So therefore, time-resolved techniques, are important. There are a lot of time-resolved techniques and out there, but most of them rely on pump and probe measurements. So you use pump to create excitation or to have any impact on the system, and then you measure the response of the system with the delayed probe measurements. So some of the techniques of the pump probe measurements are, one of them is the time-resolved fluorescence technique, where you excite the material with the ultra-short pulse, and then you collect the fluorescence emission through the streak camera, which is triggered with the laser. So the other technique is time-resolved absorption technique, where you pump the laser with a pump light, and then you probe the excitations in the material, in terms of transmission with the probe pulse, which is usually a broadband source. And another technique relies on the measuring the polarization changes in the material, which is in the reflection form. So today I'm going to talk about these last two techniques. Of course, there are other techniques out there, so you can use them. And we know that ultrafast dynamics of almost any physical effects that can be induced by ultrashort laser, ultrashort light pulses can be investigated with one of these techniques. So as I said before, today, the first technique I'm going to talk about is the time-zone absorption spectroscopy. Again, in this technique, we use a pump pulse to create an excitation between electronic excited states, or you could also create an excitation between, vibrational and rotational states based on the energy of the pump pulse. And then we use white light continuum, a broad pulse, to monitor those excitation. So to have an excited state absorption, or you could monitor any transition happening inside the material, or it could be between donor and acceptor, or it could be between one particular material. And for those who are not familiar with this technique, let me just introduce basically. So we have a pump pulse, which is a narrowband pulse, ultra short pump pulse, and then we have a probe pulse, which is a wideband pulse, which is we call it white light continuum pulse. And then what we do is actually we send the probe pulse to the material, we look at the transmission, we detect the transmission spectra of the probe pulse, and then we saw the linear absorption of the material within the white light continuum spectra. And then we create an excitation with the pump pulse. Before the excitation goes away, we send the probe pulse. And then probe pulse actually sees the excitation. That means probe pulse sees the excited state absorption that is happening between two excited levels. So what we do is we basically compare these two spectra with respect to each other, because if you divide these two spectra, you get rid of the linear absorption, but you end up with the excited state absorption. You get rid of the steady state absorption, and then you end up with the excited state absorption. How we compare this? Actually, our laser produces pulses within 1 kilohertz. So we chop the pump pulse. So we cut every other pump pulse to reduce its frequency to 500 hertz. So what we do is, if you compare adjacent white light continuum pulses with respect to each other, while one pulse has the effect of the pump, the other pulse do not have the effect of the pumps. So therefore, we compare the white light continuum pulses one after each other. And if you delay after you see the exact state absorption or whatever the transition, if you delay the white light continuum pulse with respect to pump pulse, then you get the time response of these events that you are monitoring actually. So with this kind of experiment, let me talk about the experimental apparatus. For this experiment, we are using commercial time-resolved absorption spectroscopy experiment. And in this experiment, as you can see from here, we have a pump pulse pumping the sample here, and our delayed probe pulse is focused on the sapphire plate here, and sapphire plate generates white light continuum, and the white light continuum pulses are detected through the transmission via fiber optic spectrometer. So what we do is we measure the white light continuum spectra at here is the wavelength, here is the time, and the amplitude gives the amplitude of the events that we are monitoring. So we collect this white light continuum spectra at different time delays between pump and probe pulses. So, and then we get this three-dimensional information. So if you slice this in at one particular time, and then you get the spectra wavelength versus normalized transmission, which is which gives you either the exact state absorptions or the saturation at the signal. Or if you slice this for one particular wavelength, you get the time response that are happening inside the material related with that particular wavelength, whether it's a slow, process or it's a faster process. So I'm just gonna give you two examples what kind of information you can get out of this system. For example, in this example, I chose this example because it clearly shows the ability of the experiment. So with this example, Professor Güler from Bilkent University came to us and he said that he has two molecules. One of them is the peptide molecule, which is a long chain. The other one is the phthalocyanine molecule that have the, fluorescence property. So he said he believes that when he combines these together under certain conditions, he believes that these phthalocyanine molecules are stuck inside this peptide, and then they form a nanofiber. So he wanted to, prove that they are really inside, they are stuck inside this. What we did was we measured the transient absorption of this phthalocyanine in a solution, and then we saw that in their response, they have this, yes, and when we pump it here, they have the excited state absorption here, but then they have the excited state absorption that is delayed with respect to singlet level excited state absorption. Therefore, this is considered triplet level, the excited state absorption between triplet levels. Okay, we know this information. Now, we looked at the same data when we combine these two molecules, when we form the peptide nanofibers. So when you excite the singlet level, it does not go into the triplet levels of the molecules. Basically, you get the excited state absorption, which is belong to singlet levels, because it comes up right, right after when you pump the pulse. And then we saw that, when you change the pH levels, you can make it shorter. So that was the proof that, yes, molecules are stuck inside the fiber. Why? Because when you stuck the molecules together inside the fiber, not only the electron transition happening inside the one molecule, you can also have electrons transition, happening between adjacent molecules. So every electron transition happening between adjacent molecules shortens the lifetime of the excited state. And then we can clearly see that excited state lifetime is getting ultra fast due to the electron transfer. That was the proof that, yes, the molecules are stuck inside the peptide fiber. So, or with the continuation of this work, so you can, attach P-type and N-type molecules in these peptides. So basically, you can create P-type and N-type nanofibers. So when we put them together, so you can see from this image that they get aligned with respect to each other. So then how do we make sure that they are really aligned? What is happening when they align? So we did the, pump probe measurement, and then we saw that depending on the pH level, actually when they align, so they can, when they stuck together, align together, then there's another electron transmission between one fiber and the other one, because one of them is P-type, one of them is N-type. And this type of electron transition also shortens the lifetime. And as you can see from here, the lifetime gets shortened. It gets even less than 1 picosecond. So you can get ultra fast short time. So these are the proofs that, what these are the examples, what you can do with this technique. So any chemicals, any molecules, combination of these, so you can excite it, you can detect the frequency, F rate, you can detect the transmission to, electron injection to triplet levels on between donors and acceptor molecules, all this kind of stuff we can do it. But with the time result absorption, yes, you can do all this kind of information, but this has some limitations because time result absorption relies on the transmission of the pulses, especially white light continuum pulses, because you detect the white light continuum pulses after it transmits through the material. But some materials do not transmit, light. So what are you gonna do? So you need other techniques. Therefore, we started to build up another experimental technique in the laboratory, which relies on time result polarization changes. So in this technique, similarly, I'm going to talk about this technique from the rest of my talk. So in this technique, you have a pump pulse to create an equilibrium, state inside the material, and then you reflect the probe pulse off the surface of your material, and then you detect the changes in the polarization of the probe pulse. So this technique is called, this technique is called time resolved magneto-optic Kerr effect. So the potential, let's look at the potential application. So magnetic storage media, magnetic recording, and other spintronic devices, these applications are, important applications. But in order to have these applications, you need to understand magnetization dynamics in a strongly out of equilibrium system. Not only you need to understand this, but also you need to control the magnetization dynamics of the nanostructures by optical pulses, optical lights, lasers. Therefore, you have to understand the phenomena behind this, but this phenomena behind this is incomplete. This is a new field. Therefore, this is an emerging field that, takes place last 10 years or 15 years. And this field is called ultra-fast magnetism, ultra-fast magnetizing dynamics. So that was our motivation. So characteristic time scale of magnetization dynamics, are, depicted in the figure on the left-hand side. But I want to concentrate on laser-induced ultra-fast magnetization dynamics timescales. So first, when we hit the material with the ultra-fast lasers, we basically generating hot electron within 5 or 10 femtosecond time frame. And then these generated hot electrons thermalizes with spins. So those hot electrons interact with the spin. And then this thermalization takes place on the order of 100 femtosecond. And then within that time frame, demagnetization happens. After that, around 1 picosecond time frame, electron, lattice, and the spin reservoirs interact with each other to get in an equilibrium state that I'm going to talk about this one later on. I'm going to explain it in details later on. So, and then the whole system, gets the temperatures gets in an equilibrium state. So after 10 picosecond, what happens is that precession of magnetization takes place, and damping associated with magnetization precession takes place. So these are the motivations. So explaining this laser-induced demagnetization taking place in ultra-fast timescales, there are a few models. The most accepted model is called phenomenological three-temperature model. And in this model, actually, electrons, lattice, and spins are considered thermal baths. Electron thermal bath, lattice, and then spin thermal bath. And the temperature changes with time. The electron, lattice, and spin temperature changes with time are given with these three coupled equations. Change of the electron temperature with time, change of the phonon, and then spin times. So when you solve these couples equations, you can get the electron, spin, and lattice temperature changes with time, which is a very fast time. So let me explain this graph a little bit. So this time zero is the time zero between pump and probe pulses. So what happens when you hit the material with ultra-fast pulses within 10 picosecond time frame, the temperature of the electron system increases considerably, 700 K. Then the temperature of the electron system starts decreasing, and then the interaction between this electron and the spin systems, due to the interaction between electron and spin systems, the temperature of the spin system starts rising. And due to this difference between electron and then spin system, the temperature difference causes demagnetization of the material. So magnetization of the material starts dropping when this temperature difference increases. On the other hand, this lattice and electron, this equilibrium state takes place. That means the temperature of the lattice builds up slower than the temperature of the spin system. So this is the temperature of lattice. After, couple picosecond time frame, this temperature of these three systems equilibrate. They, come at the same temperature. So this is the three temperature model describing this phenomena, ultra-fast demagnetization phenomena. Let me talk about a little bit experiments. So you all know that, optical Kerr effect. So when we have linearly polarized pulse, light, actually, we know that linearly polarized light is the combination of left and right hand circular polarization. So if the material has optical Kerr effect, that means the refractive index is different for left and right circular polarization. Then when you reflect this light of this material, due to the difference between these two polarization changes from linear to elliptic polarization. So this is called optical Kerr effect. But if you put this material inside the magnetic field, then this is called magneto-optical Kerr effect. So based on the magnetization, the vector, polarization vector, and the plane of incidence, it has a different name, polar longitudinal transfer geometry. And basically, in this technique, we are detecting the polarization change. So the simplest explanation is that we pump the material. As I said before, we pump the material, hit the electron temperature, increase the electron temperature, and material is under the magnetic field, and then we send our probe pulse and with the linear polarization, and then we detect polarization change of reflected probe pulse through the Wollaston prism and the balance detector. Of course, experiment is not as simple as this one. So experimental setup is a little bit more complicated. So this is a homemade setup because there is no such a equipment, so commercial equipment that you can buy. So we have to build this setup in our laboratory. So we have a Thai sapphire laser amplifier system delivering 50 femtosecond pulse duration and 800 nanometer wavelength. So we divide this one into two arms. One arm we use as a probe pulse, the other arm we use as a pump pulse. And for the probe pulse, we generate 400 nanometer by using BBO crystal. This is a nonlinear crystal. And all this stuff, I'm not gonna go into the detail, is to clean up the beam and they adjust the polarization wavelength and etc. So, and then this is our pump pulse. So our sample is in between, it's under magnetic field. All this magnetic field, optical delay line, and are controlled through the computer, and the detector, balance detector, the signal received from balance detector is received with the locking amplifier and then computer. So the whole system is controlled with a Levy program written by our students in the laboratory. So actually, this setup is supported by TÜBİTAK with this grant number. TÜBİTAK is the Turkish Science Foundation. Actually, the principal investigator of this project is the Eyüp Duman that I work with from Ankara University. So after we set up this experiment, we wanted to, investigate some materials. We chose iron aluminum thin films. Why did we choose iron aluminum thin films? Because we know from the literature that so when you magnetospatter this iron aluminum thin films, if you don't do the heat treatment, this film is amorphous. And in the amorphous form, this film is a ferromagnetic film. And we know from the literature that if you heat treat this material, then crystallize this material, it becomes non-magnetic. And then if this film is non-magnetic, when you hit with ultra-short pulses, what happens is that it turns into magnetic. You create magnetic region that ultra-fast pulses hit. So from that, we concluded that this material responds to ultra-fast. You can change the material's magnetization states with the ultra-fast pulses. So we thought, if we use the iron aluminum thin film without heat treatment, so we can hit with the ultra-fast pulses and then we can demagnetize this material. So that was the motivation. So we basically took the VSM curve at room temperature, which is the which shows that our material, our thin film, is a ferromagnetic material. Then that means we can, investigate the demagnetization of this material. So these are the curves that we took with our experimental setup. As you can see, this is the time zero. This is the time result magnetization change. As you can see, at time zero, when we hit, before we hit the material with the optical pulses, there's no magnetization changes through this time frame. But once you hit the material with the femtosecond pulses, you create demagnetization in a very short time, and then after for a while, this demagnetization go back to its original state, so remagnetization takes place. So here in the inset, you can see the small the fluence values of those experiments. As you can see that we can ultra fastly demagnetize this material, and then the remagnetization takes place. It's a little bit longer. When we did this experiment at higher fluence levels, we saw that the shape of the curve changes its characteristics. So what is going on? In order to understand this, we went back to the model, and then we saw that there's another model came up, which is called microscopic three temperature model. So in this work by Kaufman in 2010, they wanted to explain an experimental evidence that took place before these years. So in the experiments, from other groups, materials like nickel, which has 3D electrons, have a response of demagnetization response, which is called type 1. Their response is single step. Their demagnetization time is fast, ultra fast, 80 femtosecond, 100 femtosecond. And also they have large spin flip rate. And then they explain with this microscopic model that this is due to the strong coupling between electron and spin system. So in this work, they said that, so we have, as I said, in 3 temperature model, we have 3 temperature reservoir: electron temperature, lattice temperature, and the spin temperature. For those kind of materials,
I'm so sorry, Professor Yaloğlu, you have just 1 minute.
1 minute? Oh,
yeah.
Okay. So anyway, in this system, so you have, this is the faster process, but for gadolinium-like system, you have 4F electrons. Therefore, you have this system that takes 1 step, and then this system, the equilibration of this system takes another step. Therefore, they believe that you have 2 different steps. And therefore, in type 1 type materials, your demagnetization takes place faster, and then in type 2 materials, demagnetization is slower, and the remagnetization also have different, different evolution. So in order to have type 2 material, they predict that you need to have three mechanism to happen. One of them, that you have to do experiment at closer to Curie temperature. So the question is, can you have this type 1, type 2 transition in the same material? This is important because if you prove that you can do it in the same material, then that means ultrafast dynamics is governed by the thermal process. And then there's only one work in the literature that they did the experiment at different temperatures, and then they proved that they can have type 1 to type 2 transition within the same materials. I'm finishing in a few seconds. And then we can explain our data. Maybe we can say that if you look at our data at the lower fluence values, we have type 1 type signals, even though in the type 1 signals, even though then you increase the fluence, you still have the same structure. But in our case, we increase the fluence, but we don't have the same structure, but we have different 2-step structure. And then we fitted our data with the 3 temperature model for the low fluence data. We get about 100 femtosecond demagnetization time, which is in line with the literature, which agrees with the literature. And then we believe that within this iron aluminum film, while increasing the fluence, we are actually changing the demagnetization type from type 1 to type 2. Why we believe this one? Because, as I said before, in order to have this transition, you need to work closer to Curie temperature, and our material has Curie temperature, which is close to the room temperature. That's why we believe that you can have this transition from type 1 to type 2 demagnetization, and that is the proof that is the second evidence in the literature that this phenomena takes place due to the temperature. So the temperature change is behind this ultra-fast demagnetization. So before I finish my talk, I'd like to thank TÜBİTAK, and I'd like to thank our students for putting up this experimental apparatus, and then working long hours in the laboratory for these experiments. And thank you for the organizing committee for giving me a chance to talk about our research.
Okay, thank you very much for your excellent presentations, Professor Halime Gül Yağlıoğlu. Sorry, we passed the 3 minutes, so only we can have just one question. So, dear participants, have any questions? But we can have only one. Okay, no questions. Thank you very much again.
You're welcome.
To the conference, and have a nice evening.
Have a nice evening, you too.
Thank you. So, Süleyman Hocam.
Thank you very much, Ms. Halime Hocam, for your valuable contribution to our conference.
I thank you for organizing this conference, and it was a very successful conference. Thanks.
Have a nice night.
You too.
Bye.
Okay, thank you again. The next invited speaker is Dr. Hadise Alanyan from the Purdue University. Let me give you a brief information about Dr. Hadise Alanyan. She received her PhD in electrical engineering and physics from Stanford University in 2015. For her dissertation focused on the studies of non-Hermitian and active photonic systems. She received the silver medal from Materials Research Society in 2015. After her graduation, she moved to Germany first as a Humboldt postdoctoral fellow at the University of Bonn, and later as a junior group leader at the 5th Institute of Physics at the University of Stuttgart. Her research has been focused on quantum dynamics and phase transitions in photonic systems, including their Bose-Einstein condensation and atom-induced photon-photon interactions. In August 2020, Hadise joined Purdue as an assistant professor of the electrical engineering and physics, where she is extending her studies to the strongly interacting quantum photonics and quantum photonics gates using right-back excitons.
Hi, can you hear me?
Dr. If you are ready, please welcome.
Hi, I'm trying to start my camera, but it seems that it doesn't allow me to start my video. But that's okay. If you can see my screen, I think that's actually what matters. Can you see my screen?
Yes, we see yours.
Yeah, because I'm gonna keep turning on the camera, but you see, it's just kind of doesn't.
Okay, no problem.
Thank you, everyone, and I want to thank the organizers. Let me see if I can even just. Okay, great. So I want to thank the organizers for putting together such a program and giving me the opportunity to talk about our research. So since I'm new at Purdue, most of my research will be about the work that I've been doing in Germany with my group. So we are a group of atomic physicists and quantum opticians. So our goal was to really control the atom with lasers, slow them down, coherent control the states of the atom, basically cool them down to the Fermi degeneracy, getting the Bose-Einstein condensation, and so on and so forth. So just as a motivation, if you walk into our lab, you won't be amazed by seeing a lot of electric wires dangling, a lot of controls, laser controls, and beam shaping. And we were just wondering how much of that we could really remove and go to the smaller system sizes, basically on-chip system size, and how much of that could be integrated. And the main motivation for us was that, of course, all of the coherent control that we are doing with cold atomic physics is kind of really appealing and interesting, but as you could imagine, this system size cannot be really cascaded and kind of delivered as a quantum computer to your room. So that was the main motivation for us. And we set ourselves to do a bit of thinking and being innovative to see that how we can integrate at least part of these things on a chip. So our dream goal would be really kind of condensing this whole room on a chip that we can control everything. So not only from the laser side, but also from the electronic side. So the benefit of working with atoms is having identical quantum particles. On the other hand, nanophotonics would allow us to engineer the light field on the sub-wavelength regime. And then if we put them together, we are benefiting the best of two worlds, and we have a robust and integrated scalable quantum technology. So before talking about the specific experiment, so it's important to know that what the figure of merit is. So if you have, like, let's assume the simple scenario, I have an atom, just the most favorable and choose it, and then I say that that's a two-level system, and I have a photon, and they want to interact. So what is the figure of merit? We can think about just the scattering cross-section, the absorption, but if I pull all of them together, I can boil down everything to three important parameters. So G being the vacuum rabbit frequency, which basically tells me that how coherent the interaction between the photon and atom is. Kappa is the cavity lifetime, how long the photon can be captured in a cavity, and gamma prime is the emitter decoherence time. So if I put them in my system and try to maximize this parameter, which is known as cooperativity, then we are in the business. So the name of the game is kind of increasing the quality factor of the cavity and decreasing the mode volume. So let's see where we are regarding the technology. So here I'm kind of summarizing some of the breakthrough in the cavity quantum electrodynamics. I'm just showing various systems, as you could see here, as a function of mode volume and then the cavity quality factor. So as you can see, and you may know, the best cavities are these kind of known bottle resonators, and then the cavities developed in Jeff Kimball's group at Caltech, and that they have quite high quality factor. But then they are pretty big in terms of the wavelength. So can we do better? Yes, if you are a bit compromising on the quality factor of the cavity, then we have the macroscopic cavities that they are kind of highly reflective, or we could have fiber cavities. These are actually kind of developed in the Max Planck quantum optics. And then in France, that they basically kind of trying to improve both the quality factor and decrease the mode volume. But then, as you can see, we are still far above the mode volume compared to the normalized wavelength. So the question is, can we do better? Or there is like a technological limit, a fundamental limit? And then the answer is yes. If we are using structured features that they are below the wavelength, then we can squeeze the mode volume on the order of wavelength or even less. And that was exactly the idea that they've been doing at Stanford, and then there are also some works done at Harvard. They are kind of pioneering the work, having the, these are called nanobeams, so you can think about them as suspended bridges, that the mode is fully confined, and they are sub-wavelength structures. So the mode volume is far below the wavelength. And the quality factor is rather okay, but still you can see that they are far from what we want to be, far from the ideal scenario. And we had some talk about the plasmonic systems. For a long time, people were interested about them because they have the least mode volume so far, but then the coherence time and the length is pretty low. So for our applications of the coherent control of the atoms, basically we are trying to push in this limit just using the dielectrics, so they are not adding loss to our system, and we try to maneuver all the other difficulties that we have just to squeeze the mode as far as we can and also increase the quality factor. So in this talk, I'm going to talk about three different experiments that they are related to each other. I want to first introduce the platform that we pioneered. That's basically interfacing the atoms, the alkali atoms, in our case rubidium, with integrated nanophotonic devices. Then I'll be talking about the atom-atom interactions mediated by a photon in this sub-wavelength structure, and towards the end, I'll talk about novel atomic beams and even single photon sources that we've been working on. So this is our vacuum cell, if you wish. So we have at the heart of that, what really matters, this is kind of photonic chip. That's something centimeter by centimeter size. And we can have a whole slew of different devices. As you can see, we have beam splitters, we have ring resonators, we have cavities, ridge modes, ridge waveguides. And then, so we can really kind of manipulate the mode as we wish. That's what we advertise. And then here where we have the reservoir of rubidium, and then we can send the rubidium atoms toward our vacuum cell. And of course, it was kind of connected to a pump, so we can evacuate the cell and have the pressure as low as possible, so we do not have the collision of the atoms with the background gas. Okay, so this is the first experiment. The setup is just a bit messy and bulky, so I'd like to walk you through it. This is basically the part that I showed that's in the heart at the center of our experiment. That's where the chip is. And although the devices that I'll be talking, they are different, but they share the same working principle. We send the light through grating couplers. We have our devices mainly covered with silicon dioxide, and we only leave some of the regions as interacting regions where the atoms interact with the modes of the photonic structure, and we basically capture that behavior, somehow sense that behavior on the output grating coupler. So the atom that we choose is rubidium. That's one of the favorite atoms of atomic physicists because the vapor pressure at room temperature is kind of pretty high, so we can get a lot of atoms. And then they are alkali atoms, right? They are just the first column, so they only have one electron in their valence band, so they are the most similar one to the hydrogen atom that we know pretty well. I don't want to bore you with all of these electronic structures, and at this point it really does not matter. All of these kind of symbols for the F spin or the orbital angular momentum coupling. The takeaway message is that we are basically having 3 levels involved. These are like hyperfine levels, and at this point we just have them. So let's just say that we can have like a 3-level system, and we have transitions from the ground state. So we have the laser coming from the top. We are sending the atom from the ground state to the excited state, and we have the coupling beam just sending that to the higher energy levels. So first, let's really see all of these behaviors spectroscopically. So this is our reference cell. We have counter-propagating beams. For those of you who are kind of familiar with the atomic physics experiment, that's basically the configuration that we can suppress the Doppler broadening as much as we want it and as much as possible, so we can get the Fourier limited or the natural lifetime of the energy levels. So we have 3 levels, and then each of them are kind of allowed by the changing the quasi-spin of the photons, basically plus minus for the circularly polarized and 0 for pi polarized light. So that's why for each transition, we have 3 sub-transitions, but then you see that overall we have like 9 transitions. So we have like a whole slew of electric transitions that we can benefit from. So the system is kind of quite versatile. So what we are doing for our spectroscopy, basically seeing that how the atom interact with the mode of the photonic device, we send the light through the grating coupler as I already advertised. And here is the typical image that we are recording on our CCD camera just to make sure that we are doing the coupling properly. And then we do a lot of filtering and then spatial spectral filtering. And this is the output that we are getting at the grating coupler. And then we are scanning the laser to see all the transitions. That's really the working principle. But of course, as usual, there are some subtleties when it comes to the real case. In our scenario, it's the Casimir polar. So you might have heard the name, or maybe you are more familiar with the commonplace terminology for that, the van der Waals. So that's basically like the fluctuations, fluctuation dipoles, or you can think about that. This is like we have the atom, it's polarized. We have a high refractive index dielectric. So we would have like an image of the atom. So they exert force to each other. And then they basically changes the electronic structure of the atom. So this is also the Casimir polar force that we expected for our devices. So this is our kind of theoretical calculations. And then we wanted to, so this is the results that we get from the spectrum doing the spectroscopy. And then as you can see, the purple line is our simulation, putting together all of the Casimir forces and all the transitions. And you can see that we can nicely describe the signal that we are getting. So for your reference, I'm showing the signal from the reference signal on the reference cell that I showed with the counter propagating. And you can see that this is just a teeny tiny part of the spectrum. Why is that? The reason is that now we have these atoms that they are slowly moving, but they are leaving the beam area. So we have some transient interaction between the atom and the laser field that leads to this kind of broadening. So this is basically like the transient broadening of the transient interaction between the atom and the field. So and then the next thing, which is interesting, we are working with an atom. So Where the quantum effect kicks in, that's we basically start to pumping the atom hard, then we start seeing saturations. So we set ourselves to study that behavior. As you can see here is just the spectrum, and then we keep changing the telecom probe power, so we make it kind of stronger and stronger. And then if we kind of do the analysis on the data, we'll see that we have a region at the beginning where the telecom power is low. We have like a flat plateau. That's basically where well beyond the saturation, and suddenly the saturation kicks in, and we see the typical quadratic increase of the line width. You can see that I also have two regions designated with single photon detection and photodiode. The reason being that at the beginning, when our photon count is pretty low, we are using the single photon detector to basically do the spectroscopy, and later the number of photons that we are getting becomes larger and larger, so we can do the simple detection with a photodiode. What is interesting here, though, if you have some numbers about the saturation intensity for, let's say, rubidium in free space, that's really like a measurable number. Here I'm talking about the femtowatt power. So this is actually, and as you can see, we are starting to saturate atom with a few photons. Why is the reason? And that's one of the interesting thing about squeezing the light, as already advertised. So I have the mode area being way smaller than the wavelength. So the effective mode intensity is so large that I start to see the saturation effects at very low photon number. Okay, that's good. We knew the system, and we had also some other studies for coupling that to the other resonators. But then the next thing that I'm kind of more interested about is where we have the interaction kicks in. That's where we start to not only talking to atoms, but even forcing the atoms to talk to each other the way that we want it. So we all remember from freshman E&M that a dipolar radiation of an atom has a very anisotropic radiation pattern. So here is actually a very nice gift. You can just see that the wave fronts start to get emanated from the dipole. And then here is just a kind of snapshot. And what you can see here, as I already advertised, is that the long range, the interaction first is long range because we have like 1/r in the Fraunhofer or the far away region. And then another interesting thing is that the radiation is kind of quite anisotropic. So depending on where we put the atoms respect to each other, I expect to be able to tune the interaction. To be more concrete, we all remember our dipole-dipole interaction. That's just the radiation pattern of the dipole. And then if I assume that now I can increase the density in such a way that the atoms be in the near field of each other, which basically means that the K, the wave number R being much smaller than 1, then I can drop the far field parts. And then I'm only left with a near field term, which I would like you to kind of pay attention to that, because interestingly, there is no retardation effect as we expected because we are in the near field. And then it is anisotropic. And then as you can see, by changing this theta, which is the relative angle between the dipoles, I can tune the dipole-dipole interaction to be either repulsive or attractive. For example, I'm showing you here two extreme cases of the dipoles that they are arranged side by side. And they are here, and they are arranged head to tail. So obviously when they are head to tails, they are absorbing each other. So that's like a physical intuition. So the energy is shifted to the red side, where it's kind of lower energy, while when they are kind of aligned side to side of each other, then you can see that they repel, and then that's why the energy is shifted to the blue side. Okay, so enough of the abstract thinking. So let's see that how we can implement it. Also, this is kind of with our students, we developed a very strong package that's based on a Monte Carlo, and then putting just a density matrix formalism together. And so we can basically not only evolve our atomic structure in time, but we can even just imprint any desired trajectory on the atoms and see that how basically it moves in time as it also moves in the position. So this is basically the simple scenario that we set ourselves to study better. Let's say that we have a chunk of atoms, uniform in this case, and then we are sending the light. So of course the electric field is polarized perpendicular to that direction. That's, for example, one of the exemplifying cases. And then we look at the line shifts. I already told you that why we expect to see a line shift as a function of box length, which basically tells us that if the system is 2D or 3D. So first you see that there's an interesting transition point, that the behavior changes from repulsive to attractive. And then if I just kind of do some cuts at particular box length, so going from 2D to 3D, you'll see that the line shift is kind of proportional to the density. So if we go back, I would like to draw your attention to this one. If you go back and we look at this one, which is dropping at 1 over r cubed, it's not really surprising that it should be also proportional to the density. Okay, good. Now how we can implement it, because I was just kind of talking about very squeezed light below the wavelength. So with free space beam, you cannot do that. But that's also where nanophotonics comes to our help once more. We can squeeze the light using these nanophotonics. So this is our system. We are using the slow waveguide. These are basically like the dielectrics. In our case, they are silicon. And they are on the order of 300 nanometer and 300 nanometer. And they are separated by variable gap. So the results that I'll be showing you in the next few slides is about the gap about 50 nanometers. So they are really tight, close to each other. So the mode is fully confined within the slot. And then we have the atoms coming through this slot. So we basically have, like, you could imagine as a 1D chain of the atoms along the waveguide direction. And here is just a snapshot of the electric field, just to show you what I already qualitatively described. You can see the electric field is kind of fully squeezed inside the gap. Okay, this is our kind of only the control part of our experiment. We have 2 lasers. Again, we are using 2 photon transition just to go to the excited states. We are using a single photon detector because you remember that we saturate our atom at a few photon number, and then we have just a time tagger, and then we do like a post-processing on computer. This is one of the experimental traces. We are measuring the line shift as a function of probe power. So first thing first is that you see we have a drastic shift. That's good. That's the atom-atom interaction. But then why it's changing with power? What is happening here? So we were kind of, we had different hypotheses, but then we figured out something pretty interesting. So if you think about the system, I have a few phenomena working together. I have the atoms individually interacting with the photons. That's just a single atom physics or single body physics. On top of that, we have the atoms. They are so close to each other, so they have dipole-dipole interaction. That's good. So we see some many-body effects. But then there is like a battle or like a competition between the single atom nonlinearity and coupled atom nonlinearity. When the probe power is small, the nonlinearity of the atom is so small that we only see the single body effect, but as the probe power increases, then we start seeing the nonlinearity saturates. This is basically like some of the behaviors that I'm showing you. And then this is some of their experimental measurements. We are kind of comparing with theory. And if you kind of look closely, you'll see that, okay, we are capturing the behavior, but then we are kind of like a few times less than what we're really measuring. So then we were asking ourselves, what's next? What we are missing here? And that's another interesting thing, that using these waveguides, we can control the local density of optical states. And then by virtue of changing the local density of optical state, we can Purcell enhance the atomic radiation. So for example, here I'm just showing you the Purcell enhancement as a function of D for different polarization. And as you can see, for the electric field, which is the dipolar type, we have a Purcell factor of 40. So it means that the dynamics of the atom is 40 times enhanced. And then now if you put all of them together, you'll see that we get an excellent agreement between our experiment and the theory. And then within the next few minutes, I would like to talk about our last part of the experiment, where we are kind of designing a novel atomic beam in situ control. The technique that we are using and developing is LIAD, light-induced atomic desorption. The idea is rather simple. We have the atoms sticking on a surface, and we kick them in with a pulse, and we generate a cloud of the atoms. Then we do the absorption spectroscopy to see the density of the atoms. So this is one of the typical scenarios. You'll see that we have at T equals 0, we get the light pulse, and then we do the continuous absorption spectroscopy. And then if you just kind of zoom in at the very few part of the gigahertz region, then you'll see that we have kind of two groups of the atom contributing to this transition. So this is basically,
sorry.
Yes.
I'm sorry, Dr. Hadise Alanyan, you have 3 minutes.
Sure, yeah, that's perfect, thank you. So this is some exemplifying cases. So as you can see, we can come with a light pulse and then we can really desorb the atoms from the surface. So then the light level decreases because the atoms are absorbing them. And then as they diffuse towards the beam and outward from the beam, we get the atomic density back. Okay, so then we were kind of interested saying that, oh, hang on a minute, it seems that something interesting is happening. The line width is kind of getting broader. So we set ourselves to do more of a time result measurement on our light technique. And then we noticed that at the beginning, the line width is quite broad, but then as we go to the later times, then it becomes narrower and narrower. So we said that, okay, it should be some signature of the atom-atom interaction. And then to test it, that's basically quite straightforward thanks to the atom having different levels. So we choose another transition where the transition dipole is only 2 times larger. So it means that in the interaction, it would be 4 times larger. So we did exactly the same experiment going to the other transition. And by virtue of doing the spectroscopy, then you notice that we have the basically the D1, which is just a transition to a specific level, 5D1/2, and this D2 is 5D3/2. And then if we kind of do the fit to the data to extract the density, broadening, and the shift, you'll see that as the time goes on, the density decreases. That makes sense because the atoms diffuse out of the beam, right? Because they are flying. And then the broadening and the shift, which they are many body effects. At the beginning, we see a huge difference in the broadening proportional to the transition dipole moment. But as time goes on and the cloud becomes dilute, then the broadening and the shift, both of them disappear. Why is it so interesting? Because you might have heard about the Rydberg studies that we're doing. So now we can increase the interaction in such a way that we can even not only have slight shift in the energy, but such a drastic shift that we can blockade the other transition. For example, we can see that in our case, 5 micron away from one atom, there wouldn't be any excitation. So we have a bubble of 1 excitation. So that's exactly what we need for a single photon source. And that's kind of, I would like to finish with having the most exciting results of our experiment, getting on-demand single photon sources in our system. So we are using a 4-way mixing technique. So we are sending the atoms to the excited states and then to the Rydberg level. So here by virtue of having the dipole blockade and Rydberg blockade, we get a single photon excitation. Now it comes the Reed pulse and we take back that excitation to the intermediate level. And then here, due to the spontaneous emission, our atom decays to the ground state and it emits a photon. So that's exactly the experiment that we did. And then as you know, the hallmark of having a single photon detector is just doing the autocorrelation measurement. And as you can see, we have a noticeable drop below 1, which is just a single photon signature. And then to make sure that this is basically something that we can control by controlling the blockade radius, here we did a series of experiments on different sizes of the blockade. And as you can see, when we are below the blockade range, we have this kind of G2 dropping below 0. So we have full anti-bunching, and then we have non-classical states. But then above the blockade, we have like a coherent light. Okay, that brings me to the summary and conclusion. I hope that I introduce you and convince you to a strong platform that basically bridges between atomic physics and nanophotonics quantum optics to really lead to a new platform with benefiting from the best of both worlds. In particular, we talked about the single body physics in our atomic spectroscopy, about the dipole-dipole interaction mediated by the photons, and then towards the end, not only the dipole-dipole interaction, but only the Rydberg-Rydberg interaction leading to the blockade, and then, of course, non-classical source of light. So I'm just kind of, our outlook, of course, is just kind of moving towards the coherent control, as I already promised you. And then, of course, just benefiting from some other interesting features of the nanophotonic circuits like topology, just to imprint that on the atomic transition as well. So as you could imagine, this is not a single body work. That's really like a many body physics with many great colleagues. So I would like to thank all of my students, my colleagues, our senior colleagues in Germany, all the funding sources, and of course you for your attention. And I'd be happy to take any questions.
Okay, thank you very much, Dr. Hadise Alenyan, for your excellent presentation. So have any questions?
Professor Altuntaş, for me, I have a short question. I know.
Right, okay.
So thank you very much, Professor Alenyan, for your nice talk. I was waiting for the quantum mechanics. Eventually, at the end of three final slide, you talk a little bit about the quantum mechanics. It is very interesting to simulate and describe and investigate all of these quantum phenomena by classical electrodynamics. And are there any works which, you talk about the nano optics, about the atoms, atom interaction, and also some every quantum phenomena. Are there some other view which the role of quantum mechanics is highlighted, and the simulation, and also the works which view with quantum mechanics?
Sorry, I'm not sure that I fully get the question. So the question is that which part of the theory, the measurement, which part of that is kind of quantum, which part is classical? Is that what you were asking, or your question is kind of more general?
Yes, exactly.
Right. So I think that the basically all of our calculation is just quantum mechanical calculations. So this is just a density matrix calculation. So we have like a Hamiltonian, the Lindblad operator, and we are just evolving in that time. The only classical part is just in that quantum Monte Carlo that I mentioned to you. So the only classical part of our quantum Monte Carlo package right now is the motion of the atoms. So, and that's basically where we ignored the recoil, because, when a photon hits an atom, so it would kind of kick in a momentum and there would be a momentum back. So that is the part that we ignored. And that's kind of quite fair, because our atoms are moving with a velocity of 10 meters per second. And the recoil energy, if you kind of calculate, it's pretty low. So for us, it was quite legit to assume that the motion, the really like a trajectory where electrons are the atoms are moving on, it's a classical trajectory. So basically it's just ballistic motion of the atoms, but then the rest just kind of evolving the state of the atom, and then atom-atom interaction. These are all quantum mechanical calculations, right?
Okay.
Thank you.
You're welcome.
Okay, thank you very much, Dr. Hadise Alenyan, for your contributing to the conference.
Yeah, thank you for the invitation. Thanks.
Right. Yeah. Thank you, and hope to see you in Turkey in future.
Yeah, thank you.
Thank you very much. Okay. The next invited speaker is Professor Rashid Turan from Middle East Technical University. So let me give you a brief information about Professor Rashid Turan. He completed BS and MS degrees at the Physics Department of the Middle East Technical University, Turkey. He received his PhD degree from University of Oslo, Norway in 1990. He worked as a postdoc at Linköping University, Sweden. He joined METU Physics Department as faculty member in 1991. He worked as a visiting scientist at the Material Science Department of Toronto University, Canada in 1996. His main research interests have been physics and technology of semiconductor materials and devices, including solar cells. He has published more than 300 scientific papers in this field in the international recognized journals. Rashid Turan has coordinated many national and international projects, among them European FP6 projects, Semi-Nano, and METU Center have been among the largest research and support projects coordinated by Dr. Tura. In 2009, he founded a new research center called Center for Solar Energy Research and Applications, GUNAM, on METU campus. GUNAM has attracted nationwide and international attention. The talk lights management strategies for high efficiency silicon solar cells. Professor Rashid Turan, please welcome. You have totally 30 minutes, including the questions time.
Okay, thank you for this nice introduction, Dr. Altıntaş. It's a great pleasure to be with you here. Thank you for the invitation. I will be talking about light management on silicon solar cells, which is a very important topic, actually. Let me first share my presentation. Here's coming up. Is it seen now, right now? You see my presentation?
Yeah, we see.
Yeah, okay, thank you. Okay, the light management is very important for the solar cell efficiency, as you will see. What we are doing here is to somehow manipulate or manage the light coming onto the surface of silicon, so that we maximize the absorption by the solar cell, and then we maximize the efficiency of the solar cell. Here is my outline for this talk. After introduction, I will be talking about how we structure the surface of silicon by using metal-assisted etching, and then application of this technique to various structures, various type of solar cells, and I will finally come to the conclusion. Okay, let me briefly introduce the concept. As you might know, silicon is a kind of metallic material. I mean, of course, it's a semiconductor, but the surface is highly reflective. So it reflects almost 40% of the light falling on it. And in order to reduce this reflection, one approach is to use anti-reflection coating on the surface, which is commonly used material for this purpose is silicon nitride. Today, industry is using this one. And also another approach is to texture the surface, create some structures on the surface so that the absorption is maximized. But of course, the best result is obtained when we combine these two. Let me first have a pointer here, okay, and also maybe like this, okay. So the surface can be textured so that we maximize the conversion. We maximize the absorption by the solar cell. So here are some pictures, SEM pictures of the solar cell surfaces, which are, I mean, traditionally and commonly used by industrial solar cell manufacturing lines. So the reflection from the surface is reduced, as you see here, from the 30% down to first 10% by pyramid texturing, and then at certain wavelengths the reflection can be reduced down to 0. But still we have some loss in the UV part and also the infrared part. So one of the efforts being spent is to reduce the reflection even for the UV part of the spectrum and the infrared part of the spectrum. So the structuring surface is still an ongoing research field. So one of the techniques used to structure the surface is the metal assisted etching, so-called metal assisted etching, which is very effective. It's a simple solution-based technique. It's applicable to very large area and batch processes so that its high throughput is reachable, and it's very suitable for the industrial applications. it's a top-down approach, so the control of electronic and mechanical properties are relatively easy, and the wide range of structures can be formed by like nanowires, nanoholes, nanocones, pyramids, etc. So it can offer a superior electrical and optical performance compared to standard texturing methods used by the industry. Okay, let's see what is metal acid etching. In the metal acid etching, we use a solution consisting of silver nitride, hydrofluoric acid, and hydrogen peroxide, and water. So you see a chain of reactions takes place on the surface. First, silver nanoparticles are formed. As you see here, silver nanoparticles are formed on the surface, and these nanoparticles induces a Hall emission from the metal into the silicon, so that silicon get oxidized very easily. So this is kind of anodic oxidation. Then oxidized silicon is etched away by the HF solution. So this is how the technique is happening. So there's an animation here. First, the holes are emitted into silicon, and then silicon dioxide is etched, and it is then removed by the HF solution. So this technique is very powerful in creating structures like these nanowires. Here you see silver nanoparticles oxidizes the surface easily, and then it goes down, it sinks down into the silicon wafer, as shown here. So leaving behind the nanowires, as you see here. This is a picture of the surface after nanowire formation. Of course, when you have these nanowires, the surface becomes less reflective, and this is clearly seen here. The nanowire surfaces have quite black appearance, meaning that reflection is almost zero. So here we show the results, so that the reflection almost all in the whole spectrum is reduced, and sometimes goes down to very small values, down to zero. Especially the UV part is, as you see, is almost zero. So this approach was applied to solar cell manufacturing in our solar cell fabrication line. So we fabricated standard industrial lines, industrial solar cells, using these surface structures. You see the comparison. This is monocrystalline silicon. This one is multicrystalline silicon solar cells. In all cases, our devices are working quite well, and as expected, we have this rectangular type IV curve response. So, however, in all cases, the reference cells are, what's happening? Sorry, something happened here. I cannot pass to the next slide. Yeah, okay. So in all cases, we have observed that the reference cells are better than nanowire cells. So it seems that these structures do not generate the optimum condition for the solar cell efficiency. This is because we are losing the charge carriers due to the recombination and other reasons. So the electrical performance degrades even though we have better optical performance. So here are some discussions about these nanowire systems. These highly doped nanowires have a small area, and a lot of electron hole pairs are generated in these volumes, so that the Auger recombination becomes very important. So this is one reason why we are losing. And also the charge carrier recombination on the surface of the nanowires, the area has got a huge, in this case, we have a large surface area, so that the combination size are increased. and we lose the carriers at these recombination sites. So it seems that nanowires are not the best surface structure for the improvement of the efficiency. Okay, so we need to somehow, I mean, optimize the electrical performance and the optical performance simultaneously. So it's not sufficient to have a best condition for the reflection and absorption. We should also take care of the electrical performance of the system. So for this reason, we try to change the structure on the surface and look at the effect. So when we look into the details of this metal acetate etching, we see two competing processes here. One is the whole generation by the silver nanoparticles. The other one is the oxidation rate. So these two mechanisms are competing with each other. So if the whole generation rate is etching rate. One is whole generation rate, the other one is the etching rate. So if the whole generation rate is smaller than the whole consumption rate, it means that the oxidation rate is smaller than the etching rate. So we have structures like this, which is like nanowires. In the other case, if we have a larger whole generation rate or larger oxidation rate than the etching rate, then the structure will become different, kind of cones, nano cones on the surface. So we checked if this is happening, and if we check how the structures are changing with this variation in the solution. So here is showing the variation of the surface structures by changing the hydrofluoric acid in the solution and also the silver nitride. So when we increase the hydrofluoric acid, we increase the etch rate. And we, as you see, we go towards the nanowire formation. So when you reduce the, I mean, this is showing maybe better. When we reduce the HF concentration in the system, the oxidation rate becomes, etching rate becomes smaller, so that we are having structures like nanocones or some kind of other nanostructures. But when the HF increased, the surface structure becomes more like nanowires. And here we can look at, here you can see a closer and nicer pictures of the surface obtained with less HF content in the solution, and the surface can be further manipulated by using potassium hydroxide etching, smoothing the surface, so the surface structures can be adjusted in this way, as you see. Okay, of course, one of the important parameters in solar cell is the lifetime of the carriers. How does it change under these conditions, under different conditions? So we looked at the lifetime variation with the KOH treatment, which is smoothing process, which just rounds off the sharp edges after the etching process, and we get kind of smoother surface and better conditions for the carrier recombination. And actually, indeed, we have obtained nice results by KOH dipping time. As you see, the carrier lifetime started from 80 microsecond, has been increased up to 150 microseconds here by changing the, by using potassium hydroxide dipping. So after all these optimizations, we fabricated solar cells, and on both mono and multi-crystalline silicon wafers. But still a problem with my computer. Sorry about that. It's coming up. Okay, here. As here we see current voltage characteristics of the solar cell with standard pyramid textured surface and nano-textured surface. This is for monocrystalline silicon solar cell. And you see with the nanostructures on the surface, we have reached a efficiency value closer to the standard pyramid texture surfaces. So this is a good promising result because if this is working in the monocrystalline silicon, it should be more beneficial for the multicrystalline silicon solar cell, which we applied in this, which is shown in this slide. So in this case, we have a multicrystalline silicon solar cell fabricated on multicrystalline silicon wafers. And here we have seen that a significant improvement in the solar cell efficiency has been obtained by using this technique, because the standard etching process for multicrystalline silicon is not very good, is not very efficient. So for this reason, our technique is a very good alternative to the existing industrial processes. Indeed, this technique has been now implemented in the industrial lines. There are a few companies now using this technique in their multicrystalline silicon solar cell production lines. Okay, up to now I have shown the silver-based solutions, but there is another one which is very promising now, which is more recent. We are currently working on this. It's copper-assisted etching. In this case, we are using a copper-based solution to create surfaces like shown here. This one is a periodic inverted pyramid, which is known to generate the minimum absorption and the minimum reflection and the maximum absorption. It's very much desirable for the solar cell applications. However, this image, this sample was obtained by using photolithography, which is not desirable in solar cell manufacturing. Photolithography is an expensive and slow technique, which is not, of course, much desirable in the manufacturing lines. So we are trying to avoid using photolithography. So it would be very beneficial and advantageous if I can replace this lithography technique by another one and generate the similar surfaces. So copper assisted etching is a promising and low-cost technique in generating such structures. So I will show you some results from our own studies. So when you use this solution, which is similar to the silver case, and etch in 15 minutes, for instance, and then remove copper nanoparticles from the surface, you end up with a surface like this one. This is very promising. Actually, the inverted pyramids are formed on the surface. Of course, not periodical, but they do not need to be periodical. I mean, a random distribution is quite sufficient and acceptable for the solar cell operation. So what is going on here? The copper reaction taking place at the surface is modeled here, as you see. So it's a silicon band diagram and also the energy states of copper system. This is a solution, of course. This reaction is taking place on the surface. So the hole injection here, I mean, the same actually process is taking place. So we are having a hole injection from copper nanoparticles into the silicon surface. But in this case, the hole injection is highly dependent on the potential barrier formed at the surface, which depends on the orientation. So here, different from the silver case, we create a different electronic barrier system depending on the orientation of this silicon surface. So this leads to formation of inverted pyramids, which is different than silver nanoparticles. Okay, so we studied this a lot, and we are currently writing a paper on this one. We have fabricated surfaces with very, very small reflections. As you see, we have we have gone down to 3.7% in the reflection, total weighted reflection, and then this is quite, I mean, without any silicon nitride coating. So with a silicon nitride coating, we will obtain eventually zero reflection from the surface. Okay, so here are the surface structures. As you see, we start with a quite random rough surface, and then after etching continues, we end up with a quite nice inverted pyramid structures. And in this case, I mean, when we look into the details, we see that the etch rate is lowest in the 111 direction, but highest in 110 and 100 direction. However, there is also difference between 110 and 100 directions, so which makes it possible to have quite interesting, just like star shapes. I will show it later on, structures. So here, if you go further, I mean, if you make more like detailed adjustment and optimization, you may obtain star-like structures on the surface, and then the randomly distributed star shape inverted pyramids lead to, I mean, is led to generate a reflection about 2.6%, which is almost the smallest value seen in the literature after such a surface structuring. And I mean, the good thing about this structure is that the structure, I mean, the surface area is not very high, so that we are expecting to have a good passivation using standard passivating materials like silicon nitride and aluminum nitride. Okay. So some preliminary solar cells was fabricated, even though, I mean, these are not showing the potential of the system. We are currently working on making some new solar cells, but we have obtained extremely good value for the short circuit current, which is 39.1, as you see here. This is actually showing a very good, promising, I mean, value, so that we will reach much higher efficiencies. When we improve the fill factor is low here, 71%, and VOC will be improved even further. So then we hope to reach efficiency values in the range of 21, 22 with these structures very soon. Another fancy and nice study using this metal assisted etching. Let me see if I can go to the next slide. Here is the radial junction solar cells. When you have a flat surface like this one and thick silicon wafer, the electron hole pairs generated in silicon wafer should travel a distance like D here as shown. Okay, so this distance is not very small for an electron. Okay, and the material should be high quality in order to have electrons collected. However, if you make a radial type of solar cells like this one shown here, the distance that needs to be traveled by the electron is very short. Okay, maybe 100 nanometers or even less, depending on the size of your micro rod or nano rod, whatever. Okay, so in this study we try to make these radial junction solar cells and using again metal assisted etching. So we started with the silicon wafer, and then by lithography we defined some areas by photoresist, and then put gold film on top of that, and lift off the gold, and we created some open holes through the gold film, And then we etched away the regions under the gold metal, which is similar to actually what we obtained with silver. And then very nice micro pillars are created. And after that, we fabricated solar cells by standard technique, by phosphorus diffusion, oxide passivation, anti-reflection coating, screen printing of metallization. This is exactly same as what industry is using to make solar cells. Okay, and then we looked at, we characterized the samples. So here you see the SEM pictures of the structures we used. And of course, the nanopillar or micropillar length can be adjusted by using etch time. And the reflection from the surface is reduced by increasing the micropillar length, as you see from these measurements. And then later we fabricated solar cells, and we measured the solar cell performances. So here in this table, you see the micropillar length and the solar cell efficiency and other values. And as you see, VOC decreased with increasing pillar length, and the current is increasing first, and then here, when we look at here, it increases first and then decreasing. This is can be well understood. Field factor decreases with increasing pillar length. This is again indicating a contact formation problem, which can be solved. And the optimum value is obtained for this 11.5 micropillar length in this study.
Sorry, Professor Rashid Turan, you have 5 minutes, last 5 minutes.
I have 5 minutes. Okay, good.
Yeah,
I am coming
last
to the
5
end.
minutes.
Okay, no problem. Okay. So the radial junction solar cell is also fabricated on thin silicon in another study, which is also very interesting, because in the case of thin silicon, we have less material usage, which is good for the cost reduction. But here you need to increase the optimum. You need to increase the optical performance. So we fabricated. This is our sample. We fabricated very thin silicon, and we put silicon micropillars on top of that, and we obtained some results from these. We didn't make solar cell because they were very thin, but the results are showing promising structures on such a very thin surface. So I come to the conclusion and summary. And silicon is a poor absorber and needs light wrapping. Surface texturing is needed. Of course, metal assisted etching is an alternative. And the nanowire has very good optical properties, but poor electrical performance. So this technique can be optimized by adding, by playing with the chemical composition. An optimized recipe was applied to different cell structures, and we obtained good performance improvement. And this technique proves to be applicable to industrial application, and copper assisted etching creates inverted pyramids on the surface without any need of lithography. And finally, we have demonstrated a good operation of radial junction solar cells. So I want to use a few minutes. Okay, here are some acknowledgements, but before I close my talk, I want to use a few minutes to just tell about our center, METÜ Günam. METÜ Günam is the research center on solar energy conversion technologies, which is known in Turkey and also known in the world. We started in 2009, and today we have become an independent research center, national independent research center, independent from the university. You see our achievements now. At this point, we are capable of manufacturing industrial solar cells with quite good efficiency values. For the heterojunction system, we have reached 21%, 21.5%. In the PERC cells, we have reached 21%. IBC cells 19%, and perovskite cell 22% efficiencies. So GUNAM has been developing starting from 2009 with some very important milestones. One of the milestones was the MILGES project, which is a national big project, which is completed now successfully. We have demonstrated the outcomes of the project. And we received a second phase support in 2015, and we have established a new pilot line for the crystalline silicon solar cell manufacturing. We have been in many different projects. We have coordinated some of them, European ones, FP7, TÜBİTAK, etc., and a lot of master and PhD theses and national projects have been completed. We are organizing a major event on solar cell or photovoltaic technologies, which is called PVCon. It is written here, but PVCon 2020 was organized last year online, just like you do today. So finally, METÜ GUNAM has been authorized under law of 6550. It is being recognized as the Turkish National Center on Solar Energy Technologies. So I think that's sufficient for today. Thank you very much for your attention. If you have any questions, so I would be happy to answer them. Thank you.
Okay. Okay, thank you very much for your excellent presentations, Professor Rashid Turan. So due to time limiting, just only we can have one questions. Dear participants, have any questions? Okay. Any questions? Okay, thank you very much again for Professor Rashid Turan, and have a nice evening.
Thank you. Thank you. Thank you. Bye-bye. Thank you. Thank you. Bye-bye.
Okay. The next invited speaker is Professor Mustafa Muradov Bayram from Baku State University, Azerbaijan. Let me give you a brief information. He is the head of Nano Research Center at the Baku State University. He graduated from Moscow Engineering Physics Institute in 1981. Received his doctorate degree in physics mathematics. His academic and research interests are in the areas of nanomaterials, nanoelectronics, material science. He has published over 100 papers in highly reputed journals and international conferences. He was coordinator and participant in many European Commission and other international projects. His current research interests include optics, nanophotonics, nanomaterials growth technology, influence of growth condition and technology to structure and optical properties of nanomaterials. The title of the talk is Some Features of the Growth and Optical Properties of Nanomaterials. Professor Mustafa Muradov Bayram, welcome. And you have 30 minutes, but includes the questions time. Please welcome.
Okay. Hello, everyone. Good evening, good night, good day. I am from Baku State University Nano Research Center. First, I thanks to organizer for invitation to this conference. My lecture name is Some Future of the Growth and Optical Properties of Nanomaterials. In this lecture, will be considered the influence of growth process and environmental to electron state in nanoparticles. 100 years ago, one of famous physicists said that life is a game of electrons. In this lecture, we will consider how we can influence to electron state in process of nanomaterials growth and with changing of environmental. Outline of my lecture is information about Research Center, Baku State University, geometry, quantum wells, and optical spectrum of nanomaterials, growth and geometry influence to physical properties and influence of environmental to physical properties of nanomaterials. This is our center. Our center is one of the best equipped laboratory in Azerbaijan. Our center investigation direction is mainly in three directions. One of direction is triboelectric nanogenerator. Second direction is direction supercapacitor development. And third direction is biosensors. And we have innovative technology group which developing new technology. Now this group studying in area nano biomaterials. Quantum nanomaterials may be various type: quantum dots, wires, spheres, tubes, and others. The electrons and charge carriers is in limited space, and the state of electrons also dependent from geometry, from structure of nanoparticles. Tube, wire, or sphere, the electron will have different state, and this will be influence the quantum spectrum. And the state of all charge carriers will be described by Schrödinger equation, and the electronic spectrum also will be defined with Schrödinger equation. In nanoparticles, the dependence of energy from wave vector will be changed because in particle size we have active bonds, and they will be interacted with charge carriers in nanoparticles, and this will be change dependence of energy from wave vector, because it effective mass also will be changed dependence of defect structure, geometry of particles. Let us see growth process nanostructure by cellular process. This process is different from other growing process. This is simple process, and in this process we have thermodynamic equilibrium or between cations or between anions. This consists from process of growth consists from fourth stage, absorption of cations, rinsing process, absorption of anions, and rinsing process. And in this process, we can manage the rate of growth with changing of concentration or temperature of solution. And in this case, we have thermodynamic equilibrium between ions in solution and such kind of particles in nanocrystals. And we can manage temperature, concentration, and with this way we can influence the growing process. The chemical potential of ions or particles in solution will be dependent from temperature and concentration of solution. With changing of concentration or temperature of solution, we can change chemical potential in solution. This will be influenced to means of chemical potential in forming particles. But the changing of chemical potential will be by creating of defects of or by changing of crystallic structure. And with changing this parameter, we can change the mobility of charge carrier, the potential energy of charge carriers, energy. This will be changed the energy spectrum of charge carriers and nanoparticles, and this will be lead to changing of effective mass and optical properties of materials. We analyze literature for forming zinc sulfide and cadmium sulfide nanoparticles depends from concentration of solution. And we see that with changing of concentration of solution changes the crystalline structure of nanoparticles. And these nanoparticles can form in cubic or hexagonal phase depending of concentration and other parameters of crystallization medium. With changing of chemical potential, we can manage structure, and also we can influence the band gap of materials. There we show the dependence of band gap and structure from concentration of solution. This is this data is from literature. The literature we show here. And when we are immersing particles to electrolyte solution, there we have dipole ion electron interaction. Very strongly interaction is ion electron interaction, as such kind of interaction will be to influence electronic state in nanoparticles, because the charge carriers in particles will be interact with double electrolyte wire, and this will be change the potential energy of charge carriers in nanoparticles, and we will have additional potential energy for charge carriers in nanoparticles, and this will be leads to changing of electronic spectrum, also optical properties of materials, and particularly will be changing also the band gap of materials. We use for testing this hypothesis, cadmium sulfide nanoparticles, and use it as environmental. We use it various solution of cadmium of nitrate, cadmium acetate, natrium chloride, and this solution have various concentration, 0.01, 0.1, and 1 mole concentration, and variation of concentration will be varied the density of charge carriers around